Welcome. Over the next 5 hours, we're going to cover the core LeetCode and DSA patterns for coding interviews. In this course, we'll focus on reusable patterns that sit behind LeetCode problems so that when you see a new LeetCode problem, you can identify the underlying pattern and apply it. Now, there are two ways people prepare for LeetCode and DSA interviews. The first approach, which is the most common, is problem-based. You pick a list, maybe let's say blind 75 or the top 100 LeetCode problems, and you solve them one at a time. For each column, you learn the specific solution and move on to the next one. But here's the thing. In interviews, you almost never get the same exact problem. Very often, the interviewers will change something. Maybe they'll change the constraints. Maybe there's an extra condition. When that happens, knowing the pattern underlying will help you adapt quickly. Now, the second approach, which is what this course teaches, is pattern based. Instead of learning individual solutions, you learn the underlying techniques. The complement lookup pattern, for example, is one technique, but it solves two sum problem, subarray sum equals k problem, and also continuous subarray sub problem. There are three different problems, but they all have one underlying common pattern. So when you study this way, a new problem is not necessarily a challenge. It is a variation of a pattern that you already know. That is the difference that this course is designed around. Now here's exactly what we will be covering in this course today. For each pattern, we'll follow the same structure. First, the recognition signal. How do you know this pattern applies? Then the brute force approach and why it is too slow. Then the optimized technique with the real code. Then a step-by-step trace walking through the solution with actual values. And finally, the common mistakes candidates make and how to avoid them, and what interviewers are specifically looking for in interviews. Now here are the sections that we'll be covering in today's course. We'll start with 35 minutes on array and hashing patterns, covering topics like hash sets, hash maps, frequency counting, and the complement lookup pattern. Then we'll spend 25 minutes on prefix sums patterns, covering topics like range queries, subarray sums, and the product prefix and suffix techniques. Then we'll spend 30 minutes on two pointers patterns, covering problems like three-sum problem and container with most water problem. Followed by, we'll spend 35 minutes on sliding window patterns, covering topics like both fixed and variable windows with problems like longest substring without repeating characters and minimum window substring. Then we'll spend 40 minutes on stack and monotonic stack patterns, covering topics like matching, next nesting, next grid element, daily temperatures, and the largest rectangular histogram problems. After that, we'll spend 25 minutes on binary search fundamental problems and patterns, in which we'll cover topics like sorted arrays, rotated arrays, and lower and upper bound patterns. Followed by the 30 minutes on binary search on the answer space pattern, covering topics like and problems like, for example, Koko eating bananas and capacity to ship packages LeetCode problems. After that, we'll spend 35 minutes on linked list patterns covering reversal, fast and slow pointers, merging, and cycle detection patterns. And finally, we'll spend 25 minutes on pattern recognition and reference sheets that tie everything together into a decision framework that you can apply in your interviews. Every section here includes worked examples, interview practice problems, and a cheat sheet for revision. So arrays are the most common data structure in coding interviews. Nearly every problem starts with an array or string as an input, and the gap between a slow O of n squared solution and a fast O of n solution almost always comes down to one decision, which is to know when to trade extra space for faster time by using a hash map or a prefix sum. This section covers three foundational tools that eliminate the repeated work. The first is the hash set, which eliminates repeated searching. So instead of scanning an entire array to check if an element exists, a hash set answers that question O of 1. The second is the hash map, which eliminates the repeated counting. Instead of looping through the array multiple times to count occurrences, a hash map builds a complete frequency table in a single pass. The third is a prefix sum, which eliminates repeated range calculations. Instead of adding up elements from index I to j every time someone asks, a prefix sum pre-computes the cumulative totals so that any range query becomes a single subtraction. Once these three tools become natural to you, a large portion of medium difficulty array problems will become pretty straightforward. The hard part is not writing the code, the hard part is actually recognizing which tool fits the problem. And this is exactly what this section will cover. So now let's talk about these patterns in what companies and what type of interviews they generally appear. So the core idea for this entire section is pretty simple. When repeated lookup is a bottleneck, you should be using hashing. When repeated range calculation is a bottleneck, you should be using prefix sums. Both patterns trade off and space to eliminate an entire nested loop. So let us start with the simplest one of three, which is the hash set. So the first pattern is the most basic, but it is also one that reveals whether candidate instinctively reaches for efficient tools or defaults to a brute force approach. Here is the recognition signal. For example, let's say the problem asks, okay, does this element exist? Or have you seen this before? And your current approach is scanning the entire array every time you need to check. That scan is going to be O of n per check. If you're doing it inside a loop, you will end up with O of n squared as total. Now, a hash set will solve this problem by storing unique elements in a data structure that supports O of 1 average time lookup. Instead of scanning the array from start to end every time, you insert elements into the set as you go, and checking whether something exists it becomes a constant time operation. So now let us compare the three approaches to this kind of problem. So the first approach is a brute force approach. So for every element, you scan the rest of the array with a linear search. Each lookup takes O of n, and if you do this for all n elements, the total time will become O of n squared. Now the space is O of 1 because you're not using any extra data structure. The second approach is to sort the array first, then you use binary search for each lookup. Sorting will cost you O of n log n upfront, and each binary search will also takes O of log n. So then the total becomes O of n log n, which is better than O of n square. But sorting may or may not need extra space depending on the sorting algorithm. The third approach is a hash set. You make a single pass through the array, inserting each element into the set. Each insertion is O of 1 on average. Each lookup is also O of 1 on average. The total time is O of n. The space is O of n because the set stores up to n elements. This is a classic space for time trade. You use O of n extra memory to bring the time down from O of n squared to O of n. The template is clean. Create an empty set called scene and loop through each element in the array. For each element, check if it is already in the set. If it is, you have just found a duplicate and then you just return the true. If it is not, you add it to the set and then you continue. If you finish the loop without finding a duplicate, then you return false. Now, when should this pattern come to mind? There are clear signals in the problem statement. If the problem says, okay, check if X exists, then think of hash set. If the problem says something like, find if we have seen this before, think of hash set as well. And if it says something like, let's say remove duplicate or count distinct elements, you should also consider hash set. And again, anytime, you're considering finding, yourself, writing a membership check inside a loop, that is a signal to switch from a list to a set. Now, there's one common mistake that is worth calling out because it causes real problems in interviews. So in Python, checking if an element in a list, using let's say X in my list is O of n. It scans the entire list. But if we say X in my set, which is O of 1, and that uses hashing. So the syntax looks almost identical, but the performance difference is massive. This single mistake can turn what should have been an O of n solution to again back to O of n square, and on larger inputs, that means the solution exceeds the time limit. So again, always use a set when you need fast membership checks. And again, just like Python had this gotcha that we just covered, make sure whichever programming language you're using in the interviews, whether it's C#, Java, or C++, you exactly know how to use hash sets in that programming language. Now, hash set existence checks are the simplest pattern in this section, but they do set up everything that comes next because the hash map patterns we are just about to cover using the same O of 1 lookup principle are used for much more complex operations. So the hash set answers questions like, okay, does this element exist? Whereas the hash map answers a more detailed question, which is how many times does this element appear? Now here's the recognition signal. The problem involves counting occurrences, finding the most or least frequent element, or grouping items by some property. You find yourself wanting to know how many times a specific value appears in the array. A hash map, which is also called a dictionary, maps each element to its count. Instead of using nested loop where the outer loop, picks an element and the inner loop counts how many times it appears, you make a single pass through the array. For each element, you increment its count in the map. So by the end of that one pass, you have a complete frequency table. The template here is pretty straightforward. You create an empty dictionary called, let's say frequency or FREQ, and you will loop through each element. For each element, you use the get method with a default of 0, add 1, and store it back. After the loop, your dictionary is a frequency or FREQ that will contain every unique element and its count. Now let us compare the different approaches. The brute force approach uses nested loops. For each unique element, it scans the entire array to count occurrences. That is O of n per element and O of n squared total. The sorting approach sorts the array first in O of n log n, and then it makes a linear scan to count adjacent groups. That is better, but is still slower than necessary. The hash map approach does everything in O of n time and O of n space. One pass, one increment per element. Now, there are several common operations you can do once you have a frequency map. Counting occurrences is a basic one. Checking if a frequency matches a target is how you solve problems like valid anagram and ransom note. Finding the maximum frequency gives you the most common element. Comparing two frequency maps directly tells you whether two strings are anagrams of each other or not. And decrementing counts and removing entries when they reach 0 is a technique used in sliding window problems with character constraints. And here's something important for interviews. Let's say when an interview asks you, okay, can you do better than O of n log n? The answer is almost always yes with the hash map in O of n. That is the single most common optimization in array problems. The interviewer is testing whether you know that hashing can replace sorting when you do not actually need the elements in order. Frequency counting with hash maps appears in at least 15 of the top 100 LeetCode problems. Interviewers treat it as a baseline skill, so if this operation is not automatic for you, the harder patterns that build on top of it will also be difficult. So this is a very important foundation. Make sure it is solid, before you go on to more harder category problems. Now let us look at what happens when you use a hash map, not just for counting, but also for finding specific partners. So this is a pattern that appears in more interview problems than almost any other single technique. It is the idea behind toSum, and it generalizes it to at least 8 other problems. Now here is the recognition signal. The problem asks you to find two elements that combine to satisfy a condition such as a target sum or a target difference. And for each element, you can compute exactly what the other elements needs to be. Now let us understand why this matters by looking at the brute force approach first. Now if you need two elements that add up to a target T, the most obvious approach is to try every pair. Take the first element, check it against every other element, and then you take the second element, you again check it against every remaining element. That is two nested loops, and yes, that is O of n square time. But here's what makes the brute force not ideal solution. For each element x, you must already know what its partner must be. If the target is t, the partner is t minus x. That is a specific computable value. You do not need to search through the entire array for that bit. You just need to know whether you have already seen that value. And checking whether you have seen a value is exactly what a hash map does in O of 1. So now the approach changes from check every pair to something much more efficient. Now you walk through the array one element at a time. For each element x, you compute the complement, which is t minus x. Then you check the hash map. Have you seen this complement before? If yes, we have found our pair. If no, we store the x in hash map and we move on. One pass and it will be O of n total. The function creates an empty hash map. Let's call it scene. It iterates through the array using both the index and the value. For each number, it computes the complement as target minus the current number. It checks whether the complement exists in the map. If it does, it returns the store index and the current index. If it does not, it stores the current number as a key and its index as a value, and then it continues. Now there's a mistake that many people make, and it's pretty subtle, so please be careful about it. The order of operations do matter. You must check for the complement first, then store the current element. If you store the current element first and then you check, an element can match with itself. Let's say consider the array something like 3 and 3 with the target 6. If you store the 3 at index 0 before checking, then when you check for the complement of 3, you find the 3 you just stored, and you return the index 0 paired with index 0, and that is wrong. By checking first and storing after, the element at index 0 looks for 3 in an empty map, finding nothing, and stores itself. When index 1 arrives, it complements this 3, and now it currently finds the 3 from index 0. This reason this pattern is so important because it goes beyond the two-sum problem. The mental model should be like compute what you need, then check if you have already seen it. That is the foundation for at least 8 other LeetCode problems. We'll see it applied to prefix sum problems, to digit sum pairs problem, to modular arithmetic problem as well. Every time the same 4 steps will be like, okay, compute the partner, check the map, store if it's not found, and then move forward. Now let us now trace through a concrete example step by step. Now let us apply the complement lookup pattern to the most classic problem in all of coding interviews, which is a two-sum problem, which is LeetCode problem number 1. The input is the array, let's say 2, 7, 11, 15 with a target of 9. We need to find 2 elements that add up to 9 and return the indices. We start with an empty hash map called, let's say, scene. At index 0, the element is 2. The complement is 9 minus 2, which is 7. We check the map. Is 7 in scene? No? Okay, the map is empty. So we store 2 and then with the syntax, now scene contains 2 colon 0. So 2 is a key and the 0 is a value. At index 1 is now the element is 7. The complement is 9 minus 7, which is 2. So we check the map. Is 2 in scene? Yes, it is with the index 0. So we return 0, 1. So we found the answer in just 2 iterations. The brute force would have checked all 6 possible pairs, whereas the complement lookup checked only 2 elements and was done. Now let us look at why this is O of n instead of O of n squared. In the brute force approach, for each element we scan all other elements to find a match. That is O of n per work per element. So that becomes O of n squared in total. In the complement lookup, for each element we compute the complement in O of 1 and check the hash map in O of 1 as well. That is O of 1 work per element and O of n in total. The space complexity goes from O of 1 to O of n now because we store elements in the hash map. This is the same space for time trade we have seen with hash sets, just applied in a more targeted way. And here's something important about how to present this in an interview. Two-sum problem is often the first question in a coding interview, and it's like very standard and pretty common as well. The interviewer is not testing whether you know the answer. Almost every candidate has seen two-sum before, when they're practicing LeetCode problems. What the interviewer is watching is that your thinking process. For example, do you start with the brute force, clearly identify that the inner search is a bottleneck, and then you optimize by replacing that inner search with the hash map lookup? Walking through that progression out loud, even if you already know the optimal solution, will show the structured thinking that interviewer is looking for. It shows that you can analyze and improve, not just recall from memory. So if your two-sum solution is not automatic by now, you should be practicing it until you can finish this problem in within a few minutes. This problem is a gateway problem to every hash map pattern in this section, and the speed at which you solve it sets the pace for the rest of the interview. Now let us see how the same pattern applies to a whole family of other problems. The complement lookup pattern is not limited to the two-sum problem. The same mental model, okay, let's compute what you need and check if you have already seen it, appears in many different problems. The only thing that changes is what you store and what you look up. In two-sum problem with a target sum, you store each number's index and you look up target minus the current number. In a two-sum variant with a target difference, you store each number's index and you look up current number plus target. or current number minus target. In a problem where you need to pair numbers with equal digit sums, you store the digit sum as a key and you check whether another number shares the same digit sum. In subarrays, sum equals a k problem, you store the running prefix sums and you look up prefix sum minus k. In continuous subarray sum problem, you store the prefix sum modulo k and you check whether the remainder has appeared before. Every row in this list follows the same 4-step logic. Step 1. Compute what the partner must be. Step 2. Check the hash map for that partner. Step 3. If not found, store the current element. And step 4. Move to the next element. The key insight is this. When a problem asks you, let's say, find two things that satisfy a condition, do not start with nested loops. You should be asking yourself, okay, for each element, do I already know what its partner must be? If the answer is yes, then you can compute the partner, look it up in a hash map, and solve the problem in O of n. The single insight applies from easy problems like two-sum problem all the way to harder problems like counting subarrays with a given sum. And this is also you should something note down. The complement lookup patterns has 4 steps. Define the pattern, check the map, store if it's not found, and then move forward. This 4-step sequence is worth memorizing because it appears in so many problems that becomes a reliable default approach for any find a pair question. Interviewers expect you to recognize this pattern within 30 seconds to a minute of reading a two-sum variant. If you begin with nested loops and do not move to complement lookup quickly, it tells the interviewer that you are solving from scratch each time instead of recognizing a known pattern. Pattern recognition speed is also a core skill that separates, it'll make your life much more easier in interviews. Now let us look at a different use of hash maps, one where the key is not the element itself, but a transformed version of it. So far we have used hash maps in 2 ways, counting how many times an element appears and looking at whether a complement exists. Now we use a hash map for a third purpose, which is to group elements that share a common property. Here is the recognition signal. Let's say the problem asks you to group elements together, but the grouping is not based on the elements themselves. It is based on a transformed version. Let's say different elements should end up in the same group because you share something in common after you applied some transformation. So the core idea is this. You should build a hash map where the key is a normalized or transformed version of each element and the value is a list of all original elements that produce that key. You make one pass through the input. For each element you compute the key and then you add the element to the list for that key. By the end of the pass, all groups have been formed. Now here is the template. You create an empty dictionary, let's say called groups, and you loop through each item. For each item you compute the normalized key by calling some function on it. If that key is not in the dictionary yet, you create an empty list for it. Then append the item to that keys list. At the end, you return all the lists. The time complexity will be O of n times k, where n is the number of elements and k is the cost of computing the key for one element. The space complexity is O of 1n, because you have to store all the elements in the map. Now let us look at different normalized keys, look like across different LeetCode problems. For the group anagrams problem, the raw element is a string like let's say 8 and the normalized key is the sorted characters which is the AET. All anagrams produce the same sorted form so they end up in the same group. For grouping by digit sum problem, the raw element is like a number like 42 and the key is 6 which is 4 plus 2. Numbers with the same digit share a key. For grouping by length problem, the key is simply the length of the string. For grouping by first letter problem, the key is the first character. And for grouping shifted key strings problem, the key is a tuple of relative distances between consecutive characters. Shifted versions of the same pattern produce the same distance tuple. The important thing to notice is that the template stays the same across all these interview problems. The only thing that changes is the key function. Once you recognize that a problem is asking you to group elements by some shared property, the question then becomes, okay, what is the right key function? Finding the key function and the rest of the solution follows the template exactly. Now, group anagrams problem is one of the top 20 most frequently asked problems in coding interviews. So now let us walk through that in detail. So now the problem is group anagrams problem, which is LeetCode problem number 49. Now given an array of strings, we have to group all the anagrams together. Two strings are anagrams if they contain the same characters and the same frequencies. So strings like eat, t, and 8 are all anagrams of each other because they all contain one a, one e, and one t. Let's say the input is an array of strings which consists of eat, t, tan, 8, nat, and bat. And then the expected output would be groups, something like eat, t8, one group, and then tan and nat as second group, and bat will be just by itself. So the brute force approach would be to compare every pair of strings and check if there are anagrams. To check two strings anagrams, you could sort both and compare. That comparison costs you like O of k log k, where k is the string length. And checking every pair is O of n squared comparisons. So then the total becomes O of n squared times k log k. For large list of strings, that's pretty slow and it's not ideal for interview solution. But this is a grouping problem. Elements that share a property, being anagrams of each other, need to end up in the same bucket. That is exactly the pattern from previous slide. We just need the right key function. So now what makes two strings anagrams? They have the same characters and the same frequencies. So if we sort the characters of each string, all anagrams produce the same sorted result. Eat sorted becomes AT, T sorted becomes AT, 8 sorted becomes AET, and that sorted form is actually our key. For solution, we start with an empty dictionary. Let's say we call it groups. For each string in the input, it sorts the characters to produce the key. In Python, for example, we convert the sorted result to a tuple so it can be used as a dictionary key. If that key is not in the dictionary, we create an empty list. Then we append the original string to that keys list, and at the end, we return all the lists. The time complexity for that would be O of n times k log k, where n is the number of strings and k is the maximum string length. The k log k comes from sorting each string. The space complexity is O of n times k to store all strings in the hash map. This is a significant improvement over the brute force approach. We went from O of n squared times k log k to O of n times k log k. We did this by replacing the pair-by-pair comparison with a single pass grouping. But now let's think about it. Can we do even better? So the next slide will show you an alternate key that avoids sorting entirely. Now let us trace through the solution step by step to make the mechanics more concrete. Let's say the input here is, an array of strings with eat, t, tan, 8, nat, and bat. We start with an empty, dictionary. Let's say we call it groups. We process eat first. Sorting its characters gives us AET. This key is not in the dictionary, so we create a new list. AET colon array of EET. Next is TEA. Sorting gives that, for that it gives us AET. This key already exists, so we append AET colon eat comma T in the array. Next is tan. Sorting gives us ANT, so new key will be AT colon eat and T in an array and ANT colon TAN in an array. Next is 8. So we sorting gives us AT. So again we append the AT and then it becomes AT, T and 8. And then the second part is the ANT colon tan. Next is NAT. So sorting gives us ANT and then we append the AT and that gives us EET, TEA and ATE. And then ANT becomes tan and NAT. Finally, for bat, sorting gives us ABT, so new key becomes AT and then the array eat, T and 8, and then ANT colon, then the array tan and NAT, and then ABT colon bat. So now the output is array of arrays of strings. So the first part is eat, T and 8, the second part is tan and NAT, and the third part is, BAT. Each group contains all the anagrams of each other. One pass through the input and all groups were formed. Now there is an alternative approach that avoids the sorting. Instead of sorting each string in O of k log k, you can build a character frequency count in O of k. For this, you should be creating an array of 26 zeros, one for each letter. Walk through the string and increment the count for each character. Convert that array to a tuple and you use it as a key. The result is the same. All anagrams produce the same frequency tuple, but the cost per key drops from O of k log k to O of k. Now, which one should you be using? For short strings, the sorted key is simpler to write and the performance difference is negligible. For long strings, the character count key is faster because O of k is better than O of k log k when k is large. Now here's something important for interviews. If you present the sorted key solution and the interviewer asks you, okay, can you do better? You need to pivot to the character count key approach. This shows to the interviewer that you understand the complexity difference and you are not locked to the single approach. Being able to discuss both options and explain the trade-off is exactly the kind of depth that's the interviewer is looking for. Now let us now test what we have covered so far with some more practice problems. Now let us test what we have covered so far. For each problem, now you try to identify the pattern before reading the answer. This is a core skill interviewers are evaluating in the interview. So for example, can you recognize which tool fits from the problem description alone? So for problem 1, you're given an integer array. You should be returning true if any value appears at least twice, false if every element is distinct. Now you should need to tell me what pattern applies here. Now before looking at answer, please think about it for a minute and then we move forward. So now the answer for this is hash set for existing checks, which we covered in slide 10. For this, you walk through the array, adding each element to a set. Before adding, you check if the element is already in the set. If it is, you have found a duplicate, and then you return true. If you finish the loop without finding one, then you return false. For this, the time complexity will be O of n, and space complexity will be O of n. Now problem number 2. Let's say you are given two strings s and t. Determine if it is t is an anagram of s. And now please tell me what pattern you think will be applied here. Again, the answer for this will be hash map for frequency counting from slide 11. You should be building a frequency map of s, counting how many times each character appears. Then you go through t and decrement each count for each character. If all counts reach 0 at the end, the strings are anagrams. Again, the time complexity for this is O of n and space complexity is O of 1 because alphabet is fixed at 26 characters, so the map never grows beyond 26 entries. Now problem number 3. Let's say given an array of integers and a target, you need to return the indices of two numbers that add up to the target. Each input has exactly one solution. Now what pattern does apply here? And again, the pattern is the complement lookup pattern, which we covered in slide number 12. For each element, you compute the target minus the element, check the hash map for that complement. If found, you return both indices. If not found, you store the current element and you move on. The time complexity for this is O of n and space complexity for this is O of n. The important thing to notice across all of these problems is this. The real skill is not writing the code. The code for each of these is pretty short and straightforward once you know which pattern to apply. The real skill actually becomes recognizing the pattern from the problem description within the first 60 seconds. If you can do that, the code will follow naturally. If you cannot, then you will spend time exploring different approaches that might not lead anywhere. In a real interview, you will not see the LeetCode problem number, and you will also not see a title that will hint directly to an approach. You will see just a problem statement, and then you must classify it yourself. That classification step is what these practice problems will train you on. Now let us move to the second major pattern in this section, which is prefix sums pattern. So we have now covered 3 patterns built on hashing: hash sets for existing checks, hash maps for frequency counting, and complement lookup for finding pairs. All 3 solves the same type of bottleneck, which is repeated searching. But not every array problem is a search problem. Some problems are about repeated calculation, specifically calculating the sum of a range of elements over and over again. Now here's this kind of scenario. Let's say you're given an array of integers and you need to answer many queries. Each query asks you, Okay, what is the sum of elements from index I to index j? The straightforward approach is to loop from I to j and add up all the elements for every query. That works, but for each query it will take O of n time in the worst case. Let's say now if you have q queries for an array size of n, the total cost will become O of n times q. For large arrays with many queries, this will become pretty slow. Now the question is, why are we recalculating from scratch every time? Most of these ranges actually overlap. The sum from index 2 to 7 share most of these elements from, with the sum from index, let's say 2 to 8. We are adding up the same elements repeatedly. This is the exact same time of waste, we eliminated with hashing, just applied to, addition instead of lookup. A prefix sum approach eliminates this waste entirely. The idea is to pre-compute the cumulative sum up to each index once in a single pass. After that, the sum of any range can be answered with a single subtraction. Let us walk through how this works. Let's say take the array 2, 4, 1, 3, 5. The prefix sum at index 0 is 2. At index 1 it is 2 plus 4, which is 6. At index 2 it is 6 plus 1, which is 7. At index 3 it is 7 plus 3, which is 10. And at index 4 it is 10 plus 5, which is 15. So the prefix sum array is 2, 6, 7, 10 and 15. Now let's say someone asks, okay, what is the sum from index 1 to 3? That is, the sum of 4 plus 1 plus 3, which equals 8. With the prefix sum array we have just built, we compute this as a prefix at the index 3 minus prefix at index 0. That is 10 minus 2, which is equals 8. One subtraction and there's no looping involved. So here's the formula. The sum of elements from index I to j equals prefix at j minus prefix at I minus 1. Prefix at j contains the sum of everything from the start through index j. Subtracting prefix at I minus 1 removes everything from index, before index I. What remains is exactly the range we want. Without a prefix sum, every range query scans the subarray in O of n. Now with the prefix sum array, every range query is a single subtraction of 1. For a problem with q queries on an array of, let's say, size n, the total cost now drops from 0 n times q to 0 n times n plus q. So now you pay O of n once to build the prefix sum and then O of 1 per query. Now this is a part that what commonly happens, people do mistakes in interviews. Let's say what happens when the range starts as index 0. The formula needs a prefix at I minus 1, which would be prefix at negative 1. That does not exist. So this edge case is the number one source of bugs in prefix sum solutions. The next slide covers a clean technique that eliminates this edge case entirely. So the edge case from the previous slide, where the range starts at index 0, has a clean solution. Instead of building the prefix sum array with the same length as the original array, we build it with the length n plus 1 and set the first element to 0. The function here, as you can see, creates an array of n plus 1 zeros, then iterates through the original array. For each index I, it sets the prefix at I plus 1 to the prefix at I plus the current element. The result is a prefix array where prefix is at 0 is 0, prefix at 1 is the first element, prefix at 2 is the sum of the first two elements, and so on. Now with this convention, the sum from index I to j inclusive is simply prefix at j plus 1 minus prefix at I. No special case for index 0 is needed now. This formula works uniformly for every range. Now let us trace through this with the array 2, 4, 1, 3, 5. The prefix array has 6 elements. Prefix at 0 is 0. Prefix at 1 is 0 plus 2, which is 2. Prefix at 2 is 2 plus 4, which is 6. Prefix at 3 is 6 plus 1, which is 7. Prefix at 4 is 7 plus 3, which is 10. And prefix at 5 is 10 plus 5, which is 15. So now the full prefix array becomes 0, 2, 6, 7, 10, and 15. Now let us test it. Now the sum of the entire array from index 0 to index 4 is prefix at 5 minus prefix at 0. That is 15 minus 0, which is 15, and that is correct. The sum from index 2 to index 4 is a prefix at 5 minus prefix at 2. So that is 15 minus 6, which is 9. And we can verify. 1 plus 3 plus 5 equals to 9, which is correct as well. So now no special case was needed for any range. The formula is always prefix at j plus 1 minus prefix at I. Now this is something you should note down. You should always be building the prefix sum array with the length n plus 1 and a leading 0. This eliminates off by 1 errors, which are the number one bug in prefix sum solutions. Every time you write a prefix sum in an interview or in practice, you should be using this convention. And here's something important for interviews as well. When you write a prefix sum solution, you should state the formula out loud to the interviewer. The sum from I to j is, prefix at j plus 1 minus prefix at I. This will tell the interviewer that, you understand the mechanics and you are not just copying code from memory. Explaining the formula shows understanding, so you should be writing the code which shows the implementation. And, interviewers, they value both. So off by 1 errors in prefix sum indexing are, one of the most common errors here. So, you make sure you get the right approach when you're doing this. The leading 0 convention that we just discussed eliminates this problem completely, so you should be using this in your interviews every time. Now let us see what happens when we combine prefix sums with the complement lookup pattern from earlier. Now, this is one of the most frequently asked medium difficulty problems in coding interviews, and it's the problem where two patterns from this section come together into a single solution. So the problem is subarray sum equals k, which is LeetCode problem number 560. Given an integer array and an integer k, you should be returning the total number of continuous subarrays whose sum equals k. Now before we solve it, let us understand why this problem matters. It tests whether you can combine two ideas, prefix sums pattern and complement lookup pattern. Candidates who have memorized two sum problems list, they often face difficulties here because they do not see the connection between these two patterns. However, the candidates, who actually succeed are the ones who recognize the complement lookup logic applies not just to individual elements, but also to prefix sums as well. Now, the brute force approach here, will be using the two nested loops. So the outer loop, it picks up a starting index. The inner loop extends the subarray one element at a time, maintaining a running sum. Every time the running sum equals k, we increment the count. This works correctly, but the time complexity again is O of n squared. So for arrays with, let's say, very large amount of elements, that is pretty slow, and again it's not ideal for the interview solution. So where is the waste? We are computing the sum of every possible subarray from scratch, but we know from the prefix sum pattern that the sum of subarray from index I to index j is prefix at j minus prefix at I minus 1. If we want that sum to equal k, we need prefix at j minus prefix at I minus 1 equals k. Rearranging, we get prefix at I minus 1 equals prefix at j minus k. Now this should look familiar. For each prefix sum value, we are asking, have I seen previous prefix sum that equals the current prefix sum minus k? That is a complement lookup pattern applied to prefix sums instead of array elements. Now the optimized solution here, it maintains a running prefix sum and a hash map that counts how many times each prefix sum value has appeared. For each element, we add it to the running prefix sum. Then we compute the complement, which is prefix sum minus k. If that complement exists in the hash map, it means there are some earlier positions where the prefix sum was exactly prefix sum minus k. The number of such positions is the number of subarrays ending at the current index with the sum equal to k. We add that count to our result and then we record the current prefix sum in the hash map. Now the hash map is initialized with 0:1, so this is critical, and we'll explain exactly why in the trace on the next slide. The time complexity is O of n and the space complexity is O of n for the hash map. Now this problem is pretty common in many tech companies because it directly tests whether you can combine prefix sums pattern with hash map lookups. Now let us trace through a concrete example to make sure every step is clear. Now let us trace through the optimized solution with let's say an input array of 1, 1 and 1 at k equals 2. We want to count how many continuous subarrays sum equal to 2. So now we start with the prefix sum equal to 0. Prefix counts initialized to 0:1 and count equals to 0. At index 0, the element is 1. We add it to the prefix sum, which becomes 1. The complement is prefix sum minus k, which is 1 minus 2, which is negative 1. We check the hash map. Is negative 1 in prefix counts? No? Okay, so count stays at 0. We then record prefix sum 1 in the map. Prefix counts, it's now becomes 0 colon 1 comma 1 colon 1. At index 1, the element is 1. Prefix sum becomes 1 plus 1, which is 2. The complement is 2 minus 2, which is 0. We check, okay, is 0 in prefix counts? Yes, with a count of 1. So we add 1 to the count. Count is now 1. We record prefix sum 2. And prefix counts now becomes 0 colon 1, 1 colon 1, and 2 colon 1. At index 2, the element is 1. Prefix sum becomes 2 plus 1, which is 3. The complement is 3 minus 2, which is 1. We check, is 1 in prefix counts? Yes, with a count of 1. So we add 1 to the count. Count is now 2. We record prefix sum 3. Prefix counts is now 0 colon 1, 1 colon 1, 2 colon 1, and 3 colon 1. The final count is 2. The two subarrays are 1 comma 1 from indices 0 to 1 and 1 comma 1 from indices 1 to 2, and both sum to 2. Now let us address why prefix counts start with 0 colon 1. This handles subarrays that start from index 0. If the prefix sum at some index equals exactly k, then the complement is prefix sum minus k, which equals 0. Without 0 colon 1 in the map, the complement 0 would not be found, and we would miss that valid subarray. In our trace, when prefix sum reached 2 at index 1, the complement was 0. That 0 came from the initial entry we seeded. Without it, we would have missed the subarray 1, 1 starting at index 0. This initialization is the single most common bug candidates introduce when they're writing the solution for memory in interviews. Now one more thing. A common mistake is to try, use a sliding window for this problem. Sliding window works well when all elements are positive because shrinking the window always decreases the sum. But this problem does allow negative numbers. With negative numbers, shrinking the window might actually increase the sum, which violates the assumption that the sliding window depends on. So the prefix sum plus hash map approach is the correct one here. Now let us look at a related but different problem that applies the prefix idea to multiplication. We have seen how prefix sums pre-compute cumulative addition for fast range queries. Now let us look at a problem that applies the same directional pre-computation idea but to multiplication and with a constraint that changes the approach. Now the problem is product of array except self, LeetCode problem 238. Given an array, return a new array where each position contains the product of all elements in the original array except the element at that position. But the constraint is you cannot use division. So now without that constraint, the solution would have been simpler. Compute the total product of the entire array, then divide by each element. But the problem is that division is not allowed. And even if it was, this approach fails when any element is 0 because dividing by 0 is undefined. So the constraint is not arbitrary, it reflects a real edge case. Now the insight is to split the problem into two parts. For any index I, the answer is the product of everything to the left of I multiplied by the product of everything to the right of I. These are two independent quantities. Each one can be computed with a single pass through the array. Now the first pass goes left to right. We maintain a variable called left product starting at 1. At each index, we store left product in the results array, then multiply left product by the current element. After this pass, result at index I holds the product of all elements before index I. The second pass goes right to left. We maintain a variable, let's say we call it right product, starting at 1. At each index, we multiply result at that index by right product, then multiply right product by the current element. After this pass, result at index I holds the product of all elements except the one at index I. The time complexity for this is O of n. Two linear passes will be involved here. The space complexity will be O of 1 because the results array is the required output and does not count as an auxiliary space. Now many candidates write this with two separate arrays, one for left products and one for right products. That approach is correct, but it uses O of n extra space. In interviews, the follow-up question is almost always, can you do it without the extra arrays? Learning the in-place version from the start will avoid that follow-up entirely. Now the deeper principle here goes beyond the single problem. Anytime each position in an array depends on the information from both directions, consider making two passes, one forward and one backward. This same technique appears in the trapping rainwater problem, where each position depends on the tallest bar to the left and to the right. It appears in the candy distribution problem, where each child's allocation depends on the neighbors in both directions. Recognizing this two-pass patterns unlocks a whole family of LeetCode problems. Now let us trace through a concrete example to make this mechanics more solid. Now let us say we are given an array 1, 2, 3, 4. The left pass goes from index 0 to index 3. We start with the left product equal to 1. At index 0 we set result at 0 to left product, which is 1. The left product becomes 1 times 1, which is 1. At index 1, result at 1 is set to 1. Then left product becomes 1 times 2, which is 2. At index 2, result at 2 is set to 2. Then left product becomes 2 times 3, which is 6. At index 3, result at 3 is set to 6. Left products, might become 6 times then 4, which is now 24. Now after the left pass, the result array is 1, 1, 2, 6. Each position holds the product of all elements to its left. Now the right pass goes from index 3 down to index 0. We start with the right product equals to 1. At index 3, result at 3 is 6 times 1, which is 6. A right product becomes 1 times 4, which is 4. At index 2, result at 2 is 2 times 2 or 4, which is 8. And the right product becomes 4 times 3, which is 12. At index 1, result at 1 is 1 times 12, which is 12. And right product becomes 12 times 2, which is 24. At index 0, result at 0 is 1 times 24, which is 24. And right product becomes 24 times 1, which is 24. After the right pass, the result array now is 24, 12, 8, 6. Now let us verify. For index 0, the product of all elements except 1 is 2 times 3 times 4, which is 24, which is correct. For index 2, the product of all elements except 3 is 1 times 2 times 4, which is 8, which is correct. Now a common mistake is actually building separate left and right arrays. And this approach produces a correct answer, but it uses O of an extra space. The in-place approach we just traced uses a result array for the left pass and a single variable for the right pass, achieving one extra space. In an interview, you should always aim for this version. And here's something important for how to present the solution. Before writing code, you should be explaining to the interviewer the two-pass strategy. So you should say something like, okay, I will first make a left to right pass to accumulate the left products, then a right to left pass to multiply in right products. This gives the interviewer the overall plan before they read your code. Interviewers follow code much more easily when they already know the high-level approach, so please explain that to them. Now, product of array except self is a pretty common interview problem, pretty common LeetCode data structure algorithm problem, and frequently appears because it tests prefix and suffix thinking without being a prefix sum problem. It also reveals whether you understand the underlying principle or it's just been memorized, the sum version. Now let us practice identifying the right pattern across different prefix sum problems. Now let us test what we have covered so far on prefix sums. Again, try to identify the approach before reading the answer. So problem number 1 is, let's say given an array of integers, answer multiple queries of the form. Let's say what is the sum from index I to index j. The pattern is the basic prefix sum from slide 16 and 17. Build a prefix sum array with leading 0. Each query becomes prefix at j plus 1 minus prefix at I in O of 1. The total time is O of n to build the prefix sum, then O of 1 per query. Now again, these are just practice problems, so please think about them before answering the question. And again, they're pretty simple if you have been through the lecture so far. Now given an integer array and a target k, find the total number of continuous subarrays whose sums equal to k. And mind you that the k array can contain negative numbers. Again, the pattern is prefix sum plus complement lookup pattern from slide 18. A sliding window does not work here because of negative numbers. Shrinking the window might increase the sum, which breaks the sliding window logic. Instead, track the prefix sums in a hash map. For each new prefix sum, look up the prefix sum minus k in the map. Time is 0 often, space complexity is often as well. And problem 3, which is, let's say given an array, return a new array where each position contains the product of all elements except the one at that position, and division is not allowed. So again, the pattern for that was product, prefix and suffix from slide 19. You make two passes, left to right for left products, right to left for right products. Time is of 1 and space is of 1. The important thing across all three problems is the same underlying structure. Each one pre-computes the cumulative information so that each position can be answered in constant time. Prefix sums do this for addition. Prefix products do this for multiplication. The operation is different, but the pattern is the same. Recognizing this shared structure is what allows you to apply the pattern to new problems you have never seen before, which is exactly what interviewers are testing. In the interview, nobody will tell you which pattern to use. These patterns, so will come to you with more practice. So, that will train your classification skill, which is reading a problem statement and identifying the tool, the pattern to apply within the first minute. Now, let us take a step back and look at the big picture. We have three major patterns in this section: hashing, sorting, and prefix sums. Now, how do you choose between them? Now, let's cover that in the next slide. So, this is a decision that matters most in an interview. You're given an array problem. The brute force approach is O of n squared, and then you need to optimize. For you, then there are three tools available. So, hashing, sorting, and prefix sums. Each one is powerful, but each one solves a different type of problem. Choosing the wrong pattern will waste your time in the interview, which is not ideal, and it tells the interviewer that you're not matching the right pattern to the problem, which is also not good. So here's the framework. If the problem asks you to find a pair or a group that matches a condition, the tool is the hash map. The complement lookup gives you O of 1 per check. And then if the problem involves counting occurrences or frequencies, then the tool is a hash map as well. So that would be, and I know it's because single pass counting is O of n. And then if the problem checks for existence or uniqueness, the tool will be hash set, because the membership test will be O of 1. Now, if the problem asks for the closest pair or it needs the duplicates eliminated in a sorted order, so then the tool for that will be sorting. Sorted order enables two pointers or duplicate skipping logic. If the problem asks for, let's say, the kth largest or smallest element, sorting gives you rank directly. A heap is sometimes better, but sorting is a pretty straightforward approach. Now, if the problem involves the sum of a continuous subarray or range, then the tool for that is the prefix sum. Pre-compute the cumulative sums and then answer any range query in O of 1. If the problem asks for the product of all elements except the current one, then the tool for that is the prefix and suffix products. For that, you will do pre-compute from both directions. And for the next, if the problem now asks for, let's say, number of subarrays with a specific sum, so the tool for that would be prefix sum combined with the hash map. So that would mean complement lookup applied to prefix sums pattern. And now, if the output itself must be in sorted order, then sorting is the right choice. Hash maps do not maintain insertion order in a way that will give you sorted output. So that is pretty important to remember. Now let us compare the tools on complexity. Hash sets and hash maps both build in O of n and query in O of 1 on average. Space complexity for them is O of n, and they do not preserve the order. Now sorting builds in O of n log n and queries in O of log n with binary search. Space complexity for that varies from O of 1 to O of n depending on the algorithm. It does preserve the order. Now prefix sum arrays builds in O of n and queries in O of 1 per range. Space complexity for that is O of n, and again that does preserve the order. The key thing about interviewers, they notice is that whether you reach for the right tool and pattern based on the problem's characteristics, or whether you apply the same approach to every problem. Demonstrating that you can reason about which tool and pattern fits is what separates a good candidate clearing the interview and the one that you might not make too much progress. So it's very important to understand these patterns. But now there's some problems that need more than one pattern, one tool applied. So let's look at those problems in next slide, few slides. So up to this point, we have treated each pattern as a separate tool. Hash sets for existence checks, hash maps for counting, prefix sums for range queries. However, in real interviews, the most interesting problems, they need two patterns working together. Recognizing when to combine patterns is one of the clearest signs of depth that you can show in an interview. Now, let's take subarray sum equals k problem. That problem needs both prefix sum and a hash map. The prefix sum defines what each subarray sum is, and the hash map finds a complement that makes the sum equal to k. Neither tool solves it alone, so the combination is what makes it O of n. Now the threesome problem combines sorting with two pointers. Sorting is needed for two reasons. First, it lets us skip the duplicate values cleanly. Second, it allows two pointers to converge from both ends. Without sorting, two pointers would not work. And without the two pointers, sorting alone still requires O of n squared pair checking. Together they give us an efficient and clean solution. Now group anagrams, they combine a hash map with a key function. The hash map handles the grouping. The normalized key, either sorted characters or a group character count tuple, is what makes the grouping correct. Both of these parts are necessary. And then the top k frequent elements problem, it combines a hash map for counting frequencies with a heap or a bucket sort for extracting the top k. The hash map builds the frequency table in O of n. The heap extracts the k most frequent elements in O of n log k. Neither step would work without the other. Now here's a common mistake that shows up very often in interviews. So like many candidates, they default to sorting the array as the first step for every problem. But the sorting is O of n log n. That is fine when you actually need sorted order. For instance, when the output must be sorted, or when two pointers need sorted input. But if all you need is fast lookup or counting, a hash map will give you O of n. If you sort when hashing would have been enough, you accept a slower solution when a faster one exists. And it signals the interviewer that you're applying one tool to every problem instead of reasoning about which tool fits better. The better approach is to ask one question before writing any code in the interview, which is that, okay, do I need the elements in order or do I just need fast lookup? If the answer is order, then you sort. If the answer is lookup, then you hash. If the answer is range sums, then you do prefix sum. And this is something you should note down. Before coding any array problem, you should be asking three questions in this order. First, do I need a fast lookup? If yes, then you use hashing. Second, do I need elements in order? If yes, okay, then you use sorting. Third, do I need range or subarray sums? If yes, then you use prefix sums. These three questions, will take roughly 30 seconds in the interview, but will save you minutes and much more time working on the wrong approach. Now the ability to combine two patterns in a single solution is what separates, giving good interviews or, you're not doing well on the interviews. So it's very important to remember that, when you're doing the LeetCode interviews. And again, this is exactly what interviewers evaluate at a senior level and above. So but it also applies to, junior and intermediate candidates. So this is something to keep in mind for pretty much everyone. Now, before we close this section, let us go through the mistakes that happen, a lot in interviews and how you should avoid them. Now, each one of these mistakes is avoidable with just few more seconds of thought before writing code. So please do that. Now, the first mistake that happens is using nested loops when a hash map will give you O of n. When the problem involves repeated lookups, such as finding a pair that matches a condition, a hash map eliminates the entire inner loop completely. Now, if you write two nested loops for a problem that has an O of n hash map solution, the interviewer sees it as not knowing the pattern. So before writing a loop inside a loop, you should be asking yourself, am I doing repeated lookups? If yes, then a hash map is almost certainly the right tool. The second mistake is using a list for membership checks instead of a set. In Python, for example, doing a statement like x in my list scans the entire list in O of n. However, x in, let's say, my set, when you're using a set, we use hashing and that will be O of 1. The syntax looks almost the same, but the performance difference is massive. So regardless of what programming language you're doing your interviews in, whether it's C#, Java, and C++, you should know and remember completely, how to access sets in that language. And again, this single mistake will turn an O of n solution into O of n squared, and cause like again bad performance in the interviews. So you should please try to avoid it. Now the third mistake is sorting the array when the problem does not require sorted output. Sorting adds O of n log n overhead. If the problem can be solved with hashing in O of n, sorting is unnecessary and slower. You should only sort when the output itself needs to be in order, or when two pointers need sorted input to work correctly. The fourth mistake is forgetting to initialize the prefix counts hash map with 0:1 in the subarray sum equals k pattern. Without this initialization, subarrays that start from index 0 are missed entirely. This is a very common bug in that specific problems, and interviews look for it, so please keep this in mind. The fifth mistake is trying to use a sliding window on a subarray sum equals k problem. Sliding window only works correctly when all elements are positive, because shrinking the window always decreases the sum. When the array contains negative numbers, shrinking might increase the sum, which breaks the window's logic. For subarray sum problems with negative values, prefix sum plus hash map is the correct approach. And here's something important for interviews. At the start of any array problem, you should be running through a mental checklist in this order. First, do I need fast lookup? If yes, then you use a hash set or hash map. Second, do I need range sums? If yes, then you use a prefix sum. Third, does the output need to be sorted? If yes, you should be sorting first. Saying this checklist out loud in the interview, it will show you that you have structured thinking. Interviewers value this structure because it demonstrates that you approach problems methodologically with method rather than just guessing. Now the mistakes in this list are pretty common reasons when the interviews don't go well. So each one of them is avoidable. So if you take 10 seconds identify the pattern, like spending time on actually identifying the pattern before jumping right into writing the code, that's like super advisable. Now let us put everything together into a reference cheat sheet in the next slide. So that is designed for a quick review before you do interviews. So yeah, the next slide is super important. Let's cover it. So here's a reference cheat sheet that you should cover just before interviews, so that you have the high level mental model to recognize the patterns. And this slide is designed to be saved and reviewed before the interviews, so it covers every pattern, every template, and every complexity in one place. The first template is a hash set for existing checks. So for that, you create a set, loop through the array. For each element, you check if it is already in the set. If it is, you have found a duplicate. If not, you add it. This runs in O of n time and O of n space. The second template is a hash map for frequency counting. For this, you create a dictionary, loop through the array. For each element, you increase its count using the get method with a default of 0. After one pass, you have a complete frequency table. For this, the time complexity is O of n and space complexity is also O of n. The third template is a complement lookup for two sum problem. Creating a dictionary for this, and then you loop through the array with indices. For each element, you compute the target minus the element and check if that complement is in the dictionary. If yes, you return both indices. If no, you store the current element with this index. Again, for this, the time complexity is O of n and space complexity is O of n as well. The fourth template is the basic prefix sum for range queries. For this, you create an array of length n plus 1 filled with zeros, and then you loop through the original array. For each index, you set prefix at I plus 1 to prefix at I plus the current element. To get this sum from index I to j, you compute the prefix at j plus 1 minus prefix at I. Again, it takes O of n to build and O of 1 per query. Now the fifth element here is the prefix sum plus hash map for counting subarrays with a specific sum. For this, you maintain a running prefix sum and a hash map initialized with 0:1. And then for each element, you add it to the prefix sum. Check for how many times prefix sum minus k has appeared in the map. And then you add that to the count. And then record the current prefix sum. So for this, the time complexity is O of n and space complexity is O of n as well. Now for the complexities, hash set existence is O of n time and O of n space. Hash map frequency is O of n time and O of n space. Complement lookup is 0 of n time and 0 of n space. Prefix sum build is 0 of n time and 0 of n space. Prefix sum query is again 0 for 1 time and 0 for 1 space. Product prefix and suffix is O of n time and O of 1 extra space. Every pattern in this section runs in O of n time and O of n space. So if your array solution is slower than O of n, check whether one of these patterns applies before accepting the slower approach. Now let's summarize the entire section and connect, how it comes to what section it comes next. Now let us summarize everything we have covered in this section by connecting each pattern to its recognition signal and key inside. The hash set patterns applies when the problem asks a question like, okay, does X exist, or have we seen this before? The key inside is that O of 1 lookup replaces O of n scanning. The hashmap frequency pattern applies when the problem asks you, okay, questions like how many times, or most frequent, or sometimes even less frequent. So the key inside is a single pass counting is O of n. Then the complement lookup pattern, it applies when the problem asks you questions like, okay, find two elements that satisfy some condition. The key inside is that you compute what the partner must be and then you check the map. The grouping by key pattern applies when the problem asks questions like, okay, group elements that share some property. And the key inside here is that you transform the element into a normalized form and then you use that as a hash map key. The prefix sum pattern applies when the problem involves the sum of a continuous subarray or range. The key inside is that you pre-compute cumulative sums, so every range query becomes a single subtraction of 1. The prefix sum plus hash map pattern applies when the problem asks questions like, okay, count subarrays with sum equal to k. The key inside is that the complement, lookup logic applied to prefix sums instead of the individual elements. The product prefix and suffix pattern applies when the problem asks for the product of all elements except the current one without division. The key inside is two directional passes, left and then right, accumulating products from each side. Now these patterns do not exist in isolation. They connect to what we will be covering later in the course. Hashmap frequency counting reappears in section 9, where top k frequent elements use a hash map followed by a heap. The complement lookup reappears in section 5, where binary search on the answer uses similar, like define what you need, then search for it approach. Prefix sums reappear in section 11, where some dynamic programming problems use prefix sums to optimize range calculations. In the sliding window misconception we discussed, trying to use a sliding window on problems with negative numbers connects directly to section 3, where we'll cover when sliding window is the correct tool. Now in section 3 we'll cover two pointers and a sliding window approaches. These patterns handle the cases where the answer depends on a continuous range of or two positions moving through an array. The sliding window is a complement to prefix sums. Prefix sums answer questions like, okay, what is the sum of this range? Sliding window approach, the pattern answers questions like, what is the best range that satisfies this constraint? Together with the patterns from this section, they cover the majority of array and string problems that you will encounter in LeetCode interviews. Now, if you can identify which of the 7 patterns from this section applies within, let's say, 60 seconds or a few minutes of reading the interview problem, that will really help you during the interview. Now the next section adds 2 more patterns to your toolkit, and together they will cover pretty much a lot of array interview problems. So let's get started. So in section 2 we solved 2 fundamental problems. We eliminated redundant lookups using hash maps, and we eliminated redundant range calculations using prefix sums. This section tackles a different kind of inefficiency. So many problems ask about, okay, pair of elements or continuous ranges within an array. The brute force approach checks every possible pair or every possible subarray. That means nested loops, and that means O of n squared time complexity. For an array with, let's say, 1,000,000 elements, that is over 1 trillion operations, which is far too slow to say in an interview. Now, 2 pointers in sliding window are techniques that move through the array in a structured way. Instead of checking all possible pairs or subarrays, you maintain 1 or 2 pointers that advance forward through the data. Each pointer moves at most n times, and no pointer ever goes backward. That gives you O of n solutions to problems that would have been otherwise require O of n squared. Now this section covers 6 topics. We start with the opposite direction 2 pointers, where one pointer starts at the beginning and another starts at the end, and they move forward toward each other. Then same direction 2 pointers, where both pointers start at the beginning and one moves faster than the other. After that we move into sliding windows. First fixed size windows where the window length is given, then variable size windows where you need to find the optimal window length. We'll look at character frequency windows as a specific and important application. And finally, a decision framework for choosing between two pointers and a sliding window. In terms of interview frequency, now this section covers some of the most, commonly asked problems across all of tech companies. So for example, at large tech companies, like problems like threesome problem or container with most water and minimum windows per substring are pretty commonly asked questions. At mid-sized companies as well, like problems like palindrome checks, duplicate removal, and substring problems show up regularly as well. And in startups, string processing and data stream problems often reduce to sliding windows as solution. And in all these companies, as part of the online assessments, variable size window problems are common time questions that where the difference between O of n and O of n squared would determine whether the solution passes or times out. Now the core idea for this entire section is this. When the answer depends on a continuous range or two positions moving through sorted or sequential data, pointer movement replaces nested loops. The skill is knowing which pointer is to move and when. Now let us start with the most common two-pointer variant, which is opposite direction pointers. The recognition signal is pretty straightforward. The input is sorted, or the problem involves symmetry, or you are working with both ends of a sequence. The problem generally asks about pairs, and you notice that checking all pairs would be O of n squared. But because the data has structured, typically sorted order, you can eliminate many pairs at once by reasoning about the values at each end. Now here's how it works. Placing one pointer at the start of the array at index 0 and place at the other end, which is at index n minus 1. Now you compare the values at both pointers. Based on that comparison, move one pointer inward. Each step does not just skip one pair, it eliminates an entire row or column of the pair space. That is the power of this technique. So now when should you reach for opposite direction pointers? There are several clear signals. First, when the input is sorted and you need a pair that hits the target sum like 2 sum 2. And then the second signal is when you're checking symmetry from both ends like valid palindrome. Third is when you're maximizing area or distance between two positions like container with most water. Fourth, when you need to square elements in a sorted way while keeping the results sorted. And fifth, when you're merging or comparing from both ends like a merged sorted array. So now why is this O of n? Each pointer moves at most n times total. The left pointer only moves right, the right pointer only moves left. They meet somewhere in the middle after at most n combined steps. And no pointer ever moves backward, so no work is being repeated. The total number of operations is linear. For interviews, opposite direction two pointers is the first variant you should consider whenever the array is sorted and the problem mentioned pairs. This pattern should become an automatic instinct for you during interviews. Now let us look at the template and trace through how it works on a concrete example. The template has three parts: initialize left at 0 and right at the last index, run a while loop as long as left is less than right. Inside the loop, check if the condition is met at the current pair. If it is, then you return the result. If not, then you decide which pointer to move. If you need a larger value, you move left forward. If you need a smaller value, you move right backward. Now let us trace through this on the 2 sums 2 problem. The input is a sorted array. Let's say it is 2, 7, 11, 15. The target, let's say, is 9. Now the left starts at index 0, right starts at index 3. The sum of 2 plus 15 is 17, so that is greater than 9, so the sum is too large. We need a smaller value on the right side, so we move right from index 3 to index 2. Now the sum is 2 plus 11, which is 13, still too large. Move right again to index 1, so now the sum is 2 plus 7, which is 9. That equals the target. We return the pair at indices 0 and 1. The crucial question is, why is moving the right pointer correct when the sum is too large? Now think about it this way. If the sum of the left value and the right value exceeds the target, then the right value paired with anything larger than the current left value will produce an even bigger sum. All of those pairs are guaranteed to overshoot, so every pair involving the current right value with a larger left value is eliminated in one step. The only productive move is to try a smaller right value. Now the same logic works in reverse. If the sum is too small, the left value paired with anything smaller than the current right value will produce an even smaller sum. So we move left forward to try a larger value. The pointer movement here, is always derived from the sorted order of the data. So sum too large means move the right pointer left to get a smaller value. Sum too small means, move the left pointer to right to get a larger value. This logic applies to every variant of the opposite direction pattern. And this is something you should note down, that because being able to explain why the pointer movement is correct, not just that it works, is what distinguishes, doing well in the interview and maybe not doing that well. So you should have this in mind when you're doing LeetCode interviews. So let us apply opposite direction pointers to a different kind of problem, which is checking symmetry. The problem is valid palindrome, which is LeetCode number 125 problem. Given a string, determine if it is palindrome. The catch is that you should only consider alphanumeric characters and ignore case. So punctuation, spaces, and special characters are skipped. Now, if you take the input, let's say a man, a plan, a canal, Panama, if you strip out all the non-alphanumeric characters and convert to lowercase, you get a man, a plan, a canal, a Panama without no spacing and all lowercase. That reads the same forward and backward, so it is a valid palindrome. Now, this approach uses opposite direction two pointers, so you start at the beginning of the string and then right at the end. So then you skip any non-alphanumeric characters by advancing left forward or right backward until both point to valid characters. Then you compare those characters in a case insensitive way. If they do not match, the string is not a palindrome, and then you return false immediately. If they do match, then you move both pointers inwards and repeat. If the pointers meet or cross without finding a mismatch, the string is a palindrome. Now if you walk through the code, the outer while loop runs as long as left is less than the right. Inside, two inner while loops skip non-alphanumeric characters from both ends. Then we compare the lowercase versions of the characters at left and right. If they differ, then we return false. If they match, we advance both pointers. When the loop finishes without finding a mismatch, then we return true. The trace on our example is, which is after handling non-alphanumeric characters, left starts at the first A and the right starts at the last A. They match. Then they move both inwards, so left hits M and right hits M as well. They again match. This continues all the way until the pointers cross at the center, so that at that point every pair has matched, so we return true. Now the time complexity for this is O of n because each pointer traverses the string at most once. The space complexity is O of 1 because we do not create any new string. A common mistake is to create a clean string by filtering out non-alphanumeric characters and reversing it, and then checking if the clean string equals the reverse. That works correctly, but it does use O of n extra space. The two-pointer approach achieves the same result with O of 1 space. So in interviews, interviewers generally frequently ask a follow-up question, which is like, can you do this without extra space? Having the two-pointer solution ready from the get-go, answers that immediately. Now, valid palindrome is one of the most common, interview questions, LeetCode interview questions, because, it tests the basic two-pointer mechanics and clean string handling. Solving it quickly and correctly early in the interview builds interview confidence, for the harder problems that might be coming in the upcoming loop interviews during the, let's say, on-site loop. So far, two pointers have moved toward each other from opposite ends. Now let's look at how at different variants where both pointers start at the beginning and move in the same direction. So the recognition signal for same direction two pointer is different from opposite direction. Here's the problem involving partitioning an array, removing elements in place, or separating elements by some criteria. One pointer moves fast, scanning ahead through the data. The other moves slow, making the boundary of the process section. Now, here's the mental model. Think of the slower pointer as a gatekeeper. It marks where the good section of the array ends. The fast pointer scouts ahead, looking for elements that qualify. When the fast pointer finds a qualifying element, it copies or swaps that element to the slower pointer's position. Then the slower pointer advances by one, extending the good section. The template for this pattern is pretty concise. So if you initialize, like slow at 0, you loop fast from 0 through end of the array. Inside the loop, you check if the element at fast meets the condition. If it does, copy it to the slow position and increment slow. At the end, slow tells you how many qualifying elements there are, and the first slow elements of the array are the result. So this pattern appears in several classic problems. In remove duplicates from sorted array problem, the slow pointer marks the end of unique elements, and the fast pointer finds the next unique value. In remove element in problem, the slow marks the end of kept elements, and the fast finds elements that are not the target value. In the move zeros problem, slow marks the end of non-zero elements, and fast finds the next non-zero. In sort colors problem, also known as the Dutch national flag problem, the pointer marks the boundaries of color regions. For interviews, same direction 2 pointers almost always signal in-place modification. If the problem says do not allocate extra array or modify in place and return the new length, this pattern is what the interviewer expects. These problems are common warm-up questions, so they test whether you can manipulate the array indices cleanly without creating the off by one errors or bugs in the pointer advancement. And about the opposite direction pointers with a more complex problem. The problem is a threesome problem, which is LeetCode number 15. Given an integer array, return all the unique triplets where the three values sum to 0. The indices must be distinct and the output should not contain duplicate triplets. Now the brute force approach uses 3 nested loops to check every combination of 3 elements. That is O of n cube. For an array with even a few thousand elements, that is way too slow. The optimized approach uses a technique called fix 1, 2 pointers and the rest. Now here's the idea. First you sort the array, then you iterate through the array with an outer loop, fixing one element at a time. For each fixed element at index I, the problem reduces to finding 2 elements in the remaining portion of the array that sum to the negative of the fixed element. That is exactly the 2 sum 2 problem on a sorted array, so which we have already know how to solve with opposite direction 2 pointers. Now if we walk through the code, we first sort the array and then we loop I from 0 to n minus 3. For each I, we set left to I plus 1 and right to the last index. We run the 2 pointer search. If the total of 3 elements is less than 0, the sum is too small, so we move left forward. If the total is greater than 0, the sum is too large, so we move right backward. If the total equals 0, we found a valid triplet. Add it to the result, then skip duplicate values for both left and right before moving both pointers inwards. Now, there is one critical detail in the outer loop, which is if the current element equals the previous element, you skip it. This prevents duplicate triplets in the output. The time complexity for this is O of n squared. Sorting takes O of n log n. The outer loop runs n times for each iteration, and the 2 pointer scan runs in O of n. So the total becomes O of n squared, which is massive improvement over O of n cubed. The space complexity is O of 1 extra, not counting the output. Now the threesome problem is a very common LeetCode problem because it combines sorting, 2 pointers, and careful duplicate handling. That combination is exactly what interviewers use to distinguish candidates, which are really thinking through the patterns and applying in a structured way. So duplicate handling in the threesome LeetCode problem is where most candidates make mistakes. Let us trace through the full algorithm to see exactly how it works. Now if you take the input array, let's say it is -1, 0, 1, 2, -1, -4. After sorting this becomes -4, -1, -1, 0, 1, 2. Starting with the I equals 0, the fixed element is -4. The target for the 2 pointer search is 4. Left starts at index 1, right at index 5. The -1 plus 2 equals 1, which is less than 4. Move left and forward. So again, -1 plus 2 is equal to 1, which is still less than 4. Move left. 0 plus 2 equals 2, still less than 4. So move left. 1 plus 2 equals 3, still less than 4. Move left again. And now left equals right, so we stop. No triplets with -4. Next, I is equal to 1, so the fixed element is -1. The target is left is at index 2, right is at index 5. -1 plus 2 equals 1, which equals the target. We have found the triplet, -1, -1, and 2. After recording it, we skip the duplicate values on both left and right, and then we move both pointers. Now left is at index 3, right is at index 4. 0 plus 1 equals 1, which equals the target. We found another triplet, which is -1, 0, 1. Skip the duplicates and then we move. The pointers cross and we stop. Now I is equals to 2, so the element is -1, which is the same as the element I equals 1. We skip this iteration entirely, so if we did not skip it, we would find the same triplets again. Finally, I is equals 3, so the fixed element is 0, the target is 0, left at index 0, right is at index 5. 1 plus 2 equals 3, which is greater than 0. You move right, pointers cross, and then we stop. The result is two triplets, -1, -1, 2, and -1, 0, and 1. Now there are three places where duplicates must be handled. First, in the outer loop, at the index I, if the current element equals the previous element, we skip it because using the same fixed element will produce the same triplets. Second, the left pointer after a match, skip forward past any duplicate values. Third, the right pointer after a match, skip backward past any duplicate values. A very common mistake is checking duplicates in the outer loop by comparing the current element with the next element using nums I equals nums I plus 1. Now this is wrong because it skips the first occurrence of value, which means valid triplets that use that value are skipped entirely. The correct check compares with the previous element, so num I equals num I minus 1. Always look backward, not forward. Now in the interviews, the duplicate handling is the part interviewers watch most closely. They want to see that you handle all the three deduplication points correctly and that you can explain why each one is necessary. We have seen two-pointer mechanics on sorted arrays and palindrome checks. Let us apply the same pattern to a problem where the input is not sorted at all, but opposite direction pointers will still work. The problem is container with most water problem, which is LeetCode number 11. You are given an array of heights where each value represents a vertical line at that position. The goal is to pick two lines that, together with the x-axis, form a container holding the most water. In other words, you are looking for the pair of lines that maximizes the rectangular area between them. So the brute force approach is pretty straightforward. You try every pair of lines, compute the area for each pair, and keep the maximum. That is O of n squared because they are roughly n squared over two pairs. For large arrays, that is pretty slow and not ideal for interview answer. So now, how do we do better? So for that, the key insight comes from thinking about what determines the area. The area between two lines is the width, which is the distance between the two positions, multiplied by the height, which is the shorter of the two lines. The shorter line is the bottleneck. No matter how tall the other line is, water spills over the shorter one. With that understanding, the strategy becomes clear. Start with the wildest, the possible container by placing the left pointer at position 0 and the right pointer at position n-1. Compute the area. And then you should ask, okay, which pointer should we move for inward? Here is why moving the shorter line is the correct choice. If we move the taller line inward, the width decreases by 1. But the height is still capped by the shorter line, which has not changed. So the area can only decrease or stay the same. That move can never improve the answer. Moving the shorter line inward is the only move that has a chance of finding a taller line on that side, which could increase the height and potentially give a larger area despite the reduced width. Now this is as we call it, the greedy argument. At every step, one of these two moves is probably not useful so we eliminate it. That is exactly the same reasoning we use for 2 sum 2 on a sorted array problem, just applied to a different property. The code is clean. Initialize is left at 0 and right in n-1. Set the best area to 0. In the while loop, compute the width as right minus left and the height as the minimum of the heights at both pointers and update best if the current area is larger. Then compare the two heights. If the left height is smaller, move left forward, otherwise move right backward. When the pointers meet, return the best area. The time complexity for this is O of n. Each pointer moves at most n times and they only move inward. No work is repeated. The question that often comes up is that, okay, what if both heights are equal? In that case, it does not matter which pointer you move. Moving either one is correct. Some implementations move both pointers inward simultaneously when the heights are equal, but moving just one works fine. The proof still holds because moving either pointer still eliminates the probably non-optimal pair. This problem is pretty important for interviews because the correctness argument is the real test. Writing the code itself won't take you more than 30 seconds, but explaining why moving the short pointer is correct and why moving the taller pointer can never improve the answer is what the interviewers are evaluating. Have the evaluation ready before you walk in the interview because that is super important. We have now seen several two-pointer problems. Let us step back and build a recognition framework. When you see a new problem, how do you know whether two pointers apply and which variants to use? So there are the clear signals. So if the array is sorted and you need to find a pair with a target sum, you use opposite direction pointers. If the problem involves checking symmetry on both ends, like palindrome verification, that is opposite direction. If you're maximizing or minimizing the distance between two positions, think opposite direction. If the problem asks for all triplets summing to a target, sort the array first and then use opposite direction pointers inside an outer loop. For same direction pointers, the signals are different. If the problem asks you to remove duplicates or elements in place, use a slow and fast pointer in the same direction. If you need to partition an array by some conditions, that will be same direction. If you need to detect a cycle in a linked list, that is also same direction with the fast pointer moving twice as fast. And merging two sorted sequences uses one pointer per sequence, both moving forward. Now equally important is knowing when two pointers do not apply. Now if the array is unsorted and you need fast lookups, hash maps from section 2 are the right tool. If you need the sum of a continuous range, pointer movement does not track range sums efficiently, so prefix sums are better. If you need all combinations or subsets, pointers only track two positions, so you need backtracking, which we'll be covering in section 10. And if the problem has optimal substructure with overlapping subproblems, that points to dynamic programming, which we'll be covering in section 11. Now, the fastest way to build confidence in an interview is to state the pattern within the first 30 seconds. Saying something like, okay, this looks like an opposite direction two-pointer problem because the array is sorted and we need a pair. When you state this statement in the interview, and this will tell the interviewer that, okay, this person is thinking in a patterned way, in a more structured way, which is a much better approach to solving problems. Now let us test what we have covered so far. For each problem, we try to identify the pattern before hearing the answer. Now, let's say there is a problem 1, which is given a sorted array of integers, return an array for the squares of each number, also sorted. For example, -4, -1, 0, 3, 10 should return 0, 1, 9, 6, 16, 100. So what pattern applies here? So let's take a step back and let's think about it before saying the answer. So when you're done thinking about it, so this is the answer. This is the opposite direction two pointers. The key insight is that the largest square comes from the ends of the array because the most negative and the most positive numbers produce the biggest squares. So you place the pointers at both ends, compare the absolute values, place the larger square at the end of the result array and move that pointer inwards. Time is of n complexity and space is of n complexity for the result array. Now let's look at the second practice problem. And again, after seeing the problem, let's wait for a bit, think about it before seeing the answer. So the second practice problem is, given a sorted array, remove the duplicates in place so that each element appears at most once. Then you return the new length. And what pattern applies here? Now, this is the same direction two pointers, the pattern from slide 28. The slow pointer tracks the end of the unique element section. The fast pointer scans forward looking for the next value that differs from the current slow position. When fast finds a new unique value, copy it to the slowest position and advance slow. Time is of n complexity and space of 1 complexity. The third practice problem is, given an array of integers and a target, find all unique quadruples that sum to the target. Now what pattern applies here? This is a 4-sum problem, which is a natural extension of 3-sum LeetCode problem. So for this, you sort the array first, fix two elements with the two outer loops, Then you use the opposite direction 2 pointers for the remaining pair. The time complexity is O of n cube and the pattern generalizes pretty cleanly. For the k-sum problem, the approach is O dot is the n to the power k minus 1 using sorting and 2 pointers for the innermost pair. Now, being able to generalize from 2-sum problem to 3-sum problem to 4-sum problem shows an interviewer that you understand the underlying pattern, not just the individual problem solutions. That kind of insight is exactly what earns a strong higher signal in interviews. So we have covered 2-pointer patterns. Now let us move to the second major technique in this section, which is sliding windows. The recognition signal for a fixed size sliding window is this. The problem asks for a continuous subarray or substring of a fixed length k. You need to compute something, whether that is sum, maximum, average, or count for every window of exactly k elements. Before we look at the solution, let us understand why the brute force approach fails here. If you compute the answer for each window independently, that takes O of k per window. There are roughly n minus k plus 1 windows, which is O of n. So the total is O of n times k. For large k, this is too slow. If k is half of n, you're looking at O of n square work. The sliding window inside, eliminates its redundancy. When the window slides one position to the right, only two things change. One element enters the window on the right side, one element leaves the window on the left side. Every other element in the window is exactly the same. Instead of recomputing the answer from scratch, update the running answer by adding the new element and removing the old one. Each slide costs O of 1, so the total across all slides is 0 of n. Now let us trace through this example here. Let's say we are given an array 1, 3, 2, 6, 4, 1, 8, 5 with k equals to 3. The first window contains 1, 3, 2 and sum is k. We slide right, remove the 1 and add the 6. The sum goes from 6 minus 1 plus 6, which equals 11. And then we slide again, remove the 3, add the 4. Sum goes from 11 minus 3 plus 4, which is equals 12. Each transition is one addition and one subtraction. That is O of 1 per slide, no matter how large k is. Now, fixed size sliding window is the simpler of the two window variants. Mastering it first makes variable size windows easier to learn because the core idea of maintaining state as the window moves is identical. The difference is just whether the window size is fixed or flexible. Now let us look at the template code and understand when it needs to be extended. The basic template works in two phases. First, compute the answer for the initial window of size k. This is the only time we do O of k work. Then slide from position k to the end of the array. At each step, add the new element entering the window at index I, subtract the element leaving the window at index I minus k, and update the best answer. That is the entire algorithm. Now if we break it down into step by step here, initialization computes the sum of the first k elements costing O of k. Each slide adds one element and removes one element costing O of 1. Updating the answer by comparing with the best so far, cost O of 1. The total is k plus n minus k steps, which is simplifies to O of n. Now, not every fixed window problem tracks a simple sum. Some problems, they need to track the frequency of characters, the count of distinct elements, or other properties within that window. For these, replace the single sum variable with a hash map or counter. The slide logic stays the same. When an element enters a window, add it to the tracker. When an element leaves, we remove it from the tracker. Now the extended template for a frequency map works like this. Initialize the frequency dictionary for the first k characters. Set the best answer based on the initial window state, for example the number of distinct keys. Then slide through the remaining characters. For each new character entering the window, increment its count. For the character leaving the window, decrements its count. And if that count drops to 0, delete the key from the map. This deletion step is important because it ensures that the number of keys in the map accurately reflects the number of distinct characters currently in the window. This template handles 90% of fixed window problems. The only thing that changes between problems is what you track inside the window. Whether that is a running sum, a running maximum, a frequency map, or a count of distinct elements, the slide mechanics remain identical. a problem that does not look like sliding window at first, but uses the exact same thinking. The problem is best time to buy and sell stock problem, which is LeetCode number 121. You are given an array of stock prices where each element is the price on a given day. Find the maximum profit from buying on one day and selling on a later day. You must buy before you sell. Now the brute force approach tries, all buy-sell pairs. For each possible buy day, check every later day as a possible sell day. That is O and squared. The optimized approach works in a single pass. As you scan through the prices from left to right, track two things: the minimum price seen so far and the best price profit so far. At each position, compute the profit if you sold at today's price, which is today's price minus the minimum price seen so far. If that profit is better than the current best, update the best, and update the minimum price if today's price is lower. Now let us trace to this example here. So let's say the prices are 715364. So we start with the minimum price is 7 and best profit is 0. Day 2 the price is 1. That is the new minimum, so profit is 0. Day 3 price is 5. Profit is 5 minus 1, which is 4. New best is 4. Day 4 price is 3, so profit is 3 minus 1, which is 2. Best stays at 4. Day 5 price is 6. Profit is 6 minus 1, which is 5. New best is 5. Now day 6 price is 4, so profit is 4 minus 1, which is 3. So best stays at 5, and the maximum profit is 5 from buying at 1 and selling at 6. So time complexity for this is O of n, space complexity is O of 1. Now this problem actually does not use a fixed size window, but it uses the same mental model. As you move through the array, you maintain a running state, in this case a minimum price. That lets you compute the answer at each position in O of 1 without looking backward. You never need to revisit earlier elements. So this, let's say, maintain state as you can principle is the foundation of all sliding window problems. Now, the best time to buy and sell stock problem is one of the most frequently asked for, like LeetCode problems. It tests whether you can identify the tracking. A running minimum eliminates the need for nested loops. In production systems, in this same pattern of tracking running minimums or maximum appears in monitoring dashboards and alerting pipelines. Indicators often follow with harder variants involving multiple transactions or cooldown periods, and those variants build directly on this foundation. Now, fixed windows have a predetermined size, but what if the problem asks for the longest or shortest continuous subarray that satisfies some constraint? The window size is not given, so you need to find it, and that is where variable size sliding windows come in. So the recognition signal is clear. The problem mentions longest or shortest continuous subarray or substring that satisfies the condition. The window size is part of the answer, not part of the input. So the core idea is this. You maintain a window defined by left and right pointer, expand the window by moving right forward one position at a time. When the window violates the constraint, shrink it by moving left forward until the constraint is satisfied again. At each valid state, you update the answer. A question that comes up frequently is, why is this O of n and not O of n squared? After all, there is a while loop inside a for loop, and normally that suggests quadruplet time. But let's look at what actually happens. The right pointer moves forward n times across the entire execution, once per iteration of the for loop. The left pointer also moves forward but never moves backward. Over the entire execution, left moves at most n times total. So the total number of pointer movements is at most 2n. So that is O of n. So these are the two subpatterns within the variable size windows, and getting them confused is a pretty common source of bugs. For longest valid window problems, you expand eagerly and shrink reluctantly. You grow the window as much as possible and only shrink when the window becomes invalid. You update the answer after every expansion that keeps the window valid. For shortest valid window problems, you expand until the window becomes valid, then shrink eagerly to find the minimum size. You update the answer during each shrink step that keeps the window valid. This distinction is critical. Getting it backward means the algorithm computes the wrong answer, and we'll look at the templates for both subpatterns on the next slide. Let's now look at the two template sides side by side so the difference is completely clear. For the longest window template, initialize the window state, which is usually a hash map. You set left to 0 and the best to 0. Loop right from 0 to the end of the array. At each step, add the element at the right to the window state. Then check. Is the window invalid? If it is, then you enter a while loop that shrinks from the left. Remove the element at left from the window state, and if it counts drops to 0, delete the key. And then you increment left. After the while loop exists, the window is valid again. Now update the answer as the maximum of the current best and the window size, which is right minus left plus 1. For the shortest window template, the structure looks similar, but the logic is reversed. You initialize the window state, set left to 0 and best to infinity because you're looking for the minimum. Loop right from 0 to the end, add the element at the right to the window state, and then you check, is the window valid? So for example, if it is, then you enter a while loop. Inside this loop, you first update the answer as the minimum of the current best and the window size. Then you remove the element at the left and increment the left. Keep looping as long as the window stays valid, and at the end, you return the best if it was updated, or 0 if no valid window was found. The critical difference comes down to one thing. In the longest template, you shrink when the window is invalid and update the answer outside the inner loop, after the window becomes valid again. In the shortest template, you shrink when the window is valid and update the answer inside the inner loop before each shrink step. And this you should something note down. Longest means shrink when invalid, update outside. Shortest means shrink when valid, update inside. This is the single most important distinction in sliding window problems. Getting the expand and contract logic backward is the #1 source of bugs in sliding window solutions. If you memorize these two templates and know which one to apply, you eliminate the most common source of errors. Now let us apply the longest window template to one of the most frequently asked problems in LeetCode interviews. The problem is longest substring without repeating characters, which is LeetCode problem number 3. Given a string, find the length of the longest substring where no character appears more than once. This is the longest valid window problem. The constraint is that no character in the window repeats, so we expand right to grow the window. When the duplicate character enters, we shrink from the left until the duplicate is removed. The code uses a character index map instead of a frequency map. Instead of tracking how many times each character appears, we store the most recent index where each character was seen. When a character at position right already exists in the map and its store index is greater than or equal to the left, that means the character is inside the current window. In that case, we jump left directly to one position past the previous occurrence. So now why use character index map instead of a frequency map? Both approaches achieve O of n time, but the index jump approach avoids the inner while loop entirely. Instead of shrinking left one position at a time until the duplicate is removed, we jump left directly to the right position. This makes the code cleaner and avoids the common mistake of getting the inner while loop's exit condition wrong. So now the time complexity for this is O of n. Each character is processed once as right moves through the string. The space complexity is O of the minimum of n and the alphabet size, because the map stores at most one entry per distinct character. This problem is, very commonly asked LeetCode problem. Interviews expect you to solve it like under 10 minutes, so you need to be prepared for this. Knowing the index jump optimization beyond the basic template will show the depth understanding in interviews. So please do that. So now let us trace through the algorithm step by step on a concrete example to make sure the mechanics are completely clear. Let's say the input is a string as A, B, C, A, B, C, B, B. We start with an empty character index and index map left at 0 and best at 0. Right equals 0, so the character is A. It is not in the map, so no duplicate. We store A at index 0. The window is A. Best becomes 1. Now right equals 1, character is B. It's not in the map, so we store B at index 1. Window is AB. Best becomes 2. Right equals 2, character is C. Not in the map, so we store C at index 2. Window is ABC. Best becomes 3. Right equals 3, character is A. A is in the map at index 0, so index 0 is greater than or equal to the left, which is also 0. So this A is inside the current window. Jump left to the 0 plus 1, which is 1. So we update the A in the map to index 3. window is now BCA and best stays at 3. Now right equals 4, which is character is B. B is in the map at index 1. Index 1 is greater than or equal to the left, which is 1. Now we jump left to 1 plus 1, which is 2. So we update B to index 4. Window is CAB. Best stays at 3. Now the right equals 5. Character is C. C is in the map at the index 2. Index 2 is greater than or equal to left, which is 2. We jump left to 3. Update C to index 5. Window is ABC. Best stays at 3. Now right equals 6. Character is B. B is in the map at index 4. Index 4 is greater than or equal to left, which is 3. We jump left to 5. Update B to index 6. Window is CB. Best stays at 3. Now right equals 7. Character is B. B is in the map at index 6. Index 6 is greater than or equal to the left, which is 5. We jump left to 7. Update B to index 7. Window is B. Best stays at 3. Now the result is 3. The longest substring without repeating characters is A, B, C. Now, why does the greater than or equal to the left check matter? Without this check, the map might contain stale entries from characters that appeared before the current window. A character might have been seen at some earlier index, but the window has moved past that index. That character is no longer in the window, so if we reacted to that stale entry, we would shrink the window unnecessarily and miss valid substrings. The check ensures that we only respond to duplicates that are actually inside the current window. A common alternative approach uses a set and removes character one by one from the left until the duplicate is gone. This works, but the inner loop makes the code harder to get right under interview pressure. The index jump approach is much more cleaner. Now, being able to trace through this problem step by step without hesitation is something interviewers is very looking for in the interview. Now, this is one of the hardest sliding window problems and is a frequent hard level interview question. So let us work through it carefully. The problem is minimum window substring, which is LeetCode number 76 problem. Given two strings S and T, we return the shortest substring of S that contains all characters of T, including duplicates. If no such window exists, we return an empty string. Let's take this as an example. Let's say S is A, D, O, B, C, O, D, E, B, and C. T is A, B, C. The expected output is B and C, which contains A, B, and C. This is the shortest valid window problem. The constraint is that the window must contain every character of T with at least the required frequency. We expand right until the window becomes valid, meaning it contains all the required characters. Then we shrink left while the windows stay valid, updating the answer at each valid state, looking for the smallest window. The code uses two key variables. The first is frequency map called need, which tracks how many more of each character we still need. We initialize it with, the character counts from T. The second is an integer called missing, which tracks the total number of characters still needed. Initialize it to the length of T. As right moves forward, we check if the character at right is the one we need. If its count in the need map is greater than 0, it is a character we still actually need, so decrement missing. Then decrement the need count for that character regardless. When missing reaches 0, the window is valid. Enter the shrink loop. Update the answer if the current window is smaller than the best so far. Then try to shrink from the left. If the character at left is in the need map, increment its need count. If the count goes above 0, that means we just removed a character we actually needed, so increment the missing. Then we move left forward, continue shrinking as long as missing stays at 0. Now the time complexity for this is O of n plus m, where n is the length of S and m is the length of T. The time complexity is O of m for the frequency map. Solving this problem correctly in an interview demonstrates mastery of the variable size window pattern. It combines the shortest template, frequency tracking, and the missing counter all in one problem. Let's trace through the full execution to understand exactly how the missing counter and the shrink loop interact. The input is S equals, let's say, ADO, BEC, OD, B, and C. T equals ABC. The need map starts at A:1, B:1, C:1. Missing starts at 3. Right equals 0. Character is A. A is in the need and its count is 1, which is greater than 0. So we actually need this character. Decrement missing to 2, decrement need for a to 0. So right equals 1 through 2, characters in D and 0, not in the need map, nothing changes. So right equals 3, character is B, need for B is 1, greater than 0, decrement missing to 1, decrement need for B to 0. Right equals to 4, character E, not in need. Right equals 5, character is C, need for C is 1, greater than 0, decrement missing to 0. Now the window is valid. It spans from index 0 to 5, which is A, D, O, B, E, C, with length 6, enter the shrink loop. Try to shrink. Left is at index 0, character A. Increment need for A to 1. Since 1 is greater than 0, we lost a needed character. Missing becomes 1. The window is no longer valid. Exit the shrink loop. Best length is 6. Best start is 0. Move left to 1. Right continues to 6, 7, 8. Characters 0, D, E. Not in need. Missing stays at 1. Now right equals 9. Character B. Need for B is 0. 0 is not greater than 0. So this is an extra B beyond what we need. Missing stays at 1. Decrement need for B to negative A. Right equals 10. Character is A. Need for A is 1. Greater than 0. This is one we actually need. Decrement missing to 0. Window is valid again. Now the shrink loop begins. Now left is at index 1. Character D. Not in need. So we move left to 2. Character O. Not in need. We move left to 3. Character B. Increase need for B from negative 1 to 0. And 0 is not greater than 0. So equal. So missing stays at 0. Window is still valid. Move left to 4. Keep checking. Eventually the window shrinks to B, A, and C starting at index 9 with length 4. That is shorter than the previous best of 6. Update the best. The final answer is B, A, and C. And the most common mistake in this problem is actually decrementing missing every time a character from T appears, even when the window already has more than enough for that character. The missing counter should only decrement when the need count is actually greater than 0, meaning we still need that character. Characters beyond the required count are extras that do not affect whether the window is valid. When coding this in an interview, you should be explaining the missing variable explicitly. You should say something like, okay, I track how many characters from T are still needed. When missing reaches 0, the window contains all required characters. A single sentence will give the interviewer a clear mental model for your entire algorithm. For each problem, try to identify the pattern and the subtype before hearing the answer. Problem 1 is, let's say, given a string and an integer k, find the length of the longest substring that contains at most k distinct characters. So what pattern applies? Is it longest or shortest? Now this is a variable size sliding window, longest subtype. Expand right, adding characters to a frequency map. When the map has more than k distinct keys, the window is invalid. Shrink from the left until the number of distinct keys drops to k or fewer. Update the best answer after each valid state, so time complexity is O of n, space complexity is O of k. Now let's look at the second problem. Where it is given an array of positive integers and a target sum, find the minimum length subarray whose sum is greater than or equal to the target. So what is the pattern? Longest or shortest? This is a variable size sliding window, shortest subtype. Expand right, adding to a running sum. When the sum meets or exceeds the target, the window is valid. Shrink from the left while the window stays valid, updating the minimum length at each step. This works well because all values are positive, so shrinking always decreases the sum. Time complexity is O of n, space complexity is O of 1. An important thing to note is that if the array contains negative numbers, this approach would break. Shrinking could increase the sum when negatives are present, which violates the window variant. For arrays with negatives, use prefix sums and hash maps from section 2. Now here's the third problem. Given a string, find the maximum number of vowels in a substring of length k. Now what pattern is that? This is a fixed size sliding window. Maintain a count of vowels in the current window size k. When the window slides, add 1 to if the new character enters is a vowel. Subtract 1 if the character leaving was a vowel. Type complexity would be O of n. Space complexity will be O of 1. The takeaway here is the two-step decision-making process. First ask, is the window size fixed or variable? If the size is given as k, use the fixed template. If you need to find the optimal size, use a variable template. Second, for variable windows, is the goal to find the longest or the shortest valid window. That determines where you update the answer. In real windows, the problem will not say, okay, use a sliding window. It will describe a constraint on a continuous range. Your job is to recognize that continuity plus a constraint, which signals the window approach. So we have now covered both the 2 pointers and sliding windows in detail. Let us build a clear decision framework for choosing between them. These techniques solve fundamentally different type of problems. So 2 pointers operate on pairs of positions, often in sorted data. The typical question is, find a pair or triplet that satisfies some condition. Pointer movement is based on comparing values at both pointers. Sorted input is usually required for the opposite direction variant. There is no window concept. Sliding windows operate on continuous subarrays or substrings. The typical question here is, find the longest or shortest subarray that satisfies some condition. The right pointer, always moves forward. The left pointer catches up when it's needed. Sorted input is usually not required. The window can be fixed size or variable size. The decision flow works as a series of questions. First, is the problem about a pair of elements? If yes, you use 2 pointers. Second, is the array sorted or should you sort it? If yes, opposite direction 2 pointers is needed. Third, is the problem about in-place modification or partitioning? If yes, same direction 2 pointers is needed. Fourth, is the problem about a continuous range with a constraint? If yes, sliding window is needed. Fifth, is the window size fixed, meaning k is given? If yes, use the fixed window template. If no, use the variable window template. Sixth, does the problem want the longest or the shortest valid range? That determines where you update the answer following the templates from slide 37. For interviews, articulating this reasoning is itself a very strong signal. Saying for example, this is a variable size window problem because we need the shortest continuous subarray satisfying constraint. If you say this statement in an interview, it immediately tells the interviewer that you have a structured approach to problem solving. That clarity is valued as much as the code itself. Before we wrap up this section, let us look at the mistakes that cause a majority of interviews not going the right way. Each one of these mistakes are preventable. The first mistake is moving the wrong pointer in opposite direction problems. If you move the wrong one, you break the invariant that eliminates the invalid pairs. The fix is to always derive pointer movement from sorted order. Sum too large means move right inwards. Sum too small means move left inwards. The second mistake is, forgetting duplicate handling in the threesome problem. Without it, the output contains duplicate triplets. The fix is to skip duplicate values in 3 places: the outer loop, the left pointer after a match, and the right pointer after a match. The third mistake is applying sliding window to subarray sum equals k problem when the array contains negative numbers. Many candidates reach for a window because the problem mentions continuous subarrays and it targets sum. But when negatives are present, shrinking the window can increase the sum. That breaks the window invariant entirely. The correct approach for arrays with negatives is prefix sum plus hash map from section 2. The fourth mistake is confusing longest and shortest window update logic. So if you update the answer at the wrong point, you get incorrect results. The fix for that is simple. Longest means update outside the shrink loop. Shortest means update inside the shrink loop. The fifth mistake is not deleting keys with 0 count from frequency maps. If a character's count drops to 0 but the key remains in the map, then checking the number of keys in the map gives the wrong count of distinct characters. The fix is to delete the key when its count reaches 0. And now here is something important for the interviews. When solving a sliding window problem, state the window invariant before writing any code. Say explicitly, my window invariant is that no character appears more than once. Or you can say that, okay, my window invariant is that the window contains all characters of t. This tells the interviewer exactly what your shrink condition is and makes your code more predictable. It also forces you to clarify your own thinking before you start coding. Every one of these mistakes is preventable by pausing for just 10 seconds to identify the subtype, whether it is fixed or variable, longest or shortest, and stating the window invariant before writing the first line of code. Now here's your reference sheet for this entire section. This slide is designed to be, quickly referenced before the interviews. So let us walk through the 5 core templates. The opposite 2-pointer template initializes left at 0 and right at n-1. The while loop runs as long as left is less than the right. If the condition is met, you return the result. If you need a larger value, you increment left. Otherwise, you decrement right. The same direction 2-pointer template initializes slow at 0, so fast it traces through the array. When the element at fast qualifies, copy it to the slow position and increment slow. The fixed window template computes the initial window of size k and then slides by adding the new element and removing the old element at each step, updating the answer as it goes. The variable window template for longest problem initializes the left at 0, right iterates forward, expanding the window. When the window becomes invalid, shrink from the left. After the window is valid, update the answer as the maximum of the current best and the window size. Now the variable window template for the shortest problem also initializes left at 0 with right iterating forward. But here when the window becomes invalid, enter the shrink loop. Inside the loop, update the answer as the minimum, then shrink. Continue as long as the window stays valid. For time complexities, opposite 2 pointers, same direction 2 pointers, fixing slide window, and variable sliding window all run in O of n. The space is O of 1 for the pointer based patterns and either O of 1, O of k, O of n, or O of the alphabet size for window patterns depending on what state you track. The one exception is the threesome problem which runs in O of n squared because of the outer loop, but that is optimal for the problem. The key rule of thumb is that if your solution has nested loops that both iterate over the full array, check whether a 2-pointer or sliding window approach can eliminate the inner loop. Now let us summarize everything we covered in this section. We learned 6 patterns here. Opposite direction 2 pointers, which you recognize when you have a sorted array and need to match pairs. The key insight is that you eliminate pairs by reasoning about the endpoint values. Same direction 2 pointers, which you recognize when the problem requires in-place modification or partitioning. The slow pointer marks the boundary, the fast pointer scans ahead. The fixed sliding window, which you recognize when the problem specifies a subarray of fixed size k. You slide by adding one element and removing one. Then variable window for the longest problems, where you expand eagerly and shrink only when the window becomes invalid. And then variable window for shortest problems, where you expand until valid, then shrink while the window stays valid. And then tracking the running state, as in the stock problem, where you maintain the state like a running minimum as you scan forward without ever looking backward. Now these patterns do not exist in isolation. They connect to techniques in later sections. 2 pointers on the sorted data reappears in section 5, where binary search also exploits sorted order to eliminate work. Same direction fast and slow pointers reappear in section 6, where LinkedIn cycle detection uses the same concept on nodes instead of array indices. Sliding window with frequency maps connect to section 9, where heap problems also track the best k elements in a window-like structure. And the variable window shrink logic connects to section 11, where some dynamic programming problems optimize space by keeping only the previous row, which is conceptually similar to maintaining a window state. 2 pointers and sliding window together cover roughly 20% of all medium difficulty LeetCode problems. Combined with the hash maps and prefix sums from section 2, you now have the tools to solve the majority of array and string problems you will encounter in the interviews. Now in the next section, section 4, we'll cover stack and monotonic stack problems. So those patterns handle problems where the most recent unresolved item matters, such as matching parentheses, finding the next greater element, and computing the largest rectangle in a histogram. While 2 pointers and sliding windows move through the data left to right in a structured sweep, stacks they lead to different decisions and resolve them in a reverse order. That is a fundamentally different way of thinking about sequence problems. In the previous 2 sections, every pattern we covered processed elements in a single left to right pass: sliding window, 2 pointers, prefix sums. In all of those, the decision about each element was made immediately. We looked at the element, we processed it, and then we moved on. Stacks introduced a fundamentally different idea. Sometimes when we encounter an element, we do not have enough information to make a decision about it yet. We need to wait. We need to see what comes later before we can resolve what we are looking at right now. The stack becomes a holding area for these unresolved elements. Each new element either gets pushed onto a stack because it also cannot be resolved yet, or it triggers the resolution of elements already waiting on the stack. Now the shift in thinking is important. Instead of thinking like, okay, process each element as soon as we've seen it, now the mental model becomes that, okay, we'll defer elements until we have enough information to resolve them. Once this clicks, an entire category of problems open up. So now in this section over here, we'll start with the stack fundamentals and LIFO reasoning, which is last in first out. Then we'll cover how stack solves matching and nested structure problems like parentheses validation. After that, we'll look at how stacks can track state, giving us O(1) access to things like current minimum. Then we'll move into monotonic stacks, which are a more advanced technique for solving like next greater element and next smaller element type problems in O(n) time. Then we'll walk through multiple problem solutions with full traces and close with a reference sheet and pattern recognition guide. Now, in terms of where this shows up in interviews, stack problems appear across every company tier. At large tech companies, valid parentheses is a common warm-up question, and problems like daily temperatures and largest rectangle in histogram are main round questions. At mid-sized companies, they focus on parentheses matching, express evaluation, and basic monotonic stack in their interviews as well. For startups, they tend to test parsing nested structures and processing event logs with undo operations. And in online assessments, next greater element and stock span problems are frequently used as time questions. Now, the core idea is to carry through this entire section is this. Use a stack when the most recent unresolved item is the one that matters. Use a monotonic stack where each element needs to know the next greater or next smaller element. So now what exactly is a stack? Stack is a collection where the last element added is the first element removed. This is called last in first out or LIFO. There are only three operations that matter. Push adds an element to the top, pop removes and returns the element from the top, and peek reads the top element without removing it. The critical property is that all three of these operations run in O(1) time. Push is O(1), pop is O(1), and peek is always also O(1). Checking the size and checking whether the stack is empty are also O(1). There is no searching, no scanning, no iteration involved in any of these operations. Now, when does LIFO ordering actually matter in a problem? So stacks are the right tool when the problem has the most recent first structure. So the element we need to deal with next is always the one we saw most recently, but have not yet resolved. Now think about real systems that work this way. An undo operation in a text editor reverses the most recent action first. Not the first action, not the random action, the most recent one. That is LIFO. A browser's back button takes us back to the most recent visited page. Function calls in any programming language work the same way. When a function calls another function, the inner function must return before the outer function can continue. The most recently called function returns first, and this is why it is called the call stack. And matching parentheses follow the same principle. The most recently opened bracket must be the first one closed. Now, for example, in Python programming language, there is no need for a special stack class. A regular list works perfectly. The append method acts as a push, the pop method acts as pop, and indexing with -1, stack -1 acts as peek. One common mistake is reaching for collections.dq when implementing a stack. DQ is designed for double-ended access and is the right choice for queues, but for stacks, where we only interact with one end, a plain list is simpler and equally efficient. For interviews, the skill that is being tested with the stack problems is the pattern recognition. For example, can you identify that a problem has a LIFO structure? The strong signals are the words like most recent, last, nested, or matching in the problem statement. When those words appear in a problem statement, a stack is very likely to be the right pattern and right tool to use. So the first major category of stack problems is matching and nesting. The recognition signal is clear. The problem involves pairing elements that are nested inside each other. Opening and closing brackets, HTML tags, nested function calls. The rule is always the same. The most recently opened element must be the first one closed. So why does the stack work for this? When we encounter an opening element, we push it onto the stack. It is unresolved. It is waiting for its matching closer. So when we encounter a closing element, the top of the stack should be its matching opener. If it matches, we pop the stack. That pair is resolved. If it does not match, the input is invalid. The matching template follows this exact logic. Over here, as you can see, we create an empty stack. We iterate through each character. If the character is an opener, we push it. If the character is a closer, we check two things. Is the stack empty? And does the top of the stack match the expected opener for this closer? If the stack is empty, that means the closer appeared with no opener to match. That is invalid. If the top does not match, the nesting order is wrong. That is also invalid. If it does match, we pop and continue. At the end, the stack should be empty. If it is not, there are unmatched openers left. Now, a question that often comes up is, why can we not just solve this with simple counter? Just increment for every opener and decrement for every closer. The answer is that a counter tracks, quantity but not order. Consider the string open parenthesis, close square bracket. That has one opener and one closer. A counter would say the count is balanced, but the types do not match. Or consider the string open parenthesis, open square bracket, close parenthesis, close square bracket. The counts are balanced for each bracket type, but the nesting is wrong. The square bracket opens inside the parenthesis but closes after the parenthesis closes. Only stack preserves the order needed to verify correct nesting. For interviews, matching problems are the most common, easy level stack questions when it comes to LeetCode interviews. The main skill being tested is understanding LIFO order. The edge case that trips up most candidates is accessing the top of the stack without first checking whether the stack is empty. Now let us apply the matching pattern to the most classic stack problem, which is valid parenthesis LeetCode problem number 20. Given the string containing only the characters open and close parentheses, curly braces, and square brackets, we need to determine if the string is valid. Every open bracket must be closed by the same type of bracket and in the correct nesting order. The solution uses a dictionary that maps each closing bracket to its corresponding opening bracket. Close parenthesis maps to open parenthesis, close curly brace maps to open curly brace, close square bracket maps to open square bracket. We iterate through the string. If the character is the closer, meaning it exists as a key in our dictionary, we check whether the stack is non-empty and whether the top of the stack matches the expected opener. If either check fails, we return false. If both pass, we pop the matched opener of the stack. If the character is not a closer, it must be an opener, so we push it. At the end, we return the true only if the stack is empty. Now let us trace through the input string here. Open parenthesis, open curly brace, open square bracket, close square bracket, close curly brace, close parenthesis. We see the open parenthesis, we push it. Stack now has one element. We see the open curly brace, we push it as well. Stack now has two elements. We see the open square bracket, we push it. Stack now has three elements. Now we see the closed square bracket. We check the top of the stack, which is the open square bracket. It matches, so we pop. Stack is back to two elements. Next is the closed curly brace. So top of the stack is open curly brace. It matches as well, so again we pop. Stack now only has one element. Finally, the closed parenthesis. Top of the stack is the open parenthesis. It matches. We do the pop. Stack is empty. We return true. Now there are four edge cases here that are worth knowing. An empty string is valid because there is nothing to mismatch. A single opener with no closer is invalid because the stack is not empty at the end. A single closer with no opener is invalid because the stack is empty when you try to match. And a string like open parenthesis close square bracket is invalid because the closer does not match the top of the stack. Now here's something important for interviews. Use the dictionary mapping closers to openers rather than writing a chain of if-else statements. The dictionary approach is much more cleaner. It handles all the bracket types uniformly. And if the interview asks you, okay, like what if we add an angle bracket? We just add one entry to the dictionary instead of restructuring the code. This is a kind of design decision that signals experience. Valid branches is like a very common LeetCode interview problem, so it is often used as a warm up in the first 20 minutes of interview question or like interview round. The second major category of stack problems is stack tracking. The recognition signal here is different from matching. The problem requires maintaining access to some aggregate value like the current minimum or maximum across a series of push and pop operations. And the requirement is that the access must be O of 1 at any point, not O of n. Now here's a challenge. Suppose we track the minimum using a single variable. Every time we push a new element, we update the minimum. And that works fine for pushes. But what happens when you pop the current minimum of the stack? Now we need to find the new minimum among the remaining elements. The only way to do that with a single variable is to scan the entire stack, which is O of n. That defeats the purpose of having O of 1 access. The insight that solves this is pretty elegant. Store the aggregate state alongside each element. Instead of pushing just the value, you push a tuple containing both the value and the aggregate state at the level of the stack. When you push a new element, we compute the new minimum by comparing the element with the minimum stored at the current top. When we pop, the minimum automatically reverts to the correct value because it is now stored in the tuple at the top. Now, so why does this work? Each stack level captures a snapshot of the aggregate at that point in time. The minimum stored at the position 5 in the stack tells us the minimum of all elements from position 0 through position 5. When you pop position 5, position 4 has the correct minimum for elements 0 through 4. No recomputation is needed, no scanning, just read the tuple at the top. This pattern generalizes beyond minimums. We can track the current maximum by storing the max of the new value and the previous max at each level. We can track a running sum by storing the previous sum plus the new value. We can track a running, product the same way. The principle is always the same. Store enough state at each level so that the popping an element automatically restores the correct aggregate. For interviews, the min stack problem tests whether we can design a data structure with 0 of 1 guarantees by storing redundant data. The same design principle reappears in more advanced problems like LRU cache and LFU cache. Recognizing this principle early shows the interviewer that we think in terms of design patterns, not just isolated solutions. So let us build the min stack, LeetCode problem number 155. The requirement is to design a stack that supports push, pop, top, and retrieving the minimum element all in O of 1 time. The implementation uses a list where each entry is a tuple of two values, the element itself and the current minimum at that point in the stack. The push method computes the new minimum by comparing the incoming value with the minimum stored at the current top. If the stack is empty, the element itself is the minimum. The pop method simply pops the top tuple. The top method returns the first element of the top tuple, which is the actual value. And the getMin method returns the second element of the top tuple, which is the tracked minimum. Now let us trace through the sequence of operations to see how the minimum updates automatically. So first we push 5, the stack is empty, so the minimum is 5 itself. The stack now holds the tuple 5, 5. Then you push 3. The current minimum at the top is 5. We compare. The minimum of 3 and 5 is 3, so we push 3, 3. Then you push 7. The current minimum at the top now is 3, so the minimum of 7 and 3 is 3. So we push 7, 3. Notice that even though 7 is larger, the minimum is still 3 because 3 is below in the stack. Now we pop. The tuple 7, 3 is removed. The new top is 3, 3. The minimum is still 3, which is correct. Then you pop again. Now the tuple 3, 3 is removed. The new top is 5, 5, and the minimum is now 5. It has been restored automatically. We did not scan anything. We did not recompute anything. The correct minimum was already sitting there in the tuple. So now we push 2. The current minimum at the top is 5. The minimum of 2 and 5 is 2. So we push 2, 2, and the minimum is now 2. Now the most common mistake with this problem is using a separate variable for the minimum and updating it on each push and pop. This seems simpler, but no, it breaks the moment the current minimum gets popped. At that point, the variable holds a stale value, and the only way to find the new minimum is to scan every remaining element. The tuple approach eliminates this problem entirely because each level of the stack is self-contained. The min stack problem that we just discussed is a very frequently asked interview problem. It is a data structure design question which tests a different skill than just purely algorithm questions. Here the interviewer is not looking for clever tricks, they just want to see clean interface design with provable overfund guarantees. Now let us test what we have covered so far with 3 practice problems. For each one, you should try to identify why a stack is needed before reading the answer. So the first practice problem is, given a string containing only open and close parentheses, you need to find the length of the longest valid parentheses substring. For example, the string, let's say left parentheses, right parentheses, returns true. The string right parentheses, left parentheses, right parentheses, left parentheses, and right parentheses returns 4. So now the question is, what pattern applies here, and why cannot we just count openers and closers? So now this is stack for matching problem, extending the pattern from the valid parentheses slide we just covered in this section. A counter can tell us the total number of matched pairs, but cannot tell us where valid substrings start and end. The approach is to push the indices of unmatched parentheses onto the stack. After processing the entire string, the indices remain on the stack are the positions of the unmatched parentheses. The gaps between these unmatched positions define the valid substrings. The longest gap is the answer. Now let's look at the second practice problem, which is to design a stack that supports push, pop, and get max in one time. So let's first identify what pattern applies here. This is a straight tracking pattern, so it is exactly the same principle as min stack, just with max instead of min. Each element over here is stored as a tuple containing the value and the current maximum. When pushing, we compute the max of the new value and the max stored at the current top. When popping, the max of the new top is automatically correct. No recomputation is needed. Now let's look at the third practice problem, for which, let's say you're given a string of digits and operators in reverse Polish notation, and then you have to evaluate it. For example, the tokens 2, 1, plus 3, and asterisk evaluate to 9. So what pattern applies here? This is a basic stack processing problem, so we push numbers onto the stack. When we encounter an operator, we pop 2 numbers, apply the operator, and push the result back. The stack holds intermediate results in the correct order because LIFO matches the evaluation order of reverse Polish notation. The 2 most recently pushed numbers are always the operands on the current operator. So these 3 practice problems represent the 3 core stack use cases: matching and nesting, state tracking, and evaluation or processing. Every stack interview question falls into one of these categories. Now, being able to identify which category a problem belongs to is the first step towards solving it. Okay, now let us move forward beyond the basic stack patterns into something much more complex in the next few slides. This is a concept that comes up in almost every senior level stack interview question. The recognition signal here is that the problem asks for each element something like, okay, what is the next element that is greater than this one? Or it could be a statement like, what is the next element that is smaller than this one? So the brute force approach would be to check every remaining element for each position, giving O of n squared time. A monotonic stack solves this in O of n time. So now what is a monotonic stack? It is a stack that maintains its elements in strictly increasing or strictly decreasing order from bottom to top. The key mechanism is, when a new element arrives that violates the order, elements are popped from the top until the order is restored. And here's the important part. Each element that gets popped has found its answer. The element that has caused the pop is the answer itself. Now let us think about it, why this works. Elements that sit on the stack waiting for the answer, they are unresolved. They were pushed because at the time they arrived, there were nothing to resolve them. When a new element comes in that is larger than the top has been waiting for something larger and it has just found it. So we pop it and record the answer. If the next element on the stack is also smaller than the new element, it too has found its answer. So we keep popping until the stack order is restored, and then we push the new element because it is now waiting for its own answer. So now the natural question is, why is this O(n) if there is a while loop inside a for loop? The answer comes from counting total operations, not per iteration operations. Each element is pushed onto the stack exactly once. Each element is popped from the stack at most once. Across all iterations, of the for loop, the total number of push operations is n, and the total number of pop operations is at most n. So total work is at most 2n operations, which is again O(n). The while loop does not multiply with the for loop; it just distributes across it. And here's something important for interviews. The strongest recognition signals for monotonic stack problems are very specific phrases like next grid element, next small element, previous grid element, or days until warmer temperature. When any of these phrases appear in a problem description, monotonic stack is almost always the answer. These are among the most reliable pattern signals in all of the competitive programming and interview preparation, so please remember them. So monotonic stack problems are medium to hard difficulty and they appear frequently in interviews for large tech companies. They test whether we understand the invariant based reasoning that makes the O(n) solution correct, not just whether we can memorize a template. We understand what a monotonic stack is and why it works. The immediate next question is, when do we use a decreasing stack and when do we use an increasing stack? Getting this wrong is the single most common mistake in monotonic stack problems, so let us make sure the distinction is pretty completely clear. So there are two variants. A monotonic decreasing stack keeps values in decreasing order from bottom to top. It finds the next greater element for each position. The pop condition is pretty simple. When a new element arrives that is greater than the top has found its answer, so we pop it. A monotonic increasing stack is the opposite. It keeps values in increasing order from the bottom to top. It finds the next smaller element. The pop condition triggers when a new element arrives that is smaller than the top. Now let us trace through a decreasing stack to see it in action. Suppose the stack currently holds 8, 5, and 3 from bottom to top. That is a valid decreasing sequence. Now a new element arrives, let's say 6. We compare the 6 with the top of the stack, which is 3. 6 is greater than 3, so 3 has just been found, that is the next greater element. We pop 3 and record that the next greater element of 3 is 6. Now the top of the stack is 5. 6 is still greater than 5, so 5 has also found its next greater element. We pop 5 and record 6 as its answer. Now the top is 8. 6 is less than 8, so decreasing order is maintained. So then we push 6. The stack is now 8 and 6. Both 3 and 5 got resolved in this single step. Now let us trace through an increasing variant. Let's say the stack still holds 2, 5, and 8 from bottom to top. A valid increasing sequence, so that is good. And let's say a new element arrives, which is 4. We compare 4 with the top, which is 8. 4 is smaller than 8, so 8 has found its next smaller element. We pop 8 and record that the next smaller element of 8 is 4. The new top is 5. 4 is still smaller than 5, so 5 also gets resolved. We pop 5 and record 4 as its answer. Now the top is 2. 4 is greater than 2, so the increasing order is maintained. We push 4, and now the stack is 2, 4. Now notice the pattern here. In both the cases, the stack order is the opposite of what we were searching for. To find the next greater element, we maintain a decreasing stack. To find the next smaller element, we maintain an increasing stack. This feels counterintuitive at first, but the logic is pretty straightforward once you think about it. A decreasing stack keeps elements that are still waiting for something bigger. The moment something bigger shows up, it resolves all the smaller elements on top. An increasing stack keeps elements waiting for something smaller. The moment something smaller shows up, it resolves all the large elements on top. And this is something you should note down. To find the next greater element, you should be using a decreasing stack and pop when the new element is greater. To find the next smaller element, you should be using an increasing stack and pop when the new element is smaller. The stack order is always the opposite of what you are looking for. If you remember this one rule, you will be never picking the wrong variant in an interview, which is super important. Now here's something important for the interviews. Confusing these two variants is the number one reason candidates they kind of screw up these category of problems. So if it's not that the concept is hard, it's just that under pressure it's easy to set up the wrong comparison direction. So when you're facing monotonic stack problems, before writing any code, you should be stating the variant out loud. For example, you should be saying like, okay, I need the next great element, so I'll maintain a decreasing stack and pop when the new element that is greater than the top. That one sentence locks the correct direction and prevents the most common error. Now let us see this pattern applied to a real problem. So daily temperature is a LeetCode problem number 739 and is one of the most commonly asked monotonic stack problem in interviews. The problem gives us an idea of daily temperatures and asks, okay, for each day, how many days do we have to wait until a warmer temperature? If there is no future warmer day, the answer is 0. For example, let's say you're given the temperatures 73, 74, 75, 71, 69, 72, 76, 73. Now the expected output here should be 1142 1100. This is essentially the next greater element problem. For each temperature, we need the next day with a strictly higher temperature. From the previous slide, we know that the next greater means we should use a monotonic decreasing stack and pop when the new element is greater than the top. Now the solution over here initializes a results array of zeros and an empty stack. We iterate through each index. For each index we check, okay, is the current temperature greater than the temperature at the index stored on the top of the stack? If so, okay, then the top of the stack has found its next warmer day. We pop the index and the answer for that index is the current index minus the popped index. That gives us the number of days between the two. So we keep popping as long as the current temperature is greater than the top. Then you push the current index onto the stack. There is a critical design choice over here. So the stack store indices, not the temperature values. So we need indices because the answer requires computing a distance, which is how many days until a warmer temperature. That distance is the difference between the two indices. We can always look up the actual temperature value from an index using the original array, but we cannot recover an index from a value. This is the pattern we'll formalize in the later slide. So now the time complexity for this is O of n, and because each element is pushed once and popped at most once, the space complexity is O of n for the stack in the worst case, which happens when temperatures are in strictly decreasing order and nothing ever gets popped until the very end. Now daily temperature is the cleanest illustration of the monotonic stack pattern because the problem motivation is immediately intuitive. Next greater element maps directly to the next warmer day. This makes it an ideal problem to master first before tackling harder variants. Let us trace through the full execution step by step. The input is temperature is let's say equal to 73, 74, 75, 71, 69, 72, 76, 73. At index 0, the temperature is 73. The stack is empty, so there's nothing to compare. We push the index 0, the stack holds 0. At index 1, the temperature is 74. We compare 74 with the temperature at the top of the stack, which is index 0, temperature 73. Now 74 is greater than 73, so index 0 has found its next warmer day. We pop index 0 and record answer 0 equals 1 minus 0, which is 1. The stack is now empty and we push the index 1. Now at index 2, the temperature is 75. The top of the stack is index 1, the temperature is 74. Now 75 is greater than 74, so we pop index 1, answer 1 equals 2 minus 1, which is 1. So the stack is empty and we push index 2. At index 3, the temperature is 71. The top is index 2, temperature 75. 71 is less than 75, so no pop. We push the index 3. Now the stack now holds indices 2 and 3, corresponding to temperatures 75 and 71. Notice that this is a decreasing sequence. At index 4, the temperature is now 69, so 69 is less than 71 at the top. No pop, so we push the index 4. The stack holds 2, 3, 4, corresponding to the temperatures 75, 71, 69, which is still decreasing. At index 5, the temperature is 72. Now things get interesting. 72 is greater than the temperature at index 4, which is 69. So index 4 has found its warmer day. Pop index 4 and answer 4 equals 5 minus 4, which is 1. The new top is the index 3, temperature 71. Now 72 is greater than 71, so pop index 3, answer 3 equals 5 minus 3, which is 2. So the new top index is the index 2, which is temperature 75. Now 72 is less than 75, so we start popping, and push index 5. So the stack now becomes 2, 5. At index 6, the temperature is now 76. 76 is greater than the temperature at index 5, which is 72. So you pop index 5, answer 5 equals 6 minus 5, which is 1. The new top is index 2, temperature 75. 76 is greater than 75, so pop index 2 and answer 2 equals 6 minus 2, which is 4. The stack is empty, and then you push index 6. Now at index 7, the temperature is 73. 73 less than the temperature at index 6, which is 76, so no pop. We push the index 7 and the stack holds 6 and 7. We have now finished iterating. Indices 6 and 7 are still on the stack. They never found a warmer day. The answers remain 0, which is the default we initialized. So the final answer is 11421100. Notice what the stack looked like throughout this trace. At every point, the temperatures corresponding to the indices on the stack were in decreasing order. When indices 2, 3, and 4 were on the stack, the temperatures were 75, 71, and 69. That is a valid decreasing sequence. When 72 arrived, it broke the sequence by being greater than 69 and 71, so those two indices got resolved. But 75, was still larger, so it stayed. Now, being able to trace monotonic stacks step by step, like this one on a whiteboard, is exactly what the interviewers would like to see. If you can do this trace fluently, you will understand the pattern well enough to apply in the interview and as well. Now let us generalize what we just saw with daily temperatures into a reusable pattern. The general next greater element problem, which says that for each element in an array, find the first element to its right that is strictly greater. If no such element exists, the answer is -1 or some other default. So here's a template which is pretty compact. So we initialize the results array filled with -1. We create an empty stack. We iterate through each index. Inside the loop, we run a while loop. As long as the stack is not empty and the current value is greater than the value at its index on the top of the stack, we pop and record the current value as the answer for the popped index. After the while loop, we push the current index. That is the entire template. From the single template, there are 5 variants that cover nearly every monotonic stack problem. So the first one is the next greater element, which is the base template. We pop when the new element is greater than the top. Daily temperatures and the next greater element 1 and 2 on LeetCode use this variant. The second variant is the next smaller element. So the only change here is the comparison direction. We pop when the new element is smaller than the top. So the stock span problem uses this variant. Now the third one is the previous greater element. Instead of iterating from left to right, we iterate from right to left. We still pop when the new element is greater than the top. So, the buildings with ocean view problem on LinkedIn use this pattern. And the fourth is the previous small element. We iterate right to left and pop when the new element is smaller than the top. So on LeetCode, the largest rectangle in histogram, problem actually relies on this pattern. So now the fifth variant, it handles circular arrays where the element after the last wraps back to the first. The trick is to iterate through the array twice by going from index 0 to 2n minus 1. We use modular arithmetic, which is I mod n, to access the correct index. This ensures that every element gets a chance to find its next great element from both directions. So now on LeetCode, the next great element 2 problem uses this approach. So now the key takeaway here is that all of these variants are minor modifications of the same template. The code mechanism never changes. A stack holds unresolved elements. A new element trigger pops when it satisfies a comparison condition, and each popped element records the new element as its new answer. The interviewer is testing whether we can adapt the template to a specific variant, not whether we have memorized each one independently. So here's the scenario. We have a histogram where each bar has a width of 1 and varying heights. We need to find the area of the largest rectangle that can be formed using one or more consecutive bars. This is a LeetCode problem number 84, and it's one of the very common monotonic stack problems. So for the input heights, let's say you're given an array of 2, 1, 5, 6, 2, 3, and the expected answer for this would be 10. Now the brute force approach would be, for each bar, expand left and right to find how far the rectangle can extend at that bar's height. This checks every pair of boundaries and run an O of n squared. The monotonic stack inside is this. For each bar, the largest rectangle that uses the bar as the shortest bar extends from the previous smaller bar on the left to the next smaller bar on the right. If we know those two boundaries, the width is next smaller index minus previous smaller index minus 1, and the area is height times width. Now, monotonic increasing stack finds these boundaries pretty efficiently. So as you can see, the implementation here uses a stack that maintains indices in increasing order of their heights. Where a new bar is shorter than the bar at the top of the stack, the top bar has found its right boundary, which is the current index, and its left boundary, which is the new top of the stack after the popping. We compute the width using the formula, current index I if the stack is empty, or I minus the new stack top minus 1 if the stack is not empty. The area is popped bar's height times the width, so we track the maximum area seen so far. Now here's one important detail that we should keep in mind, which is the sentinel value. We append the 0 to the end of one of the heights array before processing, so this 0 height bar is shorter than every real bar. So when we reach it, every remaining bar on the stack gets popped off and its area gets calculated. Without this sentinel, bars remaining on the stack after the loop would be missed entirely. We remove the sentinel after processing to avoid modifying the input. The time complexity for this is O of n, and the space complexity for this is O of n as well, following the same reasoning as all monotonic stack problems. Each element is pushed once and popped at most once. So largest rectangle in histogram is a very common LeetCode interview problem. So it combines the monotonic stack mechanism with the geometric insight about how previous smaller and next smaller boundaries define the maximum rectangle. This combination tests deeper understanding of the pattern, not just the template application. So let us trace through the full execution to see exactly how the stack finds those boundaries. The input is heights equal to 2, 1, 5, 6, 2, 3 with 0 appended as a sentinel. So we process 2, 1, 5, 6, 0, 2, 3, 0. At index 0, height is 2, stack is empty. So we push 0, stack holds 0. Then at index 1, the height is 1. So 1 is less than the height at index 0, which is 2. So we pop index 2. The height of the popped bar is now 2. Now the stack is empty, which means the bar is smallest we have seen so far. The width extends all the way to the left edge, so width equals the current index, which is 1. Area is 2 times 1, which is 2, so max area is now 2. So we push index 1. Now indices 2 and 3, the heights are 5 and 6. Both are greater than the tops, we just push, so stack becomes 1, 2 and 3. Now at index 4, the height is 2. This is where the interesting work happens. 2 is less than the height at index 3, which is 6. So we pop index 3. Height is now 6. The new top is index 2. Width is 4 minus 2 minus 1, which is 1. And area is 6 times 1, which is equals to 6. Max is now 6. Now, still at index 4, 2 is less than the height at the index 2, which is 5. So we pop index 2. Height is now 5. And the new top is index 1. Width is 4 minus 1, which is 2. So area is 5 times 2 equals 10. Max is now 10, and this rectangle is formed by the bars at indexes 2 and 3, both of which are at least height 5, giving a width of 2 and area of 10. Now 2 is greater than the height at the index 1, which is 1, so the increasing order is restored. Now we push the index 4, stack is 1 and 4. At index 5, height is 3, so 3 is greater than height at index 4, which is 2, so we push 5, stack is 1, 4 and 5. At index 6, the height is 0, which is a sentinel, so 0 is less than everything. So everything gets popped. Pop index 5, height 3, width is 6 minus 4 minus 1, which is 1. Area is 3, and then after that we pop index 4 and the height becomes 2. Now the width is 6 minus 1, which is 4, and now the area becomes 8. Then we pop the index 1, height becomes 1, stack is now empty, so width is 6, area is also 6, and none of these exceed our current max of 10. Hence the final answer becomes 10, and the width calculation actually is one of the very hardest problem to internalize. So when a bar gets popped, the width of the rectangle is the gap between the current index, which is the next smallest bar, and the new top of the stack, which is the previous smaller bar. The formula I minus stack top minus 1 captures exactly this gap. When the stack is empty after popping, this means the popped bar is the smallest seen so far, and the rectangle extends all the way from the left edge to the current position. If we can explain this formula clearly in an interview, we have demonstrated essentially, like good understanding of monotonic stacks. This is the level of understanding that interviewers are looking for. A common source of confusion when first working with stack problems is, okay, should the stack store the actual values or the indices of the stack to those values? The rule is pretty straightforward. If the answer requires knowing the position of an element, such as the distance, an index difference, or the original location, we should be storing indices. If the answer only requires the value itself, either approach works. But indices are almost always the safe default because an index gives us both the position and the value. We can always look up the value using the original array, but if we store only the value, we lose the position information entirely. Now let us walk through how this applies to the problems we have just covered. Now daily temperature needs a distance in days between two positions. This is an index difference, so the stack should store indices. The next greater element 1 problem needs the greater value itself. So technically these values would work, but indices would work too and they keep the code consistent. Now the largest rectangular histogram, it needs the width between the boundaries, which is entirely position dependent. The valid parenthesis problem needs to check whether brackets match. No position information is needed here. The stack stores the characters themselves, so that's how it works. The min stack problem needs a value and the associate minimum. The stack stores the tuples of values here. In the stock span problem, it needs a number of consecutive days, which is position dependent. The stack should store indices. Now the default should be always to store indices. In almost every monotonic stack problem, the answer depends on the position. Storing indices gives us both pieces of information, so storing values gives us only one. The most common mistake here is storing values in a monotonic stack problem that requires distance calculations. When we realize mid-implementation that we also need positions, we have to add a separate data structure or refactor the stack to store tuples. This wastes time in an interview and introduces opportunities for bugs. Starting with indices, avoid this entirely. For interviews, deciding what to store on the stack is one of the first design decisions to make. Making the right choice immediately signals experience to the interviewer. Making the wrong choice here and having to refactor mid-interview will waste your valuable time and can create confusion in the code. Let us talk about the mistakes that cause the most failures in stack and monotonic stack interview problems. So these are not conceptual misunderstandings. They are small mechanical errors that are easy to make under time pressure. The first mistake is using a stack mechanically without understanding the invariant. A candidate might write the current template but not be able to explain what the stack represents or what triggers a pop. When the interviewer introduces a twist, the candidate cannot adapt because they memorize the code without understanding the reasoning. The fix is pretty simple. Before writing any code, state what the stack represents and what conditions triggers a pop. The second mistake is storing values when indices are needed. We just covered this on a previous slide, so if the problem requires distance or positions, values alone are not enough. Default to storing indices for monotonic stack problems. The third mistake is forgetting to handle elements remaining on the stack after the loop finishes. In a greater element problem, for example, any element that never found its answer is still sitting on the stack when the loop ends. If we do not handle these elements, the answers are silently wrong. Now the fix for that is to either process the remaining elements after the loop or use a central value like the zero we appended in the histogram problem that forces everything to pop. Now the fourth problem mistake is using the wrong monotonic direction. This means finding the next smaller element when the next greater was needed, or the reverse. The fix is the rule from the earlier slide, which is that a decreasing stack finds next greater, and increasing stack finds next smaller. The stack order is the opposite of what we are looking for. Now the fifth mistake is not checking whether the stack is empty before accessing the top. This causes a runtime error when a closure appears and there is no matching opener, or when we try to peek at an empty stack during a monotonic stack traversal. The fix is to always guard with a check like, okay, if stack before accessing stack -1 or calling stack top to pop. And here's something important for interviews. When presenting a monotonic stack solution, state the invariant explicitly before writing code. Something like, for example, the stack maintains indices in decreasing order of the new temperature values. When a new temperature is higher than the top has found its next warmer day. That single sentence tells the interviewer everything about the approach. It shows that we understand the mechanism, not just the template. So monotonic stack problems have a high failure rate in interviews, not because the concept is itself difficult, but because these small mechanical errors compound under time pressure. Eliminating them systematically is the difference between solving the problem and running out of time when debugging. Here's a reference sheet for the entire section. The slide is designed to be screenshotted and essentially used for quick revision before the interviews. There are 5 pattern templates to know. The first is matching and nesting. So you create a stack, iterate through the string. If the character is an opener, we push it. If it is a closer, we check whether the stack is non-empty and the top matches the expected opener. If it does not match, we return false. Pop if it matches, and at the end, return true only if the stack is empty. The second is the state tracking, as in the min stack pattern. When pushing, store a tuple of value and the minimum of the value and the current minimum. Pop just removes the top tuple. Get min reads the second element of the top tuple. All operations are O of 1. The third is the next greater element pattern using a decreasing stack. For this, you iterate through the array. While the stack is non-empty and the current value is greater than the value at the top index, you pop and record the current value as the answer for the popped index. Then you push the current index. The fourth is the next smaller element pattern using an increasing stack. The same structure, but the comparison direction is flipped. Pop when the current value is less than the value at the top index. The fifth is the largest rectangle histogram pattern using an increasing stack with a sentinel. Append a 0 to force all elements to pop. When popping, compute the height from the popped index and the width from the gap between the current index and the new stack top. Track the maximum area. For complexities, every pattern in this section is O of n time complexity and O of n time space complexity. Matching is O of n time and O of n space. Min stack operations are O of 1 time with each O of n total space. Next greater element is O of n time and O of n space. Largest rectangle is also O of n time and O of n space. The key insight that ties all of these together is that each element is pushed at most once and popped at most once. Even if there is a while loop inside a for loop, the total number of pops across all iterations cannot exceed n. This is why the nested loop structure is still O of n total, not O of n squared. Now, understanding this amortized analysis is important because the interviewer will most likely ask about it in the interview. Now, let us consolidate everything from this section into a pattern recognition framework. We covered 5 distinct patterns. So stack for matching, where the recognition signal is nested or paired elements like brackets and tags. And the key insight is that the most recently opened must close first. Now stack for state tracking, where the signal is needing O of an access to min or max across pushes and pops, and the insight is to store aggregate state alongside each element. So monotonic decreasing stack, where the signal is next greater element or days until warmer, and the key mechanism is popping when the new element is greater than the top. Now for monotonic increasing stack, where the signal is next smaller element or boundary finding, and you pop when the new element is smaller than the top. And the sentinel value trick, where the elements remaining on the stack after the loop get forced out by appending a value that triggers universal popping. So up to this point, every pattern we have covered has processed every element in the input at least once. Sliding window, 2 pointers, prefix sums, all of them give us an O of n as a best case. However, that changes now. Binary search is the first pattern in this course that achieves the O of n log time. Instead of looking at every element, it eliminates half the search space with a single comparison. For an array of 1 million elements, for example, that means at most 20 comparisons instead of 1 million comparisons. That is not a small improvement. That is a fundamental different category of efficiency. But here's what makes this section very important for interviews. Binary search is not just for finding an element in a sorted array, so that is level 1, and it is the version that most engineers learn first. Level 2 is searching in modified sorted structures like arrays that have been rotated at an unknown point. And level 3 is, which is the most important for interviews, is the binary search on the answer space. In this variant, you are not searching through an array at all. You are searching through the range of possible answers to find the smallest or largest value that satisfies the condition. The deeper skill that ties all 3 levels together is recognizing the monotonic structure. Whenever a yes or no condition flips from false to true across an order range and never flips back, binary search can find that flip point in O of n log n time. That single insight unlocks an entire category of problems that do not look like binary search at first glance. In terms of where this appears, binary search on answer problems are especially popular in online assessments because they are very difficult to brute force within the time limit. At big tech companies like Google, Amazon, Meta, rotary variants and binary search on answer are common medium to hard questions. And at the phone level, the standard binary search and lower bound, upper bound questions appear frequently as warm-ups that are expected to be solved quickly and without bugs. So now let us start with the foundation, which is a bug-free binary search template. Binary search, it sounds simple. For example, the common approach is to look at the middle element, decide which half to search, and then repeat. However, during interviews, writing a current implementation gets surprisingly difficult. Studies have shown that the majority of professional programmers introduce a bug in the first attempt at binary search. The bugs are subtle, they involve off by one errors and infinite loops, and they are very hard to debug under interview pressure. So, before we look at any problem, let us establish a template that avoids these bugs entirely. The function takes over here a sorted array and a target value. We initialize 2 pointers. Left starts at index 0 and right starts at the last index, which is the length of the array minus 1. The loop runs while the left is less than or equal to the right. Inside the loop, we compute mid as left plus the quantity right minus left, integer divided by 2. So if the element at mid equals the target, we return mid. If the element at mid is less than the target must be in the right half, so we set the left to mid plus 1. Otherwise, the target must be in the left half, so we set right to mid minus 1. If the loop exits without finding the target, we return -1. So there's one detail which is worth pausing on. The mid calculation uses left plus right minus left divided by 2 instead of the more intuitive left plus right divided by 2. Both expressions compute the same value mathematically, but left plus right can overthrow in languages with fixed size integers like Java and C++. If left and right are both close to 2 billion, their sum exceeds the 32-bit integer limit. The subtraction form, avoids this entirely. So also in Python, integers have arbitrary precision, so overflow is not an issue there. But using the save form is a good habit, and interviewers will actually notice that when you use it. It signals that you think about the edge cases, even though it doesn't matter which programming language you're programming in. Now the correctness of this template rests on a loop variant. At every iteration, if the target exists in the array, it is somewhere within the range from index left to index right, inclusive. Each iteration shrinks this range by at least one element because we always move left to mid plus 1 or right to mid minus 1, never to mid itself. So when left crosses right, the range is empty and we know that the target does not exist. In terms of performance, the time complexity is off log-in because we have the search space each iteration. The space complexity is off 1 since we only use a very few variables. For an array of 1 million elements, binary search needs at most 20 iterations. For 1 billion elements, it needs at most 30. So this template is the foundation for everything in this section. Memorize it so that in the interview, you can write it under 60 seconds without thinking about the mechanics. So that frees up your mental energy for the more harder problem coming up in the interviews. So in theory, binary search is not that difficult of a problem, and it's like pretty easy algorithm to describe. But it gets pretty hard to implement, and a lot of people make mistakes during interviews. The concept is simple: check the middle, go left or right. But the implementation has traps that catch even experienced engineers. The bugs fall into 3 categories, and understanding why they happen is more useful than just memorizing the fix. Now, the first category is infinite loops. And this happens when the boundary update does not shrink the search range by at least one element. The most common version of this bug is using left equals mid instead of left equals mid plus 1. When left and right are adjacent, say left is 3 and right is 4, mid computes to 3. If we set left to mid, left stays at 3. The range is still 3 to 4, mid is still 3, left stays at 3. The loop never terminates. The fix for this is pretty straightforward. So you always use left equals mid plus 1 when using the less than or equal loop condition. There is a version where right equals mid is correct, but only when paired with the strict less than loop condition and left equals mid plus 1. Mixing these conventions is where the bug comes from. Now the second category is off by one error in boundaries. This is returning left when the answers are right, or using less than or equal when the logic requires strict less than. These bugs produce answers that are off by one position, which means the algorithm terminates correctly but returns the wrong index. The third category is integer overflow, which we covered on the previous slide. Using left plus right instead of left plus right minus left can overflow in Java and C++. Now the root cause behind all three categories is the same: inconsistency in the loop variant. Binary search has two common conventions. One uses inclusive bounds with while left is less than or equal to right, updating left to mid plus 1 and right to mid minus 1. The other uses a half open range with while left is less than right, updating left to mid plus 1 and right to mid. Both are correct when applied consistently. The bugs appear when you mix elements from both conventions, so you use the loop condition from one and the boundary updates from the other, and then they conflict. Now the practical advice here is pretty simple. Pick one template and use it for every binary search problem. Do not try to remember multiple templates and choose between them during an interview. The template from the previous slide uses inclusive bounds with left equals mid plus 1 and right equals mid minus 1. It works for standard search. So for lower bound and upper bound, we'll learn a second template shortly, and that one also has a consistent internal convention. So 2 templates total, each internally consistent, is all you need. Now getting binary search right on the first attempt matters because debugging it under time pressure is extremely difficult. If your binary search enters infinite loop during an interview, the time you spend finding the bug is time you do not spend on the actual problem. Trace through concrete examples to see exactly how the correct template handles both success and failure cases, and then see how the wrong template breaks. First, the success case. We search for the value 5 in the array 1, 3, 5, 7, 9. So left starts at 0, right starts at 4, mid is 2. The element is at index 2 is 5, which equals the target. We return 2 immediately, found in one iteration, no boundary issues at all. Now the more interesting case. We search for the value 4 in the same array. The value 4 does not exist in the array, so the algorithm needs to correctly determine that and return -1. Left starts at 0 and right at 4, mid is 2. The element at index 2 is 5, which is greater than 4, so we set right to 1. Now left is 0, right is 1, mid is 0. The element at index 0 is 1, which is less than 4, so we set left to 1. Now left is 1, right is 1, and mid is 1. The element at index 1 is 3, which is less than 4, so we set left to 2. Now left is 2 and right is 1. Left is crossed right, so the loop exists and we return -1. The algorithm correctly identified that 4 is not in the array and it terminated in 3 iterations. Now let us see what happens with the wrong template. Same search for 4 in the same array, but this time we use left equals mid, instead of left equals mid plus 1. Now left starts at 0, right at 4, mid is 2. The element at index 2 is 5, greater than 4, so right becomes 1. Left is 0, right is 1, and mid is 0. The element at index 0 is 1, less than 4. But now we set left to mid, which is 0, so left was already 0, it stays at 0, right is still 1, mid is still 0. We set left to mid again, which is still 0. The range never shrinks, the loop runs forever. So this is not like a very uncommon edge case. This happens in a pretty common interview. So this exact scenario where left and right are adjacent and mid equals left happens in almost every binary search execution that reaches the end of the range. It is a normal path, not the exception. And this is something you should note down as well. Always use left equals mid plus 1 and right equals mid minus 1 with the while left is less than or equal to right loop condition. This combination guarantees the range shrinks by at least one element every iteration, which guarantees termination. With the templates mechanics sorted, let us move to the first variation, which is what happens when you are not searching for an exact target, but for a boundary. Sometimes the goal is not to find a specific target in a sorted array. Instead, you want to find where a target would be inserted to keep the array sorted. This is what lower bound and upper bound solve, and they are arguably very important in the interviews, and they actually appear much more than in interviews than the standard binary search. So lower bound, also called, let's say, bisect left in Python, finds the leftmost position where the target could be inserted while maintaining the sorted order. Another way to think about it, it finds the index of the first element that is greater than or equal to the target. If the target exists in the array, lower bound points to its first occurrence. If the target does not exist, it points to where the target would go. Now, upper bound is also called bisect right, finds the right insertion position. It returns the index of the first element that is strictly greater than the target. If the target exists, upper bound points to the position just after its last occurrence. The code for lower bound initializes left to 0 and right to the length of the array, not length minus 1. The loop runs while left is strictly, less than right, not less than or equal. Inside the loop, we compute the mid the same way. If the element at the mid is less than the target, we set left to mid plus 1. Otherwise, we set right to mid, not mid minus 1. The function returns left. Now, upper bound is pretty identical, so the only difference is the comparison. Instead of checking if the element at mid is less than the target, we check if it is less than or equal to the target. Everything else remains the same. Notice that this is a different template from the standard binary search on the previous slides. There are essentially two key differences. So the first is the right starts at the length of the array, not length minus 1. This allows the result to be the one past the last element, which is a valid insertion point. Second, the loop uses strict less than, and the right update is the right equals mid, not mid minus 1. This combination converges to a single point where left equals right, and that point is the answer. Now these two templates are the only two you need for all of the binary search patterns. So for example, the inclusive bounds template from the slide 61 for finding exact targets, and this half open template here for finding boundaries. Each is internally consistent, so please do not mix them. Now let us apply the standard template to the classic problem, which is LeetCode problem number 704, which is binary search. Now given a sorted array of integers and a target value, we have to return the index of the target if it exists. Otherwise, we have to return -1. So let's say you're given the array which is -1, 0, 3, 5, 9, 12, and the target is 9. Now the code is the exact template from slide 61. So the left here starts as 0 and right starts as 5. Now at first iteration, the mid is 2, the element at index is 2 is 3, which is less than 9. So left moves to 3. Now for second iteration, as you can see here, the mid is 4. Now the element at index 4 is 9, which equals the target, so we return 4. We have found this in 2 iterations. The maximum for an array of 6 elements would be log base 2 of 6, which is roughly 3 iterations. We got lucky and we just found in 2. Now let us trace through the failure case. Same array, but let's say the target is 2, which does not exist. Now the left starts at 0, right is at 5, mid is at 2. The element at index 2 is 3, so greater than 2, so right becomes 1. Now left is 0, right is 1, and mid is 0. The element at index 0 is -1 and less than 2, so left becomes 1. Now left is 1, right is 1, mid is 1, and the element at index 0 is 1 is 0, so which is less than 2, so left becomes 2. Now left is 2 and right is 1, so left has crossed right, loop exits, and return -1. So it correctly identifies the target is absent in 3 iterations. Now the problem is the simplest binary search question and is actually used quite a few times as a warm-up question in the interviews. However, the real test is not whether you can solve it, but whether you can write it correctly in less than 10 minutes, so that then you can move to harder problems in the interview. So if you write cleanly and quickly, it builds the confidence for the interviewer for the rest of the problem. And now let's move to the another variant that tests a deep understanding of binary search. So like for example, what happens when the sorted array has been rotated? So now this is LeetCode problem number 33, which is to search in a rotated sorted array. And it's also a very common LeetCode interview problem. So the setup for this problem is this. You have a sorted array that has been rotated at some unknown pivot point. For example, the array is given to you is 0, 1, 2, 4, 5, 6, 7, which might have become now after rotation as 4, 5, 6, 7, 0, 1, 2. Now given a target value, we have to find its index or return -1. The requirement for that is O of login time, which means linear scan is not acceptable. So we need to do binary search. The challenge is that the array is not fully sorted, so we cannot directly apply the standard template. But here's a key insight that makes this problem solvable. Even though the array is rotated, when you look at any position mid, at least one of those two halves, left of mid or right of mid, is guaranteed to be sorted. The rotation point is in one half, which means the other half is an unbroken sorted sequence. Now the algorithm works like this. You have to compute mid as usual. So if the element at mid equals the target, we return mid. Otherwise, we determine which half is sorted. If the element at left is less than or equal to the element at mid, the left half is sorted. Now you check if the target falls within the sorted range, meaning the target is greater than or equal to the element of the left and strictly less than the element at the mid. If it does, we search the left half by setting the right to mid minus 1. If it does not, we search the right half by setting left to mid plus 1. If the left half is not sorted, then the right half must be sorted. Now we apply the same logic in reverse. We check if the target falls in the sorted right half and search accordingly. Now the time complexity for this is O of log n because we still eliminate half the search space at each step. The space complexity for this is O of 1. Now this problem tests whether you can adapt the binary search to a structure that is not trivially sorted. The core binary search mechanics are the same. What changes is the decision logic for which half to search. Now let us trace through a concrete example to see exactly how the sorted half identification works. Now let us trace to the array 4, 5, 6, 7, 0, 1, 2, searching for, let's say, target 0. For the first iteration, left is 0, right is 6, so mid is 3. The element at mid is 7. So we check, is the element at the left, which is 4, less than or equal to the element at mid, which is 7? Yes. So the left half, the element 4, 5, 6, 7 is sorted. Now we check, is the target 0 within the sorted range? The sorted range goes from 4 to 7. The target 0 is not in that range. So we search the right half. Left becomes 4. Now for second iteration, left is 4, right is 6, mid is 5. The element at mid is 1. The element at left is 0. Now is 0 less than or equal to 1? Yes. So the left half, element 0 and 1 is sorted. Is the target 0 within the range 0 to 1? Yes. So 0 is greater than or equal to 0 and less than 1. So we search the left half, right becomes 4. Now for third iteration, left is 4, right is 4, mid is 4. The element at mid is 0, which equals the target, we return 4. The algorithm found the target in 3 iterations by correctly identifying which half was sorted at each step and determining whether the target could be in that sorted half. Now this is a common mistake on this problem that is worth addressing. When checking whether the left half is sorted, the condition should be less than or equal, not strictly less than. The difference matters when left equals mid, which happens when the range has exactly 2 elements. In that case, the element at left and the element at the mid are the same element. A single element is trivially sorted, so the left half is sorted. Using strict less than would incorrectly conclude that the left half is sorted, and the algorithm would make the wrong decision about which half to search. Now, when explaining this problem in an interview, it helps to think of this as a rotated array as 2 ascending segments placed end to end. Mid falls in one of the 2 segments. Whichever segment mid is in, the side is sorted. The other side contains a breakpoint and is not fully sorted. So this mental model makes this logic much easier to reason about. Okay, now let us talk about a closely related problem, which is instead of searching for a target in a rotated array, we work on finding the minimum element. Now this is LeetCode number problem 153, and it's a pretty commonly asked LeetCode interview problem as well. So for this, given a rotated sorted array with unique elements, we have to find the minimum element in O of log n time. So the minimum element sits at the rotation point. In the array 3, 4, 5, 1, 2, the minimum is 1, which is where the rotation happened. So the question now is, how do we use binary search to find the rotation point? The insight is to compare the element at mid with the element at the right. If the element at mid is greater than the element at the right, the rotation point and therefore the minimum is somewhere in the right half. Now let's think about it. In a properly sorted array, the middle element should be less than or equal to the rightmost element. If it is greater, the sorted order has been broken, which means the rotation point is between mid and right. So we set left to mid plus 1. If the element at mid is less than or equal to the element at the right half is probably sorted, which means the minimum is either at the mid or to the left of the mid. So we set right to mid, not mid minus 1, because mid itself could be the maximum minimum. Now the code initializes left to 0 and right to length minus 1. The loop uses strict less than, while left is less than right. And when the loop ends, left equals right, and that is the index of the minimum. Now let us trace through the array 3, 4, 5, and 2. Now left is 0, right is 4, mid is 2. The element index 2 is 5. The element index 4 is 2. 5 is greater than 2, so the minimum is in the right half. Now left becomes 3. Now left is 3, right is 4, mid is 3. The element index 3 is 1. The element index 4 is 2. 1 is less than or equal to 2, so the minimum is at mid or to the left. Now right becomes 3. Now left is equals right at index 3. The loop ends. The minimum is at index 3, which is 1. Now this is important design choice here that individuals will probe you on. So for example, why compare with the element at the right instead of the element at the left? The answer is that comparing with left is ambiguous when the array is not rotated at all. If the array is already fully sorted like 1, 2, 3, 4, 5, then the element at mid is always greater than or equal to the element at the left. The condition itself, which is element at mid is greater than or equal to element at the left, is always true, and the algorithm would never search the left half. It remains the minimum at index 0. So comparing with the element at right works correctly for both rotated and non-rotated arrays. So this problem tests the same, like the identify which half to search reasoning as a rotated array search, but with a different comparison target and different goal. Mastering both problems solidifies the pattern. Let's test what we have covered so far. Here are the 3 practice problems for you. For each one, identify which binary search variant applies before thinking about the answer. So for practice problem 1, let's say you're given a sorted array with possible duplicates. We have to find the first occurrence of a target value. Think about which variant is this. So this is a lower bound problem. We use the lower bound function from slide 63 to find the leftmost position where the target could be inserted. If the element at that position equals the target, that is the first occurrence. If it does not, the target is not in the array. The time complexity is O of log n. The key here is recognizing the standard binary search finds some occurrence of target, but not necessarily the first one. Lower bound specifically converges to the leftmost boundary. Now for practice problem 2, let's say you're given a sorted array. Count the number of times the target value appears. Which variant would that be? So this combines the lower bound upper bound the approach. The count is upper bound of the target minus lower bound of the target. Lower bound gives the index of the first occurrence. Upper bound gives the index just past the last occurrence. The difference is exactly the count. Both operations are O of log n, so the total is O of log n. This is significantly better than the O of n linear scan approach. Now let's talk about practice problem number 3. So for this, let's say you're given a sorted array of varying integers that has been rotated at an unknown pivot. You have to find the index of a given target or return -1. Now this is a rotated binary search from slide 65. At each step, determine which half is sorted by comparing the element at left with the element at the mid. Check if the target falls in the sorted half. If it does, search there. If not, search the other half. Time complexity for this is O of log n. The important takeaway from these 3 problems is this, that every one of them uses the same core binary search mechanics. The loop structure is the same, the mid calculation is the same. The only thing that changes is the comparison logic and the boundary update rule. Once you internalize the templates, adapting them to each variant becomes a matter of changing 1 or 2 lines of code. So these 3 problems represent the standard binary search variants. The next set of slides cover the more advanced and more interview critical pattern, which is binary search on the answer space. So this is a very important binary search pattern. In standard binary search, you search through an array to find a target element. In binary search on the answer, you're not searching through an array at all. You're searching through a space of possible answers. Here's the idea. Suppose the problem asks you, okay, what is the minimum possible value of x such that some constraint is satisfied? You know the answer must be somewhere in the range from low to high. And you can write a function that takes a candidate value and returns true or false, answering, okay, is this value feasible? If this feasibility function has a property that all values below the answer return false and all values at or above the answer return true, then the boundary between false and true is exactly the answer. Binary search finds this boundary in O of log high minus low iterations. Now think of it as a number line from low to high. On the left side, every candidate value is not feasible. On the right side, every candidate value is feasible. There's a single flip point where the function transitions from false to true. Binary search finds that flip point. The reason that this is so powerful is that because the brute force approach would try checking every possible answer from low to high, checking each one. That is O of high minus low time for time complexity. So binary search reduces it to O of log high minus low and calls it to feasibility function. So if the feasibility function itself takes O of n to evaluate, the total time becomes O of n times log high minus low. For practical values, that is dramatically faster than brute force approach. Here's a template. You initialize low to the minimum possible answer and high to the maximum possible answer. While low is less than high, you compute mid. If the feasibility function returns true for mid, set high to mid. Because mid might be the answer, but we want the smallest feasible value, so we search left. If feasibility returns false, we set low to mid plus 1 because mid is not feasible and neither is anything smaller. When the loop ends, low equals high, and that is the answer. The code is the same for every binary search or answer problem. What changes from problem to problem is the feasibility function and the search space bounds. The hard part is not writing the binary search. The hard part is recognizing that a problem can be solved this way in the first place. Once you see it, the implementation follows the formula. This leads to the natural question, which is, how do we know that binary search will produce the correct answer for a given feasibility function? That depends on the property called monotonicity. So we now have the template for binary search on an answer, but there is a question we have not addressed yet. How do we know that binary search will actually work on a given problem? The answer comes down to one property, which is monotonicity. For binary search on the answer space to produce a correct result, the feasibility function must be monotonic. That means there is a single point in the search range where the function flips from false to true or from true to false and never flips back. If the function oscillates, if it returns true and then false and then true again, binary search has no way to know which half of the range contains the answer. It could discard the wrong half and the result would be incorrect. The test for monotonicity is simple. You should ask one question, which is, if the candidate answer x satisfy the condition, will x plus 1 also satisfy the condition? Now if the answer is always yes, the predicate is monotonic and binary search applies. Now let us walk through how this applies to problems we will encounter. Take the Koko eating banana problem. The predicate asks, okay, can Koko eat all the bananas at speed x within the given number of hours? If she can finish at speed x, then she can definitely finish at speed x plus 1 because eating faster never makes things slower. The predicate is monotonic. Now consider the capacity to ship packages problem. The predicate asks, okay, can all packages be shipped within a minimum maximum capacity of x within the allowed number of days? If a ship of capacity x can deliver everything in time, then a ship of capacity x plus 1 can also do it because a larger ship fits at least as much per day. Again, that is monotonic. The split array largest sum problem works the same way. The predicate asks, okay, can the array be split into k subarrays where the largest subarray sum is at most x? A large allowed sum means each subarray can hold more elements, so fewer splits are needed. If x works, then x plus 1 also works. There is one subtlety worth noting. So some problems search for the maximum instead of minimum. The magnetic force between balls problem asks for the largest minimum distance between the balls. Here is the predicate flips in the other direction. If a minimum distance is achievable, then a smaller distance x minus 1 is also achievable because placing balls further apart is harder, not easier. The monotonicity still holds, but the direction of search reverses. Instead of finding the first true, we find the last true. Now, regardless of the direction, every binary search on answer problem follows these three steps. First, we define the search space. What is the range of possible answers? That gives us the low and high. Second, we write the feasibility function. Given a candidate answer, can the constraint be satisfied? Third, we verify the monotonicity. Confirm that if candidate X works, then X plus 1 or X minus 1 also works, depending on the direction. Now this you should something note down, which is these three steps are the complete framework for binary search and answer problems. Every single problem in this category follows these three steps with no exceptions. In an interview, stating these three steps out loud before writing any code shows the interviewer that you have a systematic approach. You are not guessing and you are not pattern matching from a memorized solution. You are applying a framework, and that is exactly what interviewers at senior levels would want to see. And this framework is what makes the next two problem walkthroughs almost mechanical. Once you identify the search space, write the feasibility function, and confirm the monotonicity, the binary search code itself is identical every time. So let us apply it to the most commonly asked problem in this category. So this is LeetCode problem number 875, which is Koko eating bananas problem. Now here is the problem. Koko has n piles of bananas. She eats at speed of k bananas per hour. Each hour she picks one pile and eats k bananas from it. If the pile has fewer than k bananas remaining, she eats what is left and waits until the next hour. She has h hours total. So now the question is, what is the minimum integer speed k such that she can eat all bananas within h hours? Now let us apply the three-step framework we just discussed. Step 1, we define the search space. So the minimum possible speed is 1, eating one banana per hour. She will always eventually finish, but it just might take a very long time. The maximum useful speed is the size of largest pile. Eating faster than the largest pile does not help, because once she finishes the pile, she waits until the next hour regardless. So the search range is 1 to maximum of piles. Now for the step 2, we have to write the feasibility function. Given a candidate of speed k, can Koko finish all the bananas within h hours? For each pile, we calculate how many hours it takes at speed k. That is the ceiling of pile size divided by k. We sum this across all piles to get the total hours needed. If the total is less than or equal to h, the speed is feasible. The ceiling division is computed as pile plus k minus 1 as integer divided by k. This avoids floating point arithmetic, which is important for correctness and is what interviewers would expect to see. Now step 3 is, we have already verified monotonicity in the previous slide. If speed x works, speed x plus 1 also works, because eating faster can only reduce the total time. The binary search code initializes low to 1 and high to the maximum pile size. While low is less than high, we compute mid. If the feasibility function returns true for mid, set high to mid. Otherwise, we set low to mid plus 1 and we return low. Now, the time complexity for this is O of n times log m, where n is the number of piles and m is the maximum pile size. Each iteration of the binary search calls for the feasibility function, which iterates through all n piles. The binary search runs for at most m iterations. The space complexity is O of 1. This problem is a very commonly asked binary search problem in interviews, so it is a perfect illustration of the pattern because now the feasibility function is simple, the monotonicity is obvious, and the search space bounds are straightforward. Now let us trace through the execution to see the binary search converge. Now let us trace through the full execution. So let's say the piles are 3, 6, 7, 11 and h is 8. The search space is low equals 1 and high equals 11. So the first iteration mid is 6 and at speed 6 the hours needed are ceiling of 3 divided by 6 is 1, ceiling of 6 divided by 6 is 1, ceiling of 7 divided by 6 is 2, ceiling of 11 divided by 6 is 2. Total is 6 hours. 6 is less than or equal to 8, so feasible. Set high to 6. Now for second iteration, low is 1, high is 6, mid is 3. At speed 3, ceiling of 3 over 3 is 1, ceiling of 6 over 3 is 2, ceiling of 7 over 3 is 3, and ceiling of 11 over 3 is 4. Total is 10. 10 is greater than 8, not feasible, so we set low to 4. Now for third iteration, low is 4, high is 6, mid is 5. At speed 5, ceiling of 3 over 5 is 1, ceiling of 6 over 5 is 2, ceiling of 7 over 5 is 2, and ceiling of 11 over 5 is 3. Total is 8. 8 is less than or equal to 8, feasible, so we set high to 5. Now fourth iteration, so low is 4, high is 5, and mid is 4. At speed 4, ceiling of 3 over 4 is 1, ceiling of 6 over 4 is 2, ceiling of 7 over 4 is 2, ceiling of 11 over 4 is 3, total is 8, feasible, set high to 4. Now low is 4, high is 4, loop ends, the answer is 4 bananas per hour. Now notice how the binary search tested only 4 values out of the 11 possible speeds. Brute force would have given you, tested for all 11. For larger inputs where the maximum file size is in the millions, the difference would have been enormous. Now there is a common mistake on this problem worth calling out. Some candidates, they set high to sum of all piles instead of the maximum pile. The sum of piles is a valid upper bound technically, since eating everything in 1 hour per banana would certainly finish in time. But it makes the search space unnecessarily large. The tightest upper bound is the maximum pile size because eating faster than the largest piles provide no benefit. Koko finishes the pile and wait. Following this in an interview, explain your search space bounds out loud. So you should be saying something like, okay, the minimum possible speed is 1 and the maximum useful speed is the size of the largest pile, so my search range is 1 to max of piles. Defining the search space correctly is the first thing interviewers evaluate. An incorrect or overly wide search space signals a shallow understanding of the problem. Now let us now apply the same framework to a second problem to reinforce the pattern. So this is LeetCode problem 1011. So capacity to ship packages within D days. Packages on a conveyor belt have weights. A ship loads packages in order left to right and you cannot reorder them. The ship has a weight capacity. Each day it loads consecutive packages until the next package would exceed the capacity, then it sails. So now the question is, what is the minimum ship capacity to deliver all the packages within the allowed number of days? Now the input is weights equal, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and days is equal 5. Now for step 1, we define the search space. The minimum possible capacity is the weight of the heaviest single package. If the ship cannot carry the heaviest package, it can never deliver everything. The maximum capacity is the sum of all weights, which would mean shipping everything in a single day. So low equals max of weights, high equals sum of weights. Now for step 2, we write the feasibility function. So given a candidate capacity, can all packages be shipped within the allowed days? We simulate the loading process, start with the day 1 and an empty ship. We walk through the weights in order. If adding the next package would exceed the capacity, we start a new day and reset the current load to 0. We add the package to the current day's load. At the end, if the number of days needed is less than or equal to the allowed days, the capacity is feasible. Now for step 3, which is monotonicity. If a ship of capacity X can deliver everything in time, a ship of capacity X plus 1 can also do it. A larger ship fits at least as much as cargo per day, so it needs the same number of days or fewer. The predicate is monotonic. Now the binary search code is identical to the Koko problem, only the feasibility function and the bounds change. Now let us trace through the key iterations. So low is 10, high is 55, mid is 32. With capacity 32, only 2 days are needed. Feasible, so high becomes 32. Mid is 21, with capacity 21, 3 days are needed. So feasible, high becomes 21. Mid is 15. With capacity 15, 5 days are needed, which equals the limit. Feasible, high becomes 15. Mid is 12. With capacity 12, 6 days are needed, which exceeds 5. Not feasible, low becomes 13. Mid is 14. Still 6 days are needed. Not feasible, low becomes 15. Low equals high at 15. The answer is 15. Now the time complexity for this is O of n times log s, where n is the number of packages and s is the sum of all weights. The space complexity is O of 1. Now the structural similarity to Koko eating bananas is intentional. The binary search framework is identical. The feasibility function changes. The search bounds change, but the pattern is the same. Recognizing this in an interview is pretty valuable. So if you have solved one binary search and answer problem, you can explain this to the interviewer. This follows the same pattern as the Koko eating bananas. I will define the search for space, write the feasibility function, verify the monotonicity, and apply the same binary search template. That kind of pattern level reasoning is exactly what the interviewers are looking for. Now that we have seen the pattern apply to two problems, let us step back and talk about how to recognize when binary search is the right approach in the first place. So one of the hardest things about binary search in interviews is not the implementation, it's recognizing that binary search applies at all. Especially for binary search in the answer space, the problems often do not mention sorting or searching. They look like optimization problems, so the recognition has to come from the structure of the problem, not the keywords. Now, here are the signals to look for. If the problem gives you a sorted array and asks you to find a target, that is a standard binary search. If the problem gives a sorted array and asks for the insertion point or the first element meeting some condition, that is a lower bound or upper bound. If the array is sorted but has been rotated at an unknown point, that is a rotated binary search. If the problem asks you, okay, what is the minimum x such that the condition is met, that is binary search on the answer space. Similarly, if it asks, okay, what is the maximum y such that the condition holds, that is also binary search on answer, just searching in the other direction. If the problem explicitly says, okay, can you do this in O of log n, it is almost certainly binary search. And if there is a monotonic function with a clear boundary, binary search on that boundary is the approach. Now, equally important is knowing when binary search does not apply. So, if the array is unsorted and there is no ordering property, you cannot eliminate half the search space. You use a hash map, sorting, or linear scan instead. If the problem needs all elements that match a condition, not just one boundary point, binary search alone is not enough. You might need a linear scan or a combination of lower bound and upper bound to define the range. If the feasibility function is non-monotonic, meaning it oscillates between true and false, binary search cannot guarantee it finds the current boundary. You need brute force or a different approach entirely. So, and if the problem requires O of one time rather than O of log n, a hash map for constant time lookup is a better tool. Now, there is a useful pattern in how interviewers hint at binary search. When they say something like, okay, the brute force is O of n, can you do better? And the problem involves searching, the answer is almost always binary search for O of log n. When they say, okay, the brute force tries all values from 1 to max, can you do better? The answer is binary search on the answer space. Now, these recognition signals covers roughly 95% of binary search interview problems. The hardest part is not writing the binary search itself. It is seeing that binary search is the right tool before you start coding. Now, let us consolidate the most common mistakes engineers make on binary search problems and interviews. Knowing these in advance means you can avoid them systematically. Now, the first mistake is using left equals mid when the while left is less than or equal to the right loop condition. We trace through exactly why this causes infinite loops on slide 62b. Lefts get stuck at mid when they're equal, the range never shrinks, and the loop runs forever. The fix is to use left equals mid plus 1 with the less than or equal condition. The second mistake is computing mid as left plus right divided by 2 in Java or C++. When left and right are both large values, the sum overflows a 32-bit integer range. Use left plus right minus left divided by 2 instead. Making this a habit in every language, even Python, where it is technically unnecessary. The third mistake is setting wrong search space bounds for binary search or answer. If low or high is wrong, the binary search either misses the correct answer or searches an unnecessarily large range. In Koko eating bananas problem, setting high to the sum of piles instead of the max pile makes the search space much wider than needed. The fix is to think carefully about the minimum and the maximum possible answers and state them out loud before writing the code. The fourth mistake is writing feasibility function, and that is not monotonic. If the function returns true, then false, then true again as the candidate value increases, binary search will convert to the wrong answer. Before coding, explicitly verify if x works, does x plus 1 also work? If the answer is not always yes, binary search on answer is the wrong tool for the problem. The fifth mistake is specific to the find minimum rotated array problem. Many candidates compare the element at mid with the element at left instead of the element at the right. This fails the non-rotated arrays, which are already fully sorted. We cover the reason on slide 66, which is to comparing with the left element is ambiguous when no rotation exists. Now, if you have already written the binary search and the result is wrong, there is a predictable debugging flow. If the answer is off by 1, check the boundary updates. Are you using mid plus 1 and mid minus 1 consistently? If the loop never terminates, check that the range shrinks every iteration. Print left and right at each step and verify that the distance between them decreases. If the answer is completely wrong, not just off by 1, check that feasibility function is actually monotonic. So these 5 mistakes account for majority of binary search failures and interviews. Eliminating them makes the entire category of problems pretty reliable. Here is a reference sheet for this entire section. The slide is designed to be, quickly reviewed before the interviews and to essentially capture all the concepts in the section. So let us walk through each template. Standard binary search for finding an exact target. Left starts with 0, right starts with -1. Loop while left is less than or equal to the right. Compute mid. If the element in mid is equals the target, return mid. If it is less than the target, set left to mid plus 1. Otherwise, set right to mid -1. Return the -1 if not found. Time complexity is of log n. Space is of 1. Now for the lower bound, which finds the first element greater than or equal to the target. Left starts with 0, right starts with n, not n minus 1. Loop while left is strictly less than right. If the element in mid is less than the target, set left to mid plus 1. Otherwise, set right to mid, return left. For this, time complexity is of log n, space is of 1. Upper bound is the same template, but the condition changes to less than or equal instead of strictly less than. Binary search on the answer space for finding the minimum feasible value. Now, for low starts with the minimally possible answer and high at the maximum possible answer. Loop while low is less than high. Compute mid. If the feasibility function returns true, set high to mid. Otherwise, set low to mid plus 1. Return low. Time is O of n times log m, where m is the answer age because each iteration calls a feasibility function which typically takes O of n times space is O of 1. The next is rotated array search. At each step, check if the left half is sorted by comparing the left element at the left with the element at the mid. If it is sorted, check if the target falls in that sorted range. If it does, search left. If it not, search right. If the left half is not sorted, the right half must be, and apply the same logic in reverse. Now, find minimum in the rotated array. So for this, you compare the element at the mid with the element at the right. If mid is greater than right, the minimum is in the right half. Set left to mid plus 1. Otherwise, the minimum is at the mid or to the left. Set right to mid. Loop ends when the left equals right. Now the key thing to notice across all 5 templates is that the complexities are identical. Every single pattern here runs in O of log n time complexity and O of 1 space complexity. The exception is binary search on answer, which has a feasibility function cost multiplied in. Stating this correctly in an interview, saying that okay, the binary search is of log m iterations, each calling the feasibility function O of n time for a total of O n log m. When you say this statement in the interview, it shows the interviewer that you understand both components, not just the binary search part. So let us summarize what we have covered in this section and connect it to what comes next. We start with the standard binary search template, a bug-free implementation that uses inclusive bounds and guarantees termination by shrinking the range by at least 1 element per iteration. We examined why binary search bugs happen and traced with concrete examples showing how the wrong boundary update leads to infinite loops. We then learned lower bound and upper bound, which find insertion points rather than exact targets. These use a different template with strict less than and in the loop condition and right equals mid in the update, converging to the boundary point where a left equals right. Rotated array problems gave us practice adapting the binary search to non-trivially sorted structures. The key insight is that one half is always sorted, and we determine which half to search by checking where the target falls relative to the sorted half. Now find minimum in the rotated sorted array taught us to compare with the right element, not the left, to handle the non-related edge case correctly. Next, for binary search on the answer space was a very important pattern for this section. Instead of searching through an array, we search through the range of possible answers, using a feasibility function to determine whether a candidate answer is viable. The monotonic predictable framework gives us a systematic free 3-step approach. We define the search space, write the feasibility function, verify the monotonicity. Now, looking at how this section connects to the rest of the course, the binary search principle of eliminating half the search space at each step that reappears in section 7 where binary search tree search follows the same left and right elimination logic. Binary search on the answer space shows up again in section 11, where some dynamic programming optimization problems use binary search to reduce state transitions. The monotonic reasoning we developed here connects to section 4, where monotonic stacks use a similar invariant to justify correctness. And the login search principle is the same search reason a heap operation in section 9 over login. Both are eliminating half the possibilities at each level. In the next section, we move to the linked list patterns. So binary search works on arrays because we can jump to any index at one time. Linked lists, they do not support random access. You can only move from one node to the next. This constraint changes which operation is efficient and makes pointer manipulation the central skill. This is a fundamentally different way of thinking about data structure problems. Now, combined with the array, sliding window, and the prefix sum patterns from earlier sections, binary search completes the toolkit for array-based interview problems. Roughly 10% to 15% medium or hard LeetCode interview questions are binary search problems, and about half of those use a binary search on the answer pattern. That is a significant portion of the interview landscape covered by the 6 templates on the reference cheat sheet slide. So now let's move to the next section, which is focused on linked list patterns. We are now moving into linked list patterns, and this is a section where the mindset shift matters more than the complexity of the problems. If you have been working through the array sections, you have built strong instincts around random access, index arithmetic, and sliding windows. Linked list throws all of that away, and it's a different approach. There is no jumping to index I to n over 1. There is no binary search. There is no swapping elements at 2 positions. The only thing you can do is follow a pointer from one node to the next. That constant constraint changes actually what techniques are available to you. Instead of index manipulation, the core skill becomes pointer manipulation. Every linked list problem at its heart is about rewiring the .next references. You are changing which node points to which other node, and the hard part is doing that without losing track of nodes along the way. Now, the encouraging thing about this section is that linked list problems draw from a very small pool of techniques. They are really just 4 core patterns that cover nearly every linked list question you'll face. The first is a dummy node pattern, which simplifies edge cases when the head of the list might change. The second is the first fast and slow pointer technique, which lets you find positions like the middle of the list or detect cycles without knowing that list length. The third is in the in-place reversal pattern, which rewires the nodes to the reverse of all or the part of the list. And the fourth is the merge pattern, which combines 2 sorted lists into one. We'll also cover the 2-pointer gap technique, which is a variation of fast and slow pointers used to find or remove nodes relative to the end of the list. Now, in terms of where these show up in the interviews, linked list problems actually, they're very consistent across company types. At large tech companies, problems like reverse linked list, merge case sorted list, and reorder list appear frequently at medium difficulty level questions. At medium-sized companies, cycle detection and basic reversal are common in phone screens. Startups test them less often, but they do appear when the interviewer wants to evaluate pointer manipulation skills directly. In online assessments, linked list problems are less common than arrays, but they did still show up as one question, among several one of them. Now, the core ideas to carry through this section is this. Linked list problems are pointer manipulation problems. The algorithm is almost never the hard part. The hard part is preserving references before you rewrite nodes. The first pattern in our toolkit is a dummy node, and it solves a problem that trips so many candidates in interviews. So what happens when the operation changes the head of the list? Think about it this way. If you're removing nodes from a linked list and the very first node needs to be removed, the head pointer itself has to change. Without a dummy node, you need special logic to handle that case separately from removing any other node. You end up writing one block of code for the head case and another block for everything else. Under interview pressure, this is exactly where the bugs creep in. A dummy node eliminates this problem entirely. The idea is simple. Before you start any operation, you create a fake node and set its .next pointer to a real head. This dummy node is never part of the actual data. It just sits in front of the list as an anchor. You do all your work related to the dummy, and at the end, you return dummy.next as the real head. Because the dummy is always there, the head is never a special case. Whether you remove the first node, the last node, or any node in between, the same logic, handles all of them. Now, the code on the slide shows this with the remove elements function. You create a dummy node which is list node, point it to the head, and then you walk through the list with the current pointer starting at the dummy. For each node, you check if the current.next has a value to remove. If it does, you skip it by setting current.next to current.next.next. If it does not, then you advance the current forward. At the end, dummy.next gives you the correct head even if the original head was removed. Now, without the dummy node, you would need a separate while loop at the beginning to handle cases where the head itself needs removal. Then you would need the main loop for the rest, so that is 2 loops instead of 1 with different logic in each. The dummy node collapses both into a single clean loop. Now, there are 4 main scenarios where a dummy node helps. When removing nodes from the list, the head might be removed. When merging 2 sorted lists, the new head is unknown until the first comparison. When partitioning a list into 2 sublists, you are building both from scratch. And when inserting at the beginning, the insertion point might be before the current head. In all 4 cases, the dummy node removes ambiguity about what the head will be. And here's something important for interviews. Interviewers do not give extra credit for solving a problem without a dummy node. What they do notice is when a candidate introduces head-related bugs by trying to avoid one. The dummy node is a reliability tool. It costs 1 line of code to create, and it eliminates the entire category of errors. So when you start any linked list problem, you should be asking yourself, can the head change? If the answer is yes, you have to create the dummy node immediately. Now that we have the dummy node in our toolkit for handling head edge cases, let's talk about a different kind of challenge. What if you need to find the middle of a linked list, or detect whether the list has a cycle, or find a node at a specific position relative to the end? In an array, these are trivial. You know the length, so you compute the index. But a linked list, you do not know the length unless you traverse the entire linked list first. And even if you do traverse once to count, you then need a second traversal to reach the position. So that is 2 passes. The fast and slow pointer technique gives you a way to solve these problems in a single pass. So the idea is pretty elegant. You set up 2 pointers, both static at the end. The slow pointer moves 1 step at a time. The fast pointer moves 2 steps at a time. Because the fast pointer covers ground at double the speed, when the fast pointer reaches the end of the list, the slow pointer is exactly at the middle. It is like 2 runners on a track where one runs twice as fast. When the faster runner finishes the lap, the slower runner is at the halfway point. Now the find middle function in the code over here, it shows us that both slow and fast start at the head. The loop continues as long as the fast is not null and fast.next is not null. Inside the loop, slow advances by 1 node and fast advances by 2. When the loop exits, slow is sitting on the middle node. For a list with an even number of nodes, this gives you the second of the 2 middle nodes. The same 2-pointer idea, it powers cycle detection, which is known as the Floyd's algorithm. The setup is pretty identical. Slow moves 1 step, fast moves 2 steps. The key insight is this. If there is no cycle, fast will hit null and the loop ends. But if there is a cycle, fast will loop around and eventually catch up to slow from behind. They will land on the same node, and that meeting point proves the cycle exists. Now the loop condition is critical here, and it's a common source of bugs. It must be while fast and fast.next in exactly that order. The check on fast must come from before the check on fast.next. If fast is null and you try to access fast.next, that is a null reference error. Python short circuits the evaluation, so it is fast. So if fast is null, it never checks the fast.next. Getting this order wrong is one of the most common mistakes in the linked list interviews. Now the fast and slow pointer technique has 4 main applications. For finding the middle, fast moves at 2 times the speed and slow lands on the middle node. For detecting a cycle, fast moves at 2 times the speed, and if a cycle exists, slow and fast meet inside the cycle. For finding the start of a cycle, you reset one pointer to the head after the meeting point and move both at 1x speed. They meet at the cycle starting node. And for finding the nth node from the end, you give fast a head start on if n steps, and then move both at 1x speed. When fast hits the end, slow is at the target. Now if this technique feels familiar from the array section, it should, because fast and slow pointers in linked list are the equivalent of the two-pointer technique on arrays we covered in section 3. It is the same core idea of two references moving at different speeds or with a fixed gap adapted to a data structure that only allows sequential access. So let us put Floyd's algorithm into practice with one of the very commonly asked questions, which is linked list cycle LeetCode number problem 141. So the problem gives you the head of a linked list and asks you to determine whether the list contains a cycle. A cycle exists when some nodes on .next pointer points back to a previously visited node, creating a loop. Now the solution uses exactly the fast and slow pointer setup that we just discussed. So both pointers start at the head, slow advances one step, fast advances 2 steps. After each move, we check if the slow and fast are pointing to the same node. If they are, a cycle exists and we return true. If fast reaches null, the list has a definite end, so there is no cycle and we return false. Now let us trace through the list and to see that which has a cycle or not. Imagine that the list is 1, 2, 3, 4, where node 4's .next pointer points back to node 2. At step 0, both slow and fast are at node 1. At step 1, slow moves to node 2 and fast moves to node 3. At step 2, slow moves to node 3 and fast, having gone to 2 steps from node 3, loops through node 4 back to node 2. Now at step 3, slow moves to node 4 and fast, moving 2 steps from node 2, goes to node 3 and then node 4. Slow and fast are now both at node 4. They are equal, so we return true. Now let us trace a list without a cycle. So for example, we have a list of 1, 2, 3, none. And at step 0, both are at node 1. At step 1, slow is at node 2 and fast is at node 3. At step 2, fast.next is none, so while collection fails and we exit the loop. Now we return false. The list has a definitive end, so there is no cycle. Now there is an alternative approach that uses hash set. You store every node you visit, and if you encounter a node you have already seen, there is a cycle. This works correctly, but it uses of and space complexity to store all the visited nodes. Now Floyd's algorithm achieves the same result with of on space, just 2 pointers, no extra data structures. So this space difference is almost always a follow-up question interviewers ask. They want to see if you can improve from the hash set approach to the constant space approach. Now one important detail to keep in mind is that the order of operations inside the loop matters. You should advance the pointers first, then check for equality. If you check for equality at the start of the loop before moving, slow and fast are both at the head, and you would incorrectly return true on every input. So this problem is a strong foundation for a common medium level follow-up, which is linked list cycle 2, LeetCode number problem 142. And that it is asked that okay, you have to find where the cycle starts, not just where one exists. So that problem uses the same fast and slow pointer direction plus an additional pointer starting from the head that advances in sync with one of the meeting point pointers until they converge as a cycle's entry. So we have covered how to handle head edge cases with dummy nodes and how to find positions in a linked list with fast and slow pointers. Now let's talk about the single most fundamental linked list operation, which is reversal. Now the recognition signal for this is pretty straightforward. Anytime the problem asks you to reverse a linked list or reverse a portion of it, you need this pattern. Reversal means changing the direction of .next pointer so that each node points to its predecessor, instead of its successor. The core challenge with reversal is something that does not exist in array problems. In an array, if you swap two elements, both values are preserved because the array holds them in fixed positions. In a linked list, the only way to reach the next node is through the .next pointer. The moment you change current .next to point backward, you have lost your forward reference. If you did not save it, you cannot advance to the next node. So now the linked list is broken. This is why the pattern is called the 3-variable dance. At every step in the reversal, you maintain exactly 3 references. The previous variable holds the node that current one should now point to. The current variable is a node being processed right now, and the next underscore node is the original next node saved before you do any rewiring. The process at each step follows a strict order. First, save. Store the current.next in next underscore node so you do not lose the reference. Second, rewire. Set the current.next to previous, which reverses this one link. Third, advance. You move the previous to current and current to next underscore node, setting up for the next iteration. Now the function starts with the previous set to none and current set to the head. The loop runs as long as the current is not null. Inside each iteration, you save, rewire, and advance. When the loop ends, current is none and previous is pointing to the last node you processed, which is the new head of the reverse list. You return previous. Now this runs in O(n) time complexity because you visit each node exactly once. It uses O(1) space complexity because you only maintain 3 pointers regardless of the list length. Now reversing a linked list is not just a standalone problem. It obeys as a subroutine in at least 5 of the linked list problems. For example, reverse linked list about part 2, which reverses the subrange. Palindrome linked list, which reverses half the list to compare. Reorder list, which reverses the second half, then merges. Reverse nodes in K group, which reverses in chunks, and add to numbers variations. So now, mastering the reversal pattern will actually give you a building block that you will reuse across many problems. Let's trace through the reversal on a concrete example. This reverse linked list problem, which is LeetCode number 206, and one of the very commonly asked problems. Now, the input is 1, 2, let's say 1, 2, 3, 4, 5, and the expected output for that would be 5, 4, 3, 2, 1. Now the function is the same 3-variable dance. Previous starts at none, current starts at node 1. At step 0, as you can see, as we are tracing this problem now. So at step 0, the current is node 1. We save next underscore node as node 2. We rewire the node once dot next to point to none, which is previous. Then we advance. Previous becomes node 1, current becomes node 2. At step 1, current is node 2. We save next node as node 3. We rewire nodes 2 dot next to point to node 1, which is previous. Then we advance. Previous becomes node 2, current becomes node 3. At step 2, current is node 3. We save next underscore node as node 4. We rewire node 3's dot next to point to node 2. Then we advance. Previous becomes node 3 and current becomes node 4. At step 3, current is node 4. We save next underscore node as node 5. We rewire the node 4's dot next to point to node 3, and then we advance. Previous becomes node 4 and current becomes node 5. At step 4, current is node 5. We save next underscore node as none. We rewire node 5's dot next to point to node 4, and then we advance. Previous becomes node 5. Current becomes none. Current is now none, so the loop exits. We return the previous, which is node 5, and node 5 now points to 4, which points to 3, which points to 2, which points to 1, which points to none. So the list is fully reversed. Now there is a common mistake here that catches many candidates. So after the loop, the variable head still points to node 1, but node 1 is now the tail of the reverse list. If you return head instead of previous, you're returning the tail, not the new head. So the new head is always the previous after the reverse loop completes. This is a simple but costly mistake in an interview setting. Being able to rewrite this function from memory in under 3 minutes is expected at pretty much every interview level. So it is fundamental that interviewer you treat it as a baseline fluency check. If they see a candidate struggling with basic reversal or linked lists, unfortunately it signals to them that more complex linked list problems will be out of reach as well. So please make sure that before going to interviews you have understood and mastered this pattern quite well. Now this slide gives you the visual representation of what happens at each step of the reversal, and is worth spending time on because this is exactly the kind of diagram you should be able to draw on a whiteboard during an interview. At the initial state, you have none followed by nodes 1, 2, 3, or 5, all pointing forward to none at the end. Previous is set to none and current is at node 1. After step 0, node 1's dot next has been rewired to point to none. The forward chain is broken between node 1 and node 2. But that is safe because we saved node 2 and node next underscore node before we did the rewire. Now previous is at node 1, current is at node 2. You can see two separate chains forming. A reverse chain on the left and the remaining forward chain on the right. After step 1, and what we do is that node 2's dot next now points to node 1. So reverse chain is now none, 1, 2, and 2 going backward, and the forward chain is 3, 4, 5. Now the pattern continues at each step. The reverse chain grows by one node from the right side, and the forward chain shrinks by one node from the left side. After step 4, the entire list has been reversed. Essentially, the current is none. So the critical discipline is, okay, save before you rewire. At step 0, before setting node 1's dot next to none, you must store node 2 in the next node. If you rewire first and then try to save, node 2 is already unreachable. You have no way to get it to it, so make sure you do that. The node is not deleted from the memory, but you have lost every reference to it, so for your purposes, it is essentially gone. Now this is the single most important habit in all of linked list manipulation, that you keep track of the references. Now the slide also shows here a recursive alternative. The recursive version calls itself on head.next to reverse everything from the second node onward. Then it takes the current head and makes it the tail of the reverse sublist by setting head.next to head and head.next to none. It returns the new underscore head, which propagates back from the base case. Now the recursive version is elegant and worth knowing, but it uses often call stack space because due to the recursive depth. Most interviewers prefer the iterative version because it runs off one space. However, being able to explain both shows versatility and a deeper understanding of the reversal mechanics. Now the whole idea is this: at every step you are peeling one node off the front of the remaining list and attaching to the back of the reverse list. Save, rewire, advance. 3 operations, 3 variables, repeated until the list is fully reversed. This leads us directly to the fourth core pattern, which is merging. The merge pattern applies when the problem asks you to combine 2 sorted linked lists into a single linked list, or more generally to interleave or recombine lists in a specific order. The technique builds on the dummy node pattern from slide 77. You create a dummy node to serve as the starting point of the merged list. Then you maintain a current pointer that tracks where the next node should be attached. You compare the heads of both input lists, attach the smaller one to the current.next, advance that input list pointer, and advance the current. You repeat this until one of the lists is exhausted. The code here creates a dummy list node and set current to it. The while loop runs as long as both list 1 and list 2 have remaining nodes. Inside the loop, you compare list1.val and list2.val. If list 1's value is less than or equal to list 2's value, you attach list 1's current node to the merged list and advance list 1. Otherwise, you attach list 2's current node and advance list 2. After the loop, one list has remaining nodes. Since those nodes are already sorted, you attach the entire remaining list in one step with current.next equals list 1 if list 1 still has nodes, otherwise list 2. Finally, you return dummy.next, which is the head of the merged list. Now this runs in O of n plus m time, where n and m are the lengths of the two lists. The space complexity is O of 1 because you're reusing the existing nodes. The only new allocation is the dummy node. The dummy node is essentially here, and that is a great example of why. The first node of the merged list depends on which input list has a smaller head value. Without a dummy, you would need an if statement before the loop to determine the head, and then the loop logic would need to account for the fact that the first attachment is already done. The dummy node lets you treat every attachment, including the first one, identical inside a single loop. One pattern and no special cases. Now this merge function is not just a standalone problem, it is a fundamental building block for merge case sorted list problem, which you will encounter in section 9. That problem uses a heap to efficiently select the smallest head among k list, but the underlying attachment logic is the same merge pattern you are learning here. Understanding this two list merge deeply makes the k-list generalization down in the future section much more easier to understand and implement. Now let us walk through merge to sorted list problem, which is LeetCode number 21 with a concrete trace. Let's say the inputs are list 1 with nodes 1 through 4 and list 2 with nodes 1, 3, 4. Now the expected output for this would be 1, 1, 2, 3, 4, 4. So we start with a dummy node pointing to none and current pointing to dummy. Now at step 1, list head's head is 1 and list 2's head is 1. Since 1 is less than or equal to 1, we attach list 1's node 1 to the merged list. The merged list is now dummy pointing to 1. List 1 advances to node 2, current moves to node 1. At step 2, list 1's head is 2 and list 2's head is 1. Since 2 is greater than 1, we attach list 2's node 1. The merged list is a dummy, so 1, and then after that, list 2 advances to node 3, current moves to the second one. At step 3, list 1's head is 2 and list 2's head is 3. Since 2 is less than or equal to 3, we attach list 1's node 2. The merged list is dummy 1, 1, 2. List 1 advanced to node 4, current moves to node 2. Now at step 4, list 1's head is 4 and list 2's head is 3. Since 4 is greater than 3, we dash list 2's node 3. The merged list grows to dummy 1, 1, 2, 3. List 2 advances to node 4. At step 5, list 1's head is 4 and list 2's head is 4. Since 4 is less than or equal to 4, we attach list 1's node 4. List 1 becomes none. Now list 1 is exhausted, so the while loop exits. List 2 still has a node 4 remaining. We dash it with the current.next equal to list 2. The file merged list becomes 1, 1, 2, 3, 4, 4, which matches the expected output. Now a common mistake with this problem is creating new nodes instead of reusing existing ones. The problem specifically asks you to splice the original nodes together. If you create new list node objects and copy values into them, you are using O of n plus m extra space complexity unnecessarily. Interviewers expect you to rewire the .next pointers on the original nodes. And here's a detail that is easy to forget. The tail attachment after the loop. The line current.next equals list 1 if list 1 else list 2 handles the case where one list still has remaining nodes. Since both input lists are already sorted, the remaining nodes are guaranteed to be in order and can be attached as a single chain. If you forget this line, the merged list gets truncated and you will lose nodes. It is a small line of code, but omitting it is a pretty common error. Now this problem is foundational. It is a prerequisite for merge sort on linked list, where you recursively split the list, sort each half, and merge them back together. It is also the prerequisite for merge k sorted list, which generalizes this to k input list using a heap. Both are common follow-up questions. So we have covered 4 patterns: dummy nodes, fast and slow pointers, reversal, and merging. Now let's look at a problem that combines 2 of these patterns into a single solution. So this is a problem called remove nth node from the end of the list, which is LeetCode problem number 19. It asks you to remove the nth node from the end of the list and return the head all in one pass. Now the challenge is that you do not know the list length. In an array, removing the nth element from the end is trivial because you can just compute the index. In a linked list, if you want to do it in one pass, you will need a way to identify the position without counting the total length first. Now this is where the 2-pointer gap technique comes in. The idea is to create a fixed gap of n nodes between 2 pointers. You advance the fast pointer n plus 1 steps from the dummy node first. Then you move both slow and fast one step at a time. When fast reaches none, slow is sitting exactly one node before the target node. You then skip the target by setting slow.next to slow.next.next. Now let us trace through the example. Let's say the input is 1, 2, 3, 4, 5 and n is 2. Now, meaning that we need to remove the second node from the end, which is node 4. We create a dummy node pointing to the head, and both slow and fast start at the dummy. First we advance fast by n plus 1, which is 3 steps. After 3 steps from the dummy, fast is node 3. Slow is still at the dummy. Now we move both pointers one step at a time. Slow moves to node 1, fast moves to node 4. Then slow moves to node 2, fast moves to node 5. Then slow moves to node 3, fast moves to none. The loop ends. Now slow is at node 3, which is one node before our target, node 4. We set slow next to slow.next.next, which skips node 4 and connects node 3 directly to node 5. The result now is 1, 2, 3, 5. The question that usually comes up here is that, okay, why n plus 1 steps instead of n? The reason is that we want slow to land on the node before the target, not on the target itself. We need the node before the target so we can rewire its next pointer. If we only moved fast by n steps, slow would land on the target itself, and in a singly linked list, we cannot go backward to rewire the previous node's pointer. The dummy node plays a critical role here too. So for example, consider the edge cases where the list has only one node and n is 1. The head itself is a node to remove. Without a dummy node, you will need special logic to handle this case. With a dummy node, the algorithm works exactly the same. Slow lands on the dummy and slow.next get rewired to skip the head. The dummy node and the 2-pointer gap work together to handle every case uniformly. Now this problem is a strong example of how interviewers test you whether you can combine multiple techniques cleanly. The dummy node handles the edge case, and the two-pointer gap handles the position logic, all in a single pass without knowing the list depth. So let us test what we have covered so far with 3 problems that are common in actual interviews. For each one, try to identify the patterns before reading the answer. So the first practice problem is palindrome linked list. Let's say given a linked list, determine that we have to know if it is a palindrome, of n time, of one space. Think about what patterns you would need. So the answer is that, okay, this problem requires combining 2 of our core patterns. First, we use fast and slow pointers to find the middle of the linked list. Once we have the middle, we reverse the second half of the linked list using the reversal pattern. Now you have 2 halves. So the first half still points forward from the head, and the second half points forward from the original tail. You walk both halves simultaneously, comparing values node by node. If every pair matches, the list is a palindrome. This runs in O of n time and O of one space because the reversal is done in place. Now the second practice problem is, which is a reorder list. Let's say you're given a linked list of 1, 2, 3, 4, 5. You have to reorder it to 1, 5, 2, 4, 3 in place. So think about how do you decompose this. So this is a 3 pattern combination. Step 1, we find the middle using fast and slow pointers. Step 2, we reverse the second half. Step 3, we merge the 2 halves by alternating nodes. After finding the middle of 1, 2, 3, 4, 5, you split into 1, 2, 3 and 4, 5. Then you reverse the second half to get 5, 4. Then you interleave. Take 1 from the first half, 1 from the reverse second half, 1 from the first, 1 from the second, and attaching the remaining node. The result becomes 1, 5, 2, 4, 3. So this combines all 3 of our core patterns in this section. Again, it takes O of n time and O of 1 space. The third practice problem is add 2 numbers problem. So 2 linked list here represent the non-negative integers stored in reverse order. You have to add them and return the sum as a linked list. Now this uses a merge pattern adapted for addition. You have to walk both lists simultaneously, adding corresponding digits along with the carry value. You have to use a dummy node to build the result list. At each step, the sum of 2 digits plus the carry gives a new digit and then the new carry. When one list is shorter, treat as missing digits as 0. After both lists are exhausted, if there is still carry, append one more node. This runs in O of max and m. So out of the n and m, what is the maximum? So O of that time. So now the key insight from these 3 practice problems is that most medium and hard linked list questions are not single pattern problems. They combine 2 or 3 patterns. Palindrome linked list combines fast and slow reversal. A reorder list combines fast and slow reversal and merge. The real skill is not knowing each pattern individually. The skill is recognizing which combination the problem requires and executing each step cleanly. So before we move to the cheat sheet, let us go through the most common mistake that cause linked list interviews to go wrong. These are not conceptual errors, these are mechanical errors in pointer handling, and they account for the vast majority of linked list failures. The first mistake is losing the .next pointer before rewiring. When you change current .next to point somewhere new, the original next node becomes unreachable unless you save a reference to it first. The fix is a single line. Save next node equals, current .next before you change anything. This should be automatic for every rewiring operation. Now the second mistake is not using a dummy node when the head might change. Many candidates try to handle head removal or head insertion with a special case logic. Under time pressure, this special case code is where a bug appears. One line to create a dummy node and one line to return dummy.next at the end eliminates this entire category of errors. The third mistake is using an array as a workaround. Some candidates convert the linked list to an array, solve the problem on the array, then convert back. Technically this works, but uses O of n extra space and completely misses the point of the problem. Interviewers ask linked list questions specifically to test in-place pointer manipulation. Using an array signals that you cannot work with the data structure directly, and that's not a good sign. The fourth mistake is not handling null inputs. If the function receives an empty list, head is none. Any code that accesses head.next without checking head first will crash. We have to start every linked list function with a base case check, which is if not head, return the appropriate value. For problems where a single node list is also a special case, check if not dead head.next as well. So the fifth mistake is returning the wrong pointer after reversal. After the reversal loop finishes, the variable head still points to the original first node, which is now the tail. The new head is previous. Returning head instead of previous gives you the tail of the reverse list, which produces a completely wrong result and is difficult to debug if you're not expecting it. And here's something important for interviews. Before rewriting any code for linked list problem, you should take 60 seconds to draw 3-4 nodes with arrows on the whiteboard. Label the pointers you plan to use: previous, current, next node, slow, fast, whatever the problem needs. Trace through the 2 to 3 steps manually. This small upfront investment catches pointer errors before they happen. Most linked list bugs are not about having the wrong algorithm, they are about rewiring the wrong pointer or forgetting to save a reference. The 60-second trace prevents both. Here's a reference card for the entire section. This slide is designed to be quickly reviewed before the interviews. The slide shows the template code for all 5 patterns in this section. The dummy node pattern was here, which we start with, essentially creates a list node with value 0, set to dot next to head, and perform whatever operation is needed, and return the w dot next. That is 3 lines of setup and eliminates all the head related edge cases. Now the fast and slow pattern for finding the middle initializes both slow and fast to the head. The loop runs while fast and fast dot next are both non-null. Inside the loop, slow advances 1 step and fast advances 2. When the loop ends, slow is in the middle loop node. Now the fast and slow pattern for cycle detection is almost identical, but inside the loop, after advancing both pointers, you check if the slow equals fast. If they are at the same node, a cycle exists. Now the reversal pattern sets the previous to none and current to the head. The loop runs while the current is not null. Inside, you have that save next node, rewire the current dot next to the previous, advance the previous to current, advance current to next node, return previous as the new head. Now the merge pattern for 2 sorted lists create a dummy node and a current pointer. The loop compares head of both lists, attach the smaller one, and advances the list pointer along with the current. After the loop, attach whichever list has remaining nodes, return the dummy dot next. The 2-pointer gap pattern for removing the nth node from the end advances fast by n+1 steps first, then moves both until fast is none, then removes the node after slow by skipping it. Every single pattern in this section runs in O of n time complexity and O of 1 space complexity. Finding the middle is O of n time, O of 1 space. Cycle detection is O of n time, O of 1 space. Reversal is O of n time, O of 1 space. Merging two lists is O of n+1 m time and O of 1 space. Removing nth node from the end is O of n time, O of 1 space. If your linked list solution uses O of n space, or other than building a required result list, that is a signal to check whether an in-place approach exists. For linked list, it almost always does. So let us bring this section together. We covered 5 patterns, and each one has a clear recognition signal that tells you when to use it. The dummy node patterns applies when the head of the list might change. It creates a fake node before the head, eliminates all the head-related edge cases with 0 complexity cost. Fast and slow pointers apply whenever you need the middle of the list, need to detect a cycle, or need to find a position later to the end without knowing the list length. The fast pointer at double speed reaches the end when the slow pointer is at the midpoint or catches the slow pointer inside the cycle. The reversal pattern applies whenever you need to reverse all or part of the list. The core discipline is this: the 3 variable tans: save next, rewire current, advance all 3 pointers. The merge pattern applies whenever you need to combine 2 sorted lists. A dummy node anchors a merged list, and you compare heads repeatedly, attaching the smaller node each time. The 2-pointer gap applies when you need to find or remove the nth node from the end in a single pass. Advance fast by n steps to create the gap, then move both pointers until fast reaches the end. Now, these patterns connect directly to the other section of the course. Fast and slow pointers are the same concept with the same direction 2 pointers on arrays from section 3, adapted for sequential access. The merge to sorted list is the building block for merge k sorted list, which we'll be covering in section 9, where a heap generalizes the merge of k input lists. The reversal pattern appears as a subroutine in many combination problems like palindrome checks, list ordering, and k group reversal. And the dummy node pattern reappears in section 7, where tree problems use a similar approach of creating helper structures to simplify edge cases. In section 7, we move to tree patterns. Tree is a natural extension of the linked list. A linked node has one dot next pointer, a tree node has two dot left and dot right. So that branching structure introduces recursion as a primary traversal rule, replacing the iterative loops we use throughout the section. The pattern you learned here, especially the pointer manipulation discipline, will carry forward directly into how you handle tree node references. Now, linked list problems roughly cover 5 to 8, 10% of the coding interview questions. They're less frequent than arrays trees, but they're still very important. Failing a linked list question sends a strong negative signal to interviewers because the pattern set is small and well documented. The 5 patterns in this section cover nearly every linked list problem you will ever encounter. Mastering them ensures that you do not lose point in the problem, that you should be within range, and every interviewer actually expects you to know them in LeetCode interviews. So over the previous sections of this course, we have covered the core patterns that appear in a large portion of coding interview problems for LeetCode and DSA problems. Now hash maps, prefix sums, two pointers, sliding windows, stacks, stacks, binary search on the answer space, and linked manipulation patterns are some of the patterns we covered in this course. Each of those sections taught you one pattern in depth with templates, examples, and practice problems. But now here's the challenge. In a real interview, the problem does not arrive with a label that says, okay, use sliding window pattern, or there's a binary search on the answer pattern. So it arrives as a paragraph of text, and the first thing you need to do is to classify it. That classification step, getting it right within the first 60 seconds, is often what separates candidates who solve the problem from candidates, who actually get stuck and do not do well in the interviews. So the final section is about putting everything together, and we'll build a decision tree that lets you classify any problem quickly. We'll map the specific single phrases that appear in the problem statements to the pattern they point to. We'll consolidate the time and space complexity of every pattern in a single reference. We'll also work through mixed patterns practice problems where you will not know which pattern applies until you analyze the problem yourself. We'll also look at the standard optimization paths from brute force to optimal, how patterns combine when a single pattern is not enough, and the most common mistakes that cause failures across all the sections we have covered. And finally, we'll close with cheat sheets for every section and a clear roadmap for what to practice next. Let's build a mental framework for classifying problems. There's a decision tree you run in your head every time you see an unfamiliar problem. With practice, this takes under 30 seconds. The first question to ask is, okay, is the input sorted or would sorting it help? If you need to find a specific target in a sorted array, that is binary search. If you need to find a pair with a target sum in a sorted array, that is two pointers moving from opposite ends. If the problem asks you for the minimum value of something such that a condition is satisfied, like let's say minimum speed such that all tasks finish within a deadline, that is a binary search problem on the answer space. If the sorting does not seem relevant, then we move on. Now the second question is the problem about a continuous range or a subarray? So if a fixed window size k is given, that is a fixed size window. If the problem asks for the longest or shortest valid range with subcondition, that is a valid variable sliding window. If the problem involves a subarray sum and the array can contain negative numbers, that is a prefix sum plus hash map combination because the sliding window invariant breaks with negative values. If continued ranges are not the focus, then we continue. So the third question is, okay, does the problem need fast lookup or counting? So things like, okay, does x variable exist in the collection? Points to a hash set. A statement like, let's say, how many times does x appear? Points to a hash map. A statement like, let's say, find two elements that satisfy condition points to a complement lookup pattern where you store elements as you iterate and check whether the complement of the current element already exists. If the lookup is not the core need, then we keep going. Now the fourth question is like, okay, so does the problem involve nested or matched structures? Matching brackets, valid parentheses, or matching HTML tags all point to a stack. Statements like next grid element or next model elements points to a monotonic stack. And the final question is the input a linked list? If the head might change during the operation, we start with a dummy node. If we need to find a middle or detect a cycle, we use fast or slow pointers. If you need to reverse all or part of the list, you use the iterative reversal technique with previous, current, and next pointers. If you need to combine two sorted lists, you use the merge pattern with a dummy node. So this decision tree is not a rigid script, it is a checklist. The goal is to make pattern recognition automatic, so so that by the time you finish reading the problem for the second time, you already have a strong hypothesis about which pattern applies. And here's why this matters in an interview. Picking the wrong pattern and spending 15 minutes before realizing you need to restart is one of the common reasons candidates do not do well on the interview. Running through the decision tree for 30 seconds at the start prevents that entirely. So decision tree classifies the problems based on type of input and what problem asked for. But there's a faster shortcut. Specific phrases in the problem statements that map directly to patterns. Think of these as trigger words. Let me walk you through the major ones. So let's say when the problem says, okay, find a pair that sums to a target. That is the hash map complement lookup pattern. You iterate through the array, and for each element, you check whether the complement, which is target minus the current element, already exists in the hash map. When you see phrases like count occurrences or frequency, that is a straightforward hash map where you accumulate counts. When you see phrases like group elements by property, like grouping anagrams together, that is a hash map where the key is normalized representation of the property, such as a sorted string or a character frequency tuple. When you see a statement or a phrase like Subarray sum equals k, it signals a prefix sum combined with a hash map. When you see a phrase like, let's say, product of array except self, this signals a prefix and suffix pass technique. For two-pointer problems, a statement phrase like pair in sorted array or threesome problem, it signals opposite direction 2 pointers. Whereas the phrases like remove duplicates in place signal same direction 2 pointers, where the slow pointer tracks the right position and the fast pointer scan ahead. For the window problems, let's say phrases like longest or shortest continuous substring signals the variable sliding window. For phrases like maximum sub of subarray of size k signals the fixed sliding window. Phrases like valid parentheses or matching brackets signal the stack, whereas phrases as next greater element or next smaller element signals a monotonic stack. Largest rectangular histogram statement phrase will specifically signal a monotonic increasing stack. Now, phrases like find target in sorted array, that signals a binary search, whereas phrases in like minimum speed or capacity, such as a condition holds, signals binary search on the answer spaces. Now, phrases like search in a rotated sorted array, it signals a modified binary search where you determine which half is sorted before deciding which way to move. For linked list problems, phrases like reversal linked list means iterative reversal with previous, current, and next pointers. Whereas the phrases like direct cycles mean fast and slow pointers, and phrases like merge to sorted list means the dummy node plus the compare heads pattern. And then again, the phrase like remove the nth node from the end means the 2-pointer gap technique where you advance one pointer n steps ahead and then move both pointers together until the leader reaches the end. Now the value of this mapping is speed. In a real interview, you do not see a problem tag with its pattern name. You see a paragraph of English text. Your ability to extract these single phrases from that paragraph and immediately connect them to a right pattern is what lets you solve, within the first 2 minutes instead of spending 5 or more minutes wondering where to begin. Once you have identified the right pattern, you need to know 2 things: what time and space complexity it gives you, and whether that complexity is fast enough for the given input size. So let me walk you through every pattern. So hash set and hash map solutions run in OF and time and OF and space. You make a single pass through the data with OF on lookups at each step, but you store up to n elements. Then prefix sums take OF n to build, and then OF 1 per range query with OF n space for the prefix array. The product prefix and suffix technique is actually OF n time, and it uses only OF n extra space beyond the output array. Now, opposite 2 pointers and same direction 2 pointers are both OF and time and OF on space because the pointers move through the array without requiring any additional storage. The fixed sliding window is OF and time with OF on space or OF k space depending on what you track inside the window. The variable sliding window is OF and time with space that depends on the problem, typically OF n or OF size of the alphabet for string problems. The threesome pattern with sorting and 2 pointers, is OF n squared time because you fix one element and run 2 pointers on the rest, repeating that for each element. The space complexity is OF 1 beyond the output. The stack and matching problems are OF n time and OF n space. Monotonic stack is also OF n time and OF n space. because each element is pushed and bound at most once. So the binary search here is of log n time and of one space. Binary search for the answer space of n log m time and of one space. Where the feasibility check takes of n and you binary search over a range of size m. All linked list operations, traversal, reversal, and merging to sorted list are of n time and of n one space. For merging, it is of n plus m, where n plus m are the lengths of the two lists. Now here's the practical application of these numbers. The input constraints tells you what complexity class you need. If n can be up to 20, even of 2 to the power n, or even of n factorial will pass. But if n can be up to 1000, of n squared still kind of will work. But if n can be up to 100,000, you need O of n log n or better. If n can be up to 1 million, you need O of n. And if n can be up to 10 to the power 9th, you need O of log n or O of 1. This is why checking the input constraints is one of the first things you should do when reading a problem. If the problem says n can be up to 100,000 and your proposed solution is O of n squared, that is 10 billion operations, so it will not pass. You need to find O of n or O of log n approach, which immediately narrows down which patterns are viable. So knowing the patterns and knowing the complexities is necessary, but you also need a repeatable process for the first 5 minutes of every interview problem. These 5 minutes set the trajectory, so if you get them right, then the rest flows naturally. But if you get them wrong, and you spend the remaining time trying to recover, which is not ideal. In the first minute, you have to read the problem completely and ask clarifying questions. Many candidates start thinking about solutions halfway through reading the problem and miss the critical details. Read the entire problem statement first, and then ask, what are the constraints on n? Can there be duplicate values? Can values be negative? What should I return for empty input? These questions accomplish two things. They give you information that narrows down the right approach, and they show the interviewer that you think carefully before acting. In minute 2, you have to identify the pattern. This is when the decision tree from slide 91 and the signal table from slide 92 come in. So what is the data structure is the input? Is it an array, a string, or linked list? What does the problem ask for? A count, a minimum, a maximum, a boolean, all valid solutions. What signal phrases appear in the problem statement? Running through these questions should point you to one or two candidate patterns. In minute 3, state the brute force approach and its complexity. Even if you already see the optimal solution, always mention the brute force approach first. You should say something like, okay, I could check all pairs, which would be O of n squared. So this statement, stating the brute force approach serves two purposes. It confirms to the interviewer that you understand the problem correctly and gives you a baseline to optimize against. In minute 4, you apply the pattern and state the optimization. You should say something like, okay, since we need fast lookup, I can use a hash map to reduce this from O of n squared to O of n. Or you can say something like, okay, since this array is sorted, I can use 2 pointers to find the pair in a single pass. State the new time and space complexity explicitly. Interviewers they specifically listen for this. Then in minute 5, you have to plan before coding. Outline your approach in 2 to 3 sentences. Describe the key steps and then start writing code. And here is what not to do. Do not start writing code immediately. Jumping into code without a plan leads to confused implementations and wasted time. Do not jump to the optimal solution without mentioning the brute force approach. Interviewers want to see your reasoning process, not just the final answer. And do not stay silent while thinking. Interviewers cannot read your mind, so if you're considering whether a hash map would help, say out loud. Narrating your thought process is how you earn credit for your problem-solving ability, even if you do not reach the perfect solution. A candidate who classifies the problem correctly by minute 2 and states a clear optimization by minute 4 is already ahead of the vast majority of candidates, and that advantage compounds through the rest of the interview. Put your pattern recognition to test. For each of the following practice problems, try to identify the pattern before I walk through the answer. In a real interview, you will not have a section title telling you which technique to use, so you will have to classify the problem yourself, so it's better to be prepared for that. So practice problem 1, let's say you're given an array of integers, you have to find the length of the longest subarray where the absolute difference between any two elements is less than or equal to a limit. Now let's take a moment to think about what patterns this signals. The key signal is the phrase longest subarray. That phrase points directly to the variable sliding window. The constraint is on the elements within a continuous range. You expand the window to the right, and when the difference between the maximum and the minimum elements in the window exceeds the limit, you shrink from the left. The tricky part is efficiently tracking the current minimum and maximum as the window changes. A brute force approach would recompute min and max for every window position, but that would add an O of n cost per step. Instead, you can use a monotonic DQ or two heaps to maintain the running min and max in O of log n, or amortized O of 1 per operation. Now let's look at practice problem number 2, which is, let's say given a sorted array, you have to remove duplicates in place, so each element appears at most twice, and then you have to return the new length. The signal here is the phrase remove combined with the phrases in place and sorted array. That points to the same direction for two pointers pattern. The slow pointer tracks the right position and the fast pointer scans ahead. The variation from the standard remove duplicates problem is that you allow up to 2 of each value instead of 1. So the right condition changes slightly. You check whether the current element is the same as the element 2 positions behind the slow pointer. If it is, skip it. If it is not, write it. The sorted order guarantees that this composition is sufficient. Now for problem 3, let's say given a singly linked list, determine if it is a palindrome in O of n time and O of 1 space. Now this is a problem where a single pattern is not enough. 3 patterns combine here. First, we use the fast and slow pointers to find the middle of the list. Second, we reverse the second half of the list in the place using the iterative reversal technique. Third, we compare the first half and the reversed second half node by node. And if all the values match, the list is a palindrome. And this is the kind of problem that tests whether you can recognize how patterns work together, which is a different and more advanced skill than recognizing a single pattern isolation. Now these patterns and problems are deliberately harder than the ones we practiced in individual sections. The difficulty is not in the implementation. It is a classification step, recognizing the right pattern when no context is telling you what to look for. So let us continue with 3 more problems. Now let's go with practice problem number 4, which is, let's say you're given an array of integers. We have to find the number of subarrays where the product of all elements is less than a given target k. All values are positive. So now the signal is the phrase subarrays combined with the condition on a continuous range. That points to the variable sliding window. But you might wonder, why does the sliding window work here when the operation is multiplication, not addition? The answer is that all values are positive, so the product strictly increases as the window grows and strictly decreases as it shrinks. This satisfies the monotonic property that the sliding window requires. If the array contains 0 or negative numbers, this invariant would break and you would need a different approach. For each position of this right pointer, the number of valid subarrays ending at that position is right minus left plus 1, because every subarray starting from left through the right and ending at the right is valid once the window condition holds. Now let's look at the practice problem number 5. So given an array of integers where every element appears twice except for 1, find that single element, and the array is sorted. Now the naive approach would be to use XOR across all elements, which works in O of n time. But the problem says the array is sorted, and when a problem gives you sorted input, that is almost always a signal to use binary search. The key insight is the index pairing property. Before the single element, every pair of duplicates sits on an even index followed by an odd index. After the single element, this pairing shifts. Duplicates sit on the odd index followed by an even index. You binary search on this property at each midpoint, check whether the pair alignment is still in the before single element pattern or has shifted to the after single element pattern. This finds the single element in O of log n instead of O of n. Now let's look at practice problem number 6, which is, let's say given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. Now this is a classic problem where multiple patterns lead to valid solution. One approach uses a monotonic stack similar in spirit to the largest rectangle in histogram problem. You process bars left to right, and when you encounter a bar taller than the one on top of the stack, you compute the trapped water for the region between them. Another approach uses 2 pointers from both ends. You maintain a left max and a right max, and at each step you process whichever side has a smaller maximum. The water at any position is determined by the minimum of the left max and right max at that position, minus the height of the bar itself. Both approaches run in O(n) time. The two-pointer approach uses O(n) space, while the stack approach uses O(n) space. Now, being able to discuss both approaches and explain the trade-offs between them is exactly the kind of depth that earns a strong, higher signal in an interview. It shows you are not just applying one memorized technique, you understand the problem well enough to see multiple valid paths. Now, here's a principle that applies to almost every coding interview problem. The brute force solution is usually O(n) squared or worse, and the optimization almost always follows one of small number of well-known paths. If you understand these paths, you can systematically find the optimal solution instead of hoping for a flash of insight. Let me walk you through each one. The first path, so when the brute force uses nested loops checking all pairs and the inner loop is doing repeated lookups, and the optimization is to replace the inner loop with a hash map. This takes you from O(n) squared to O(n). The two-sum problem is a very good example of it. The second path is when the brute force recomputes a subarray sum for each starting position. The redundant addition across overlapping ranges is the bottleneck. The optimization is to pre-compute a prefix sum array which gives you O(n) range queries, so total time goes from O(n) squared to O(n). The third path, when the brute force uses nested loops on a sorted array and the inner loop scans the remaining elements for each outer element, the optimization is to replace the inner loop with two pointers moving toward each other. This takes you from O(n) squared to O(n). The fourth part, which is when the brute force checks all the subarrays for some condition, and most of the work is redundant because shifting the edge window by one position only changes one element. The optimization is a sliding window. If you add one element on the right, move one on the left, and update state incrementally. This takes you from O(n) squared to O(n). The fifth path, when the brute force checks all remaining elements to find the next greater or next smaller element, a monotonic stack resolves all elements in a single pass. Each element is pushed once and popped once, giving you O(n) total. The sixth path says when the brute force performs a linear search repeatedly and the data is sorted, the optimization is binary search. Each search drops from O(n) to O(n). And the seventh path is when the brute force tries all the possible answer values from 1 to some maximum, testing each candidate linearly. Binary search on the answer space narrows the search from linear to logarithmic. This gives you n log m when the n is the cost of the feasibility check and m is the size of the answer range. The way to use this in the interview is pretty straightforward. State the brute force, identify the bottleneck, find which row in the table matches the bottleneck, apply the optimization from that row. This gives you a structured, explainable path from slow to fast, and the interviewer's value seeing that structured reasoning far more than the value seeing someone jump directly to the answer. The journey from the brute force to optimal, explained step by step, is one of the stronger things you can demonstrate in a LeetCode interview. So for most of the problems we have practiced use a single pattern, but many medium and hardly any LeetCode interview problems require combining two patterns. Recognizing when one pattern is not enough and knowing which second pattern fills the gap is a sign of real-world problem-solving maturity. Let me walk you through the key examples. Subarray sum equals k problem combines prefix sums with a hash map. The prefix sum converts the subarray sum problem into a complement search problem, and the hash map provides the O(n) lookup for complements. Neither pattern solves it. Without prefix sums, you have no way to represent subarray sum efficiently. Without the hash map, you have no way to find complements without a nested loop. Now, threesome combines sorting within the two pointers. So sorting the array first enables two things. Duplicate skipping becomes simple because identical values are adjacent, and the two-pointer conversion logic works because the array is on order. Without sorting, you would need a hash map approach that is harder to implement correctly with the triplicate handling. Now, group anagrams combine a hash map with a normalization step. The hash map group elements, but you need a key that treats anagrams as identical. And that key comes from sorting the characters of each string or from encoding the character frequencies as a tuple. The grouping and the normalization are separate subproblems that combine into a full solution. So the Palindrome linked list combines these three patterns, fast and slow pointers to find the middle, in-place reversal of the second half, and a linear comparison of both halves. Each pattern handles one step of the solution. Now the reordered list follows a similar structure. Fast and slow pointers find the middle, reversal splits the second half, and then you interleave nodes from both halves. Trapping rainwater can be solved with either two pointers on monotonic stack. Both approaches process the elevation map and off and time, but they reason about the problem differently. Two pointers process from both ends inwards, and the monotonic stack processes left to right, resolving the trapped water when a taller bar appears. The general principle is this: when a single pattern gets you part way to the solution, but not all the way, you should ask yourself, what is the remaining gap? That gap usually points directly to a second pattern. So prefix sums compute Subarray sums, but you still need fast lookup for complements, so you add a hash map. Fixing one element in threesome problem reduces it to a two element problem, but you still need an efficient pair finder, so you add two pointers. Fast and slow pointers find the middle of a linked list, but you still need a second half reverse for comparison, so you add the reversal pattern. Once you can solve the easy version of each individual pattern fluently, combining them under the interview pressure becomes much more manageable. So before we move to the cheat sheets, let us go through the 9 most common mistakes across all the patterns we have covered in this course. Each one is preventable with a few seconds of careful thought, but each one causes real interview failures when it is missed. First is using a list for membership checks instead of a set. Checking whether an element exists in a list is O(n) because the list must be scanned sequentially. Checking whether it exists in a set is O(1) because sets use hash internally. Any problem where you need to check whether something exists in a collection, default to a set. This single change can be a difference between an O(n) squared solution and an O(n) solution. Second, forgetting to initialize the prefix count maps with 0 mapped to 1. In the prefix sum plus hash map pattern, this initial entry handles subarrays that start from index 0. Without it, those subarrays are missed entirely. It is a one-line initialization, but forgetting it is one of the most common bugs in this pattern. Third, moving the wrong pointer in two-pointer problems. When the sum of two elements is too large, you need to decrease it by moving the right pointer inwards. When the sum is too small, you move the left pointer outwards. So the logic derives directly from solid order, but under interview pressure, it is easy to move the wrong one. Now, before adjusting to any pointer, you should be asking yourself which direction makes the sum smaller and which direction makes it larger. Fourth, confusing the update logic for longest versus shortest sliding window problems. For longest valid window, you shrink only when the window becomes invalid, and you update the answer outside the shrink loop. For shortest valid window, you shrink while the window remains valid, and you update the answer inside the shrink loop. Getting this reverse means your solution silently returns wrong answers. For fifth, storing values on a monotonic stack instead of indices. The default should always be to store indices. From an index, you can look up the value, but from a value, you cannot recover the position. In many monotonic stack problems, need the position to compute the distance or the widths. Sixth, using left equals mid with the while loop, with the while left is less than or equal to the right loop in binary search. This combination causes an infinite loop because when left equals mid, left bound never advances. The safe pattern is to always use left equals mid plus 1 when updating the left bound. Seventh, setting incorrect bounds for binary search on the answer space. The low bound should be minimum of possible answer and the high bound should be the maximum possible answer. Getting either one wrong means the correct answer might fall outside your research range. You should be stating a bounds out loud in an interview before starting the binary search loop. And eighth, losing the next pointer before rewiring nodes in a linked list. Anytime you change the current dot next, the original next node becomes unreachable, unless you save a reference to it first. So the fix is simple. Always save next node equals current dot next before modifying the current dot next. Making this the first line inside every linked list mutation loop is very recommended, so you should do that. For ninth, not using a dummy node when the head of the linked list might change. Operations like deleting the head node, inserting before the head, or merging two lists can all change which node is first. A dummy node pointing to the head eliminates the entire category of special case bugs with one line of code. So these mistakes account for majority of the interview failures for LeetCode patterns in this course. Each one is pretty fixable and each one is preventable, so being aware of them before walking into the interview room is half the battle. So please consider them and prepare for them while preparing for your LeetCode interviews. Now here's a reference card for the arrays, hashing, and prefix sum section. This slide is designed to be screenshotted and used for quick revision before interviews. Let me walk you through each template. So the hash set templates handles existence checks. You initialize an empty set, iterate through the array, and for each element you check whether it already exists in the set. If it does, you have found or duplicate. If it does not, you add it. So this runs in O(n) time and O(n) space. The hash per frequency count template handles the counting occurrences. You iterate through the array, and for each element, increment its count in the map. The get method with default of 0 handles the case where the element has not been seen before. The complement lookup template solves the two-sum pattern. So for each element, you compute the complement, which is target minus the current value, and check whether the complement exists in the map. If it does, you have found your pair. If it does not, store the current value and its index. This solves in a single pass. So the prefix sum template, it handles range sum queries. You build an array of length n+1, where each entry stores a cumulative sum up to that index. Then the sum of any range from index I to index j is simply the prefix value at j plus 1 minus the prefix value at I. The build is O(n) and each query is O(1). The prefix sum plus hash map template counts subarrays that sum to target k. You maintain a running prefix sum and map that counts how many times each prefix sum value has occurred. For each element, after updating the prefix sum, you check how many times the value prefix sum minus k has appeared, because each sum occurrence represents a subarray and that sums to exactly k. And remember, initialize the count maps from 0 map to 1 to handle subarrays starting from index 0. Every pattern in this section runs in O(n) time and O(n) space. If your array solution is slower than O(n), check whether one of these templates applies. Chances are that it does. Now here's the reference card for 2 pointers after sliding window patterns. The opposite 2 pointers template starts with 1 pointer at the beginning and 1 at the end of the array. While they have not crossed, check the current pair. If it matches the condition, return the result. If you need a larger value, move the left subpointer rightward. If you need a smaller value, move the right pointer leftward. The solid order is what makes this logic work. Both pointers move towards the center, and every step eliminates at least one candidate. The same direction 2 pointers template uses a slow pointer for writing and a fast pointer for reading. The fast pointer scans through every element. When an element qualifies to be kept, get written at the slow pointer's position and the slow pointer advances. When it does not qualify, the slow pointer stays put. At the end, everything becomes a slow pointer. Everything before the slow pointer is actually the valid output. The fixed window template computes the initial window size k, then slides it one position at a time. At each step, you add the new element entering on the right and remove the element leaving on the left. This avoids recomputing the entire window from scratch at each position. For the variable sliding window, the template differs depending on whether you want the longest or the shortest valid window, and this distinction is pretty important. For the longest valid window, the right pointer expands the window by adding each new element. When the window becomes invalid, you shrink from the left until it is valid again. The answer gets updated outside the shrink loop and the window is invalid, because you want the largest window that satisfies the condition. For the shortest valid window, the right pointer again expands by adding each element. By this time, while the window is valid, you update the answer and then shrink from the left. The answer gets updated inside the shrink loop because you want the smallest window that satisfies the condition, so you keep shrinking as long as the condition holds. Longest means shrink when invalid, so update outside. Shortest means shrink while valid, update inside. Getting this distinction right is the single most important thing in the sliding window problems. Reference card for stacks, monotonic stacks, and binary search. The matching and nesting template handle problems like valid parentheses. So you iterate the string. When you encounter an opening character, you push it onto the stack. When you encounter a closing character, check whether the stack is empty or whether the top of the stack matches. If the stack is empty or the top does not match, the string is invalid. If it matches, pop at the top. At the end, the string is valid only if the stack is completely empty. So for the next grid element template uses the decreasing monotonic stack. You iterate through the array, and for each element, while the stack is not empty, and the current element is greater than the element at the index on the top of the stack, the current element is the next grid element for that index. You pop the top and record the result, and then you push the current index. Every element gets pushed once and popped once, so the total times O(n), even though there is a while loop inside the for loop. The standard binary search template initializes left to 0 and right to n-1. While left is less than or equal to right, compute mid as left plus right minus left divided by 2, which avoids the integer overflow. If the value at mid is equal to the target, return mid. If it is less than the target, move left to mid plus 1. If it is greater, move right to mid minus 1. The key correctness guarantee is that always use mid plus 1 and mid minus 1. Never use mid alone for updating left because that causes infinite loops. The binary search on the answer template works differently. Here, left and right define the range of possible answer values, not indices. While left is less than right, without the equal sign this time, compute the mid and check whether the mid is a feasible answer. If it is, narrow the search to the left half by setting right to mid. If it is not, narrow to the right half by setting left to mid plus 1. When the loop ends, left equals right and that is the answer. The critical step is defining the feasibility function correctly and setting the initial bounds to cover the full range of possible answers. The monotonic stack and binary search on the answer are two of the most under-practiced patterns. Both appear frequently in medium and hard interview problems for LeetCode category, and both are highly mechanical once you internalize the templates.